Another kind of inductive argument concerns causes or causal reasoning. Now, we think about causes all the time in everyday life. Suppose that all of a sudden your computer screen goes black. Whoa, what made that happen? Was it the Coursera website going down, or is there some problem with your computer, or was I just playing a trick on you? Well, you need to know that in order to figure out whether or not you need to get your computer fixed. Or suppose that you make a cup of coffee. I love a good cup of coffee. Oh, that's disgusting. What went wrong? What made it taste so bad? There must be something in the coffee that made it taste bad. But what was it? What caused that horrible taste? Or think about a courtroom, a lawsuit. Someone's found guilty of murder. Well, to be found guilty of murder, you have to show that they are the one that caused the death, that their action, pulling the trigger, putting the poison in the food, whatever, caused the death. And whether you send them to prison for a long time depends on that causal judgment. So we got to get causal judgments straight. But causal judgments cannot be certain. We can't know with absolute certainty what causes what. It's just not like that in life. That's why we need inductive arguments in order to support these causal judgments that play such a big role in all of our lives. Okay, so we need inductive arguments to support causal claims. But how does that work? To get straight on that, we need to think a little bit about causation. Causal claims are about individual events. One event causes another event. For example, my phone is off, but if I push this button on the bottom, then it turns on. Great. And if I push this button on the top, then it turns off. That particular event of me pushing the button on the bottom turned it on, and the particular event of me pushing the button on the top turned it off. But behind that connection between the particular events lies a general rule. Every time I push the button on the bottom, it turns on, and every time I push the button on the top, it turns off. If it didn't hold as a general rule, it wouldn't be a causal relation, right? So how can we test general principles? That's going to be the topic for this whole week. The big question is going to be, which cases in the data do we need to look at? And how do we know when we have enough data to really believe in a general principle? But the first thing we need to do is to draw an important distinction between two different types of general principles. Sometimes we say that one thing is a sufficient condition for another thing. And that means basically that whenever you have the first thing, you're also going to have the second thing. But sometimes we're going to claim that something is a necessary condition for the second thing. And basically, again, that means that if you don't have the first thing, you're not going to have the second thing. And it's going to be crucial to distinguish sufficient conditions from necessary conditions, because people confuse them all the time, and we need to get them straight. So let's start with a very simple example. First, being a whale is sufficient for being a mammal. Well, that's because every whale is a mammal, so if you've got something that's a whale, you know you've got something that's a mammal. Okay? But being a whale is necessary for being a sperm whale. If you're not a whale, you're not a sperm whale. You can't be a sperm whale without being a whale. So being a whale is necessary for being a sperm whale, and being a whale is sufficient for being a mammal. One way to illustrate this is to draw them into circles. So if you know that there's a large group of mammals, that's a big circle, but within that is the set of whales, which is smaller than the mammals, but even within the whale circle, there's a set of sperm whales. Then you know that being a whale is sufficient for being a mammal because everything in the whale circle is in the mammal circle, and being a whale is necessary for being a sperm whale because everything that's not in the whale circle is also not in the sperm whale circle because the sperm whale circle is totally inside the whale circle. Okay? Now let's try to formulate a definition of necessary and sufficient conditions a little more precisely. The definition for sufficient conditions and necessary conditions is a little different with events than it is with features. So we're going to give you two different versions, and you can really use the one that applies to the case at hand. We can define a sufficient condition by saying that F is a sufficient condition for G if and only if, that is, just in case, whenever an event of type F happens, then an event of type G also happens. And to put it more appropriately for features, we can say that anything that has the feature F will also have the feature G. So in our whale example, anything that's a whale is also a mammal. Anything that has the feature of being a whale also has the feature of being a mammal. So being a whale is sufficient for being a mammal. And we can do the same thing with necessary conditions, but we got to put the negations in there. That's the only difference. F is a necessary condition for G if and only if, that is, just in case, whenever an event of type F does not happen, then an event of type G also does not happen. By putting the negation on both sides, you turn it into a necessary condition. And for features, we can say anything that does not have the feature F does not have the feature G. So back to our whale example, anything that is not a whale is not a sperm whale. So being a whale is necessary for being a sperm whale. And that's how our definitions work. Now, since you took propositional logic a few weeks ago with Rom, it might help to think of this as equivalent to the propositional forms. So you can think of F is sufficient for G is like F, if F, then G, or F horseshoe G. It's not really quite the same. It's different because you need quantifiers, but if you think of it that way, it won't hurt. And then to say that F is necessary for G is kind of like saying, if not F, then not G. Or in symbols, not F, horseshoe, not G. And thinking of it along those lines is, as again, not quite right because there are no quantifiers, but it's close enough and it might help you understand the distinction between sufficient conditions and necessary conditions. The same concepts apply in causal examples, but they're a little bit trickier to apply. And the main reason is that word whenever, because it's a quantifier and it applies to a restricted domain of discourse. Now, you don't know what that means because we haven't studied that yet, but the point is that it only holds whenever in a certain range of cases, not just any old case. So, to get clear about that, let's look at an example. Striking this match right here, right, is sufficient for lighting it. So when I strike it, I light it. Okay? And striking the match on a rough surface is necessary for lighting it, because if I strike it on a surface that's not rough, it doesn't light. So now we know that striking it is sufficient and striking it on a rough surface is necessary, but wait a minute, that can't be right. It can't be true that whenever you strike the match, it lights, because we know that when you strike it on a surface that's not rough, it doesn't light. So how do we get that striking it is sufficient for lighting it when we know that if you strike it on the wrong place, it's not going to light? And the answer is that when we say whenever we strike it, we're taking for granted that we're talking about a normal match, maybe just this one, with the right chemicals on the end. And then we're talking about striking it, we're talking about striking it in a certain way at a certain place. So when we say whenever, we're saying whenever we strike it on that surface, then it will light. I mean, for example, if you were to take the match and you were to start with a regular match, but then dip it in the coffee, that still tastes horrible. Then it won't light when you strike it because it's wet. So in causal cases, you're always saying that within a certain range of circumstances, it will hold. Whenever, in those circumstances, you strike the match, it will light. And the same point holds for necessary conditions. So, this match, this box, rough surface, it's not lighting. Well, why not? Because if you don't strike the match, it won't light, right? No, that's not right either. Because if you take another match and you light it, then look, I can light this match without striking it. So it turns out that necessary conditions and sufficient conditions in causal cases have to be understood as holding as a general rule within appropriate circumstances. And that means that we have to change our definition of necessary conditions and sufficient conditions to make that clear. To be strictly true, then, we need to qualify the definition with the phrase in normal circumstances. And the in normal circumstances tells us how the term whenever applies. So then, F is a sufficient condition for G, if and only if, in normal circumstances, whenever F happens, G also happens. Or, in normal circumstances, anything that's an F is also a G. And the same holds for necessary conditions. F is a necessary condition for G if and only if, or just in case, or that's what this means, is that in normal circumstances, whenever F does not happen, G does not happen. Or, for features, in normal circumstances, for normal cases, anything that's not an F is also not a G. Now, of course, what counts as normal circumstances is going to be a tricky term that changes from case to case. And this definition applies in a lot of different kinds of cases. We already saw one case. That's the conceptual case. So let's look at that first. Being a whale is sufficient for being a mammal. Now notice, being a whale is not necessary for being a mammal because there are lots of mammals that aren't whales, like sea otters. And being a whale is necessary for being a sperm whale, but it's not sufficient for being a sperm whale because there are lots of whales that aren't sperm whales. Okay? So that's a conceptual case. And then we saw a causal case. Striking this match is sufficient for lighting it, and striking this match on a rough surface is necessary for lighting it. Okay? But it also have the same distinction in other kinds of cases. Here's a moral example. Torturing someone just for fun is sufficient for doing something wrong. Because torturing somebody just for fun is always wrong. You shouldn't do it, period. Or at least so someone might claim. I think so, at least. And doing something wrong is necessary for being punishable. Now notice that torturing for fun is not necessary for doing something wrong, because you can do wrong without torturing for fun. Okay? And doing something wrong is not sufficient for being punishable because you ought to get a fair trial before you're punished. If you do something wrong and didn't get a fair trial, you're not ready to be punished yet. But notice, I've now made some controversial claims here. Some people might say that doing something wrong is not really necessary for being punishable. Sometimes we ought to punish people even when they didn't do something wrong. So when you get into the moral realm, it's going to be a little more controversial, and that shouldn't be surprising. In any case, the main point here is that we try to understand the claims that are being made, and in particular to distinguish the claim that something is sufficient from the claim that that thing is necessary. Okay? Distinguishing sufficient conditions from necessary conditions is crucial, because if you mess these up, you'll make all kinds of mistakes in arguments. So let's do a few examples, a few exercises, in order to be sure that you understand that before we look at the tests for sufficient conditions and necessary conditions. Now that we understand the distinction between sufficient conditions and necessary conditions, we need to ask how we can tell which conditions are necessary and which conditions are sufficient. So we're going to have one pair of tests for sufficient conditions, one pair of tests for necessary conditions. For each of these, we're going to have a positive test and a negative test. So, for example, the negative test for sufficient conditions is going to tell you what's not a sufficient condition, and the positive test for sufficient conditions is to tell you what is a sufficient condition. And one of these is going to be deductive and the other is going to be inductive. So let's go through these various tests one by one. First of all, you get the negative version of the sufficient condition test, which basically says that something X is not a sufficient condition of something else, Y, if there is any case where X is present and Y is absent. You don't have to be a lot of cases, just one. If there's any one case where X is present and Y is absent, then that shows you that X is not sufficient for Y. This test is negative because it tells you what is not a sufficient condition for Y. It does not tell you what is a sufficient condition for Y. Basically, it says that if there's one case where X is present and Y is absent, then that's a counterexample to the generalization that whenever X is present, Y is always present. Because if Y is absent, it's not present. So we've now got basically a deductive argument against the generalization that whenever X is present, Y is present as well. And because it's deductive, that means it's not defeasible. If you add other cases, it doesn't matter. More information in the premises, the argument's still going to be valid. Because as long as you have one counterexample, that shows that X is not sufficient for Y, because it's not the case that whenever X is present, Y is present. To see how this negative sufficient condition works, let's go through an example. Now, the example we're going to talk about derives from the great comedy classic Airplane with Leslie Nielsen. And so we've added a link that you can check out if you want. But I'll warn you, there's some offensive parts of this comedy, and you ought to be ready for that. Partly to avoid those offensive parts, and also so that we can really get all the cases straight and specify them in the way we need to, we're going to use our own example, and we're going to call it the banquet. So what happens is that there are a group of people who are eating together, and they eat a full meal. They have a soup course, they have a main course, they have some wine, then they have dessert. And the meal goes pretty well until the end. Oh, that was great. I love the tomato soup.
Yeah? This fish is to die for.
Yeah, and this wine, oh my gosh, it was so good.
I love the combination of both the fish and the red wine together.
Yeah, it's so sad that the dinner is over. Oh man, when I stood up, my stomach started hurting.
No, mine did too.
Oh man.
Ow, really? I feel great.
Yeah, I feel fine.
Vegetarian.
Oh man, what's making them all feel this way?
way.
And the question is, what caused them to die? So we check a number of different things. They weren't shot. They weren't stabbed. There was poison. And where was the poison? Well, we checked their water glasses and we checked for injection points if somebody shot the poison through a syringe. None of that. So we figure the poison must have gotten to them through the food. And now we need to look at all the different people who were at the banquet and what each particular person ate at the banquet in order to figure out which of these different food items was the one that killed them. So we have a little chart. Anne went to the banquet, Barney went to the banquet, and Kathy went to the banquet. So each of the rows on this chart indicates a different diner, a different person who ate at the banquet. And each of the columns indicates what they ate or drank. So one column's for the soup course, one column's for the main course, one column's for the wine, one's for the dessert, and then of course the last column to the right tells you whether they lived or died. And what we need to figure out is which of those food items or drinks is what caused their death. We're going to use the letter Y to refer to the target feature or the effect, the thing that is caused. And we're going to use the letter X to refer to the different candidates for the cause. And our question is, which candidate X is sufficient for the target Y? And the table with all the diners and all the courses represents all of the data that we have available to us to answer that question. So let's look first at the very first course, the soup course. What does the soup course show us? Does it show us that anything is not sufficient for death? Yes. It shows tomato soup is not sufficient for death. Why? Because Anne had tomato soup and she didn't die. So it's not true that whenever you have tomato soup you die, since Anne had tomato soup and did not die. So that candidate X, tomato soup, is not sufficient for the target Y, death. Kathy shows the same thing. She shows that tomato soup is not sufficient for death. Now, what do we learn from the main course? Do we learn that anything is not sufficient for death? Yes. We learn that chicken is not sufficient for death because Anne has chicken and doesn't die. And what does Kathy tell us is not sufficient for death? The case of Kathy tells us that beef is not sufficient for death. So now we have a whole list of things that have been ruled out as sufficient conditions. Tomato soup, chicken, and beef. And what about the wine course? What does Anne tell us in the wine course? It tells us that white wine is not sufficient for death. And what does Kathy tell us in the wine course? Red wine is not sufficient for death. Now notice that it's Anne and Kathy that are giving us all this information about what's not sufficient. And that's because they didn't die. So anything that they ate or drank cannot be sufficient for death. But Barney did die. So the things that he ate and drank still might be sufficient for death. They're not ruled out by the negative sufficient condition test. Of course, tomato soup was ruled out by the other cases, and red wine was ruled out by Kathy. But still, what about fish? Could fish be sufficient for death? It's not ruled out, right? It's not ruled out by the negative sufficient condition test because there's no case in this data where somebody eats fish and doesn't die. But does that mean that eating fish is sufficient for death? No, because this is just the negative sufficient condition test. It tells you what's not sufficient. It doesn't tell you what is sufficient. Okay? But still, we want to look at the rest of the chart and figure out, is there anything else that's not ruled out as a sufficient condition? Well, pie is ruled out as a sufficient condition because Anne had pie but is still alive. Kathy shows that ice cream is not a sufficient condition for death, but cake still might be a sufficient condition for death, for all we've read. So now we've got two candidates. Fish and cake still might be sufficient conditions for death. They're not ruled out by the negative sufficient condition test, but that doesn't mean they are sufficient for death. In order to conclude that they are sufficient conditions for death, we need to apply not the negative sufficient condition test, but instead the positive sufficient condition test. The positive sufficient condition test tells us when we have a good reason to believe that X is a sufficient condition. What makes it positive is it tells you that you have a reason to believe that X positively is a sufficient condition, unlike the negative test. And it says that you have a good reason to believe that X is a sufficient condition of Y if all of the following conditions are met. Now, I want to warn you, there are going to be 4 conditions, and they have to all be met in order for you to reach a positive conclusion, or be justified in reaching a positive conclusion that X is a sufficient condition of Y. Now, the first condition is pretty simple. It simply says, we have not found any case where X is present and Y is absent. Basically, it says you've already passed the negative part of the sufficient condition test. You can't rule out X as a sufficient condition on the basis of any cases. The second part says that we've tested a wide variety of cases, including cases where X is present and Y is absent. And the reason that we have to have this condition is that without it, we could reach really silly conclusions much too easily. For example, on the basis of the data that we looked at before, we could reach the conclusion that pea soup is sufficient because there wasn't a single person who had pea soup and didn't die. There can't be a case where somebody had pea soup and didn't die if there isn't a case where somebody had pea soup. That's why we have to check cases where X is present. But similarly, imagine that the only case that we knew was Barney, right? And that means nobody lived. Everybody died. Well, if everybody dies, then we don't have any cases where somebody had tomato soup and didn't die, or where somebody had fish and didn't die, or where somebody had beef and didn't die, or where somebody had cake and didn't die. Whatever they had, they died because everybody died. So if everybody dies, it's really hard to tell which of the different candidates is the one that's really causing the death. So that's why we have to have some cases where X is present, that is, where the candidate that we're testing is present, and other cases where the target feature, Y, is absent. And that's what the second part of the positive sufficient condition test tells you that you need. Now, those two clauses are pretty trivial, but the next one's more important, and it's also a little bit trickier. What it says is that if there are any other features that are never present where Y is absent, then we've tested cases where those other features are absent, but X is present. Now, this can be confusing, but the basic idea is that if there are two competing hypotheses, two competing candidates for a sufficient condition, and neither one is ruled out by the negative sufficient condition test, then we need to look at cases that would decide between those hypotheses. Now, in our example, we saw that neither fish nor cake is ruled out as a sufficient condition. And if we want to decide whether it's fish or cake that really is a sufficient condition, then what we need to look at is a case where fish is present but cake is not, and a case where cake is present but fish is not. We can't be sure from the first 3 cases because we don't have that combination of fish and cake, so we have to do a little more research. And luckily for us, not for them, of course, because one of them dies, but luckily for us, Doug and Emily were also at the banquet. And Doug had tomato soup, beef, red wine, and cake and lived, and Emily had tomato soup, fish, red wine, pie, and poor Emily died. The crucial thing here is that Doug had cake but not fish, and Emily had fish but not cake. Now, do these cases help us determine whether cake is sufficient for death? Yes, because one of these new cases rules out cake as a sufficient condition of death. Which one does that? Well, it's Doug, because by the negative sufficient condition test, Doug had cake and didn't die, so that shows you that cake is not sufficient for death. Now, does Emily rule out anything as a sufficient condition for death? No. Why not? Well, because she died. And if somebody dies, they can't rule out something as a sufficient condition for death. Cases of death can't rule out what's sufficient for death, because to rule it out, you need a case where the candidate's present and the target's not present. Okay? So the cases that rule out something as a sufficient condition of death are going to be the cases without death. Anyway, fish still might be a sufficient condition for death. So fish seems to be the only remaining candidate because we ruled out cake. So fish is the only remaining candidate for a sufficient condition, at least among those on the list. Now, we can conclude fish is a sufficient condition for death, right? No. Because remember, I warned you, there are going to be 4 conditions. We need all those conditions to be met in order for us to be reasonably conclude that something's sufficient, and there's one more to come. Now, why do we need more? The answer really is that we don't know whether all the different features that might have caused the death are on our list. We've only looked at the soup course, the main course, the wine, and the dessert. It might be something else. So we need to add one more clause, this last positive clause, to our positive sufficient condition test. Namely, that we've tested enough cases of various kinds that are likely to include a case where X is present and Y is absent if there is any such case. So this clause is obviously going to be hard to apply, right? It's not mechanical. How do we know whether we've tested enough cases of various kinds? We have to know what kinds of things can cause death and which kinds of things can't cause death. That's going to depend on background conditions, background knowledge, right? We need to know something about potential causes of death, what can and cannot cause death. And we need to take that for granted in applying this last cause. So it's not going to be simple at all. But if we do know that there has to be some sufficient condition, I mean, after all, people don't just die for no reason. And if we know that nothing else could be a sufficient condition, just maybe we checked the water and we looked for syringe marks and there were no bullet holes and so on, then we have at least some reason to believe that the sufficient condition must be somewhere among the features that we're testing. Some people might say it's something else. After all, it could be, I've got an idea, it could be the fact that Barney and Emily both have the letter E in their name. But you know that's not going to cause their death. That's just common sense background knowledge. And we looked at their glasses. There was no poison in their glasses. So we have at least some reason to believe that the sufficient condition must lie somewhere among the features that we're testing. Now, this argument is not deductive. If something fails the negative sufficient condition test, then it's valid to conclude that that candidate is not a sufficient condition for that target. But if something passes the positive sufficient condition test, then the argument's not valid. It's possible still that this is not sufficient, and that argument, namely an application of the positive sufficient condition test, can be undermined by future data. It's defeasible, like all inductive arguments. For example, we haven't mentioned Fred, Gertrude, and Harold yet. And what do they show? Well, wait a minute. Gertrude shows that fish is not sufficient after all. Notice that all the data before Fred seemed to point to the conclusion that fish was sufficient for death, but it just takes one more case, Gertrude, to show that fish is not really sufficient for death after all. That shows that it's an inductive argument, and that means that it's going to be defeasible. Still, of course, the inductive argument can be strong if we have enough data, we've looked at enough cases, and our background knowledge really is reliable. So we're not saying that inductive arguments are no good, but the point is that they're defeasible. They're going to be better when we've got more data, when our background assumptions are more reliable, and strength then is going to be a matter of degree and can go from slightly strong to very strong. In this case, because of Gertrude, we know that fish is not sufficient. So we'll have to think more about what still could be sufficient. But first, let's ask what's necessary. Last time we looked at sufficient condition tests, and they tell us what is or is not a sufficient condition. But we also need to know which factors or features or candidates are necessary conditions. So this time we're going to look at necessary condition tests. And as with sufficient condition tests, there are going to be two of them. There's a negative necessary condition test that tells you what is not a necessary condition, and then there'll be a positive necessary condition test that tells you what is a necessary condition. So first, the negative necessary condition test. It says simply that X is not a necessary condition of Y if there's any case where X is absent and Y is present. Because to be a necessary condition, it has to be the case that whenever X is absent, Y is absent too. So if there's even one case where X is absent and Y is present, that's a counterexample to the universal claim that whenever, that is in all cases, where X is absent, Y is absent. Okay? So let's apply this to our data so far. But let's look first just at the first three people, Anne, Barney, and Kathy. You remember them from last time. They were at the banquet. Is pi a necessary condition of death? Well, is there a case where pi is absent and death is present? Yes. That means that pi is not a necessary condition of death. Which case shows us that? Well, it's Barney. Notice that it's not Anne. Some people get confused about this. But what Anne tells us is that pi is not sufficient for death. It's Barney that tells us that pi is not necessary for death, because with Barney, you get death without pi. So pi was not necessary for Barney to die. So it's the cases of death, namely Barney, out of these three, that tell us what's not necessary for death. Now, the case of Barney also tells us that another dessert is not necessary for death. Which one is that? Ice cream. Because Barney also didn't have ice cream and he died. So he died without having ice cream. So ice cream is not necessary for death. So what might be necessary for death? Tomato soup might be necessary for death, because out of these three cases, there's nobody who dies without having tomato soup. Fish might be necessary for death, because out of these cases, there's nobody that dies without having fish. Red wine might be necessary, and cake might be necessary. Because Barney's the only one who dies, all of those things still might be necessary for death. And the only way to rule out some of those candidates so as to narrow down the field is to get more data. So remember Doug and Emily, our old friends from the banquet. What do they show us? Is cake necessary for death? No, because now we have a case of someone dying without eating cake, namely Emily. And is fish necessary for death? Whoa, well, both Emily and Barney had fish, so there's nobody who dies without having fish. So far, for this data, it looks like fish still might be a necessary condition for death. So, since it survived this far, I guess we can conclude that fish is a necessary condition for death? No way. Because remember, this is just the negative necessary condition test. It tells us what is not a necessary condition. We still are not in a position to conclude that fish is a necessary condition for death. For that, we'll need to look at the positive necessary condition test. The positive necessary condition test is just like the positive sufficient condition test, except that you change absent for present in the two positions throughout the test. So, it tells you that we have good reason to believe that X is a necessary condition of Y if all of the following conditions are met. Remember, it's got to be all four that are met before you can reasonably conclude that it really is a necessary condition. And it's positive because it allows you to conclude positively it is a necessary condition. So the first clause is that we've not found any case where X is absent and Y is present. Again, it's just like the sufficient condition test, except that we've changed absent for present. And what this is saying is that this particular candidate, X, has passed the negative necessary condition test. And you got to do that because if you're ruled out as a necessary condition, there can't be adequate reason to conclude that you are a necessary condition because you've been ruled out. Second, we've tested a wide variety of cases, including cases where X is absent and cases where Y is present. I mean, after all, if nobody dies, you can't test to see what's necessary for death. You're not going to be able to have enough data. You're going to reach silly conclusions. So we need to make sure that we have a bunch of cases where X is absent and a bunch of cases where Y is present, or we're not going to have any reason at all. So remember our data. What about tomato soup? Is tomato soup necessary for death? Well, it might be because we didn't have any cases in the first three, at least, where nobody drank tomato soup. So that would be a silly conclusion to reach. We need to look at cases where people didn't have tomato soup in order to determine whether the tomato soup really was necessary to cause death in that case. Now, the third condition says that if there are any other features that are never absent where Y is present, then we've tested cases where those other features are present, but X is absent. And the idea here is that you've got competing hypotheses. Some people might think that one candidate is a necessary condition for death, and other people might think that another candidate is a necessary condition for death, and some people might say, well, I don't know which one, because neither one's ruled out. Well, if neither one's ruled out by the necessary test, then we need to have cases that decide between the competing candidates, the competing hypotheses, to determine what really is necessary for death. So that means that in our example, at least for the first three cases, Anne, Barney, and Kathy, fish and red wine and tomato soup all still might be necessary conditions of death. And to figure out which one really is, we want to look at a case of somebody who has fish and red wine, but not tomato soup. Somebody who has fish and tomato soup, but not red wine. And somebody who has tomato soup and red wine, but not fish. So we need to do more research. Now, luckily, again, lucky for us, but not for them, we have additional people who came to the banquet and had just those combinations, namely Fred, Gertrude, and Harold. Fred had fish and red wine, but not tomato soup. Gertrude had fish and tomato soup, but not red wine. And Harold had tomato soup and red wine, but not fish. So, what does Fred tell us? What does this case rule out as a necessary condition? It tells us that tomato soup is not a necessary condition for death because Fred died without having tomato soup. He had leek soup instead, and no tomato soup. What does Gertrude tell us? What does this case rule out as a necessary condition? Nothing. Why? Because Gertrude didn't die. And it's only the cases where people die that can rule out necessary conditions. What about Harold? What does Harold tell us? Same thing. Harold didn't die, so he doesn't rule out anything as a necessary condition. Okay. Gertrude might show us that fish is not a sufficient condition for death. We already talked about that in the last lecture. But since Gertrude and Harold are alive and don't die, they can't rule out candidates as necessary conditions. So far, it looks like fish might be necessary but not sufficient for death, given this set of data with Anne through Harold. It also looks like red wine still might be necessary but not sufficient for death. So, is it reasonable to conclude that both of these features, both of these candidates, are necessary and not sufficient for death? No, not yet. Because remember, there's a fourth condition. And the fourth condition says that we've tested enough cases of various kinds that are likely to include a case where X is absent and Y is present, if there is any such case. And as with the positive sufficient condition test, this is going to require background knowledge about what kinds of things might or might not be causally relevant, might or might not be necessary and sufficient conditions for death. It's going to be defeasible. It's not going to be valid because it's an inductive argument. But still, we can get pretty good reason to believe that something's a necessary condition for death if we have enough cases with enough variety. And that's what this positive necessary condition test is telling you. What kinds of cases you need, what kind of variety you need. Of course, the more cases and the more variety, the stronger the reason, because inductive arguments come in degrees, but we've got at least some good reason when these conditions are met. But if we've got both fish and red wine as being necessary but not sufficient for death, well, what is sufficient for death? That's what we'll have to talk about in the next lecture. Last time we ended with a bit of a mystery. We concluded that fish still might be necessary and not sufficient for death, and red wine might be necessary, but it's definitely not sufficient for death. And the question is, well, if neither of those is sufficient, what is sufficient? And to answer that question, we've got to look at complex conditions. Now, complex conditions are just conditions or features or candidates that are combinations of other candidates or features or conditions. They might be a negation, not having fish. They might be a disjunction, having either fish or beef. But we're going to look at conjunctions. That is, having some combination of two or more of the food and drink at the banquet. And we're going to understand these in exactly the same way we understood the simple or atomic conditions or features or candidates. So, for example, we're going to use the same definition of a sufficient condition. F is a sufficient condition for G. Well, what that means is that whenever F is present, so is G. And then we're going to have a negative test for a sufficient condition. This is just reminding you of a couple of lectures ago, that X is not a sufficient condition of Y, that is, of a certain target like death, if there's any case where X is present and Y is absent. Now notice, since we used X and Y as variables, you can stick anything in for them. So to get a conjunctive condition, we're going to simply substitute in the conjunction W and X. So W and X, that combined conjunctive candidate, is not a sufficient condition for Y if there's any case where both W and X are present and Y is absent. Just like in the other cases, but we're just using a conjunction to replace one of the variables. And we can look at our data from before to determine which conjunctions are and are not sufficient conditions for death. So, are there any conjunctions that still might be sufficient conditions for death? What about tomato soup and chicken? Maybe when you have tomato soup and chicken together, that'll kill you. Nope, that can't be. Why not? Which case rules out the conjunction of tomato soup and chicken as a sufficient condition of death? Anne does. Because Anne had tomato soup and chicken, but she didn't die. What about red wine and cake? Is red wine and cake together as a combination, as a conjunction, is that sufficient for causing death? Well, it caused death, or it was related to death in the case of Barney, but is there another case where you have red wine and cake without death? Look down the list and you'll see it's Doug. Doug shows us that red wine and cake are not sufficient for death. Now, which conjunctions are not ruled out as sufficient conditions for death? Well, what about fish and red wine? Could that be sufficient? Well, Barney has fish and red wine, and he dies. And Emily has fish and red wine, and she dies. And Fred has fish and red wine, and he dies. And there's nobody else that has fish and red wine who doesn't die, because there's nobody else who has fish and red wine other than those three. So it looks like fish and red wine might be a sufficient condition for death. Okay, what about fish and cake? Could that be sufficient? Yeah, so far that could be sufficient as well. Fish and cake, Barney has them and dies. Fish and cake, Fred has them and dies. So fish and cake might be a sufficient condition of death, according to the data that we have so far. So let's look next at what's necessary, because the same points are going to apply. We're going to take the definition of a necessary condition. F is a necessary condition for G if whenever F is absent, G is absent. We're going to use the same old negative test of a necessary condition. X is not a necessary condition of Y if there's any case where X is absent but Y is present, because that shows X is not necessary for Y. And all we have to do is to substitute a conjunction in for the variables X and Y in order to apply this test to conjunctive cases. So a conjunction, W and X, is not necessary for Y. If there's any case where you have that conjunction, both W and X, as being absent, and yet Y is present. So now we have a negative test for a conjunctive necessary condition. So let's go back to our data. Is leek soup and fish necessary for death? No. Well, who shows that? Barney, because Barney died without having leek soup and fish. Is there any other case that shows that? Yeah. Emily shows that because she died without having leek soup and fish. So that combination is not necessary for death. Okay, so Barney and Emily show that leek soup and fish is not necessary for death. What about tomato soup and fish? They both had tomato soup and fish, so maybe tomato soup and fish is necessary for death. Does that work? No, because of Fred. Fred dies without having tomato soup and fish, because he has leek soup and fish. So Fred shows us that the combination tomato soup and fish is not necessary for death, because you can die without that combination if you have leek soup and fish instead. So neither of those combinations is necessary. What might be necessary? Which combination is not ruled out as necessary? Well, here's one. Fish and red wine. Fish and red wine might be necessary for death because everybody who died at this banquet had fish and red wine. There was nobody who died without having fish and red wine. So fish in red wine is not ruled out as a necessary condition of death. But wait a minute. Fish in red wine was also not ruled out as a sufficient condition for death, because everybody who had fish and red wine together died. That means that this particular combination, fish and red wine, is both necessary and also sufficient for death, at least given the data that we have so far. I won't go through developing the positive test for conjunctions, because it's going to be just like the positive necessary condition test and the positive sufficient condition test that we went through in previous lectures. You just substitute conjunctions for the variables and you get those tests. But it looks like for the data so far, we've got at least some reason to believe that fish in red wine is necessary for death and also sufficient for death. Great. Now we know which combination meets those tests, but what does that tell us? We don't know any mechanism, right? Why would fish in red wine cause death? Well, obviously, these people died of bad taste. The chef, who'd worked all afternoon on the fish, can't stand the fact that people might eat his beautiful fish and have red wine, which is going to destroy the taste of the dish. So anybody who ordered red wine with the fish, he poisoned them. That would be the mechanism for why everybody who had fish with red wine died. You know, there might be some other story about how some chemical in the fish interacted with the red wine, but if you can rule that out from background knowledge, then we've got a pretty good reason to believe that somebody back there in the kitchen, probably the chef, is the one who was mad at them and poisoned them. They died of bad taste. Now, we need more research to be sure. We need lots more candidates. We need to test various combinations. But that's just an inductive argument. Inductive arguments never make you absolutely certain that the conclusion is true. They're defeasible. They're not valid. We know all that. But at least we have some evidence to believe that fish and red wine is necessary and sufficient for the death. That's what caused these people to die, and it's the chef who ought to go to jail. We've gone through one example in some detail, but like many other things in this course, the best way to learn this material is to practice, practice, practice. So let me give you a little hint. You can create all the exercises you would ever want just by taking the chart that we've looked at in the last couple of lectures that goes from Anne through Harold and change what each of them had in the soup course, or what each of them had in the main course, or what each of them had in the wine course, or what each of them had in the dessert course, or change which ones lived and which ones died. And you can create more examples to practice the necessary condition tests and the sufficient condition tests. And if you want to know whether you got it right, bring your chart and your answer to the discussion forums, and the other students in the course can help you out by telling you whether they agree about what's necessary and sufficient in the setup that you created. So if all you students out there in Coursera land practice, practice, practice by changing the banquet to meet your own specifications, then you'll all learn better how to distinguish necessary and sufficient conditions and how to test for necessary and sufficient conditions. So go off and have some fun with it. Last time we talked about tests for sufficient conditions and necessary conditions. And those tests will work fine in a lot of cases, but they're not going to work in all cases. Because remember, we were looking at what caused death. Death, well, you're either dead or you're not dead. And we talked about whether the person had fish or not. We didn't look at cases where people ate just a little bit of fish. They either ate fish or they didn't eat fish. But there are a lot of causal relations that hold not between absolute or dichotomous properties, you're either dead or not dead, you ate fish or you didn't eat fish. Instead, some causal relations hold between properties that come in degrees. For example, carbon dioxide and global warming. Well, there's always carbon dioxide. The atmosphere always has some of it. So you can't say that carbon dioxide is sufficient for causing heating in the world, since sometimes the world cools down. And there's still some carbon dioxide then. So what we need to think about is the degree of carbon dioxide. And sure enough, that's what the Intergovernmental Panel on Climate Change, the IPCC, used to reach its conclusion that increasing levels of carbon dioxide were causing increasing global temperatures. And we can't use the sufficient condition test or the necessary condition test, but we can still reach a conclusion about causation, and we can even know the mechanism for the causation. The carbon dioxide reflects the heat from the sun back to the earth and traps it in like a greenhouse effect, as it's called. So the question for this lecture is, how are we going to use arguments to justify those kinds of causal claims? So let's look at another example. Suppose a runner runs a mile and it takes them 10 minutes. Why were they so slow? Well, maybe because they were really heavy. Now, weight can't be sufficient for running slow because everybody's got a certain weight. So it's not an on-off property. It's a property that comes in degrees. And again, the heavier, the harder it's going to be to run. We know the mechanism because it takes more energy to move a heavy body. So we've got a pretty good causal story and a pretty good causal hypothesis, but you can't use the necessary and sufficient condition test because we're dealing with properties that come in degrees. A third example, suppose the wages go down. Well, that's because the unemployment was high. There's always some unemployment. Wages are never as high as you'd like them to be. So how do you get a causal claim? Well, it's because the more unemployment there is, the lower the wages are, because if a lot of people are unemployed, they're willing to take jobs for a lot less wage. So we've got a causal story, we've got a causal claim. They seem to be justified, but you can't use the necessary and sufficient condition test. You need a different test. And the test you need has to deal with properties that come in degrees. And the test that does that is called the method of concomitant variation. It was developed by John Stuart Mill in the 19th century. Brilliant philosopher. He also developed tests that basically what we've been calling the necessary condition test and the sufficient condition test parallel. He gave them different names, but it's the same basic idea. This lecture is on the method of concomitant or concomitant variation, also developed by John Stuart Mill in the 19th century. Now, in order to apply the method of concomitant or concomitant variation, the first thing we got to get straight is the idea of what a concomitant or concomitant variation is. Well, to avoid that word, people these days call them correlations. And the first kind of correlation we got to understand is a positive correlation. X and Y are positively correlated when an increase in X is associated with an increase in Y, and a decrease in X is associated with a decrease in Y. That's what a positive correlation is. In contrast, a negative correlation is when an increase in X is associated with a decrease in Y, and a decrease in X is associated with an increase in Y. That's why they're negatively correlated, because increase is associated with decrease. Whereas they're positively correlated when increase and increase are associated and decrease are associated. So let's look at some examples. First of all, calorie intake is associated with weight. The more calories you take in, the more weight you're going to gain. So they're positively correlated. Whereas weight and exercise are negatively correlated. The more exercise, the less weight, because it burns off those calories you took in. So you get a negative correlation between weight and exercise and a positive correlation between weight and calorie intake. Another example, height and age are positively correlated before the age of 20 because people tend to get taller as they grow older. But height and age are negatively correlated after the age of 60 because the space between people's vertebrae tend to decrease after a certain age. So this shows that two things can be positively correlated in some circumstances and negatively correlated in others. Which correlation holds is going to depend on the circumstances, that is, how old the person is. And now the next question is, how can we get from these correlations to causal relations? When two features are correlated, positively or negatively, then there are four possible causal relations between them. First, A might cause B. Sometimes when A and B are correlated, that means that A is causing some kind of change in B. Second possibility is that B causes A, because the correlation is symmetrical. If A is correlated with B, B is correlated with A. And then we don't know whether A causes B or B causes A. But those are two different possibilities, and we'll have to see how to distinguish them in a minute. But the third possibility is that some third thing, C, causes both A and B. If C causes B and C also causes A, then A and B are going to be correlated. Because whenever C is there, you get both of them, and when C is not there, unless something else causes them, then they're not going to be there. So A and B will be correlated simply because a third thing, C, is causing them both. And the fourth possibility is that the correlation is purely accidental. A and B just happen to change together. Okay? So here are some examples. First of all, let's do an example of A causing B. Okay? The speed of driving is positively correlated with automobile accidents and deaths from automobile accidents, because when you're going very quickly in your car and have an accident, you're more likely to die. Okay, which causes which? It's the speed that causes the accidents and the deaths. The death didn't cause you to drive faster before you died. That seems pretty clear. Okay? Now what about the second possibility? B causes A. Well, it's just the reverse. You can use the same examples. You can say automobile accidents and deaths are correlated with fast driving, with speed. And in that case, it's not that the thing we mentioned first causes the thing we mentioned second. It's the other way around. Because as we said before, it's the speed that causes the automobile accidents and the deaths, not the deaths and the accidents that cause the speed. Okay? What about the third possibility? That some third thing causes them both. Well, here's an example. Having yellowed teeth is correlated with having lung cancer. Well, why is that? Because there's some third thing that causes people's teeth to become yellow and also causes lung cancer, namely smoking. So people who smoke tend to have yellower teeth, and they also tend to have more lung cancer. So those are correlated because smoking causes both of them. Okay? Another example. In young children, shoe size is correlated with the quality of handwriting. As people's shoes get bigger, their handwriting gets better. Now, why is that? It's because they're maturing. And as their bodies mature, their feet get bigger, and also their handwriting gets better. So now we have an example of each of the first three types of cases that we talked about. What about the fourth? Correlation is accidental. Well, here's an example. The height of my son and the height of the tree outside the window, well, they're correlated. The taller my son gets, the taller the tree gets. And the taller the tree gets, the taller my son gets. They're symmetrical. They're correlated together. But does that mean that something about the height of my son causes the height of the tree? No. Or vice versa? No. Well, you might say there's some third cause, namely maturation. But unlike the case of handwriting and size of feet, where it was the maturation of the same person, the same body, here, my son's body maturing and the tree's body maturing are just unrelated. You might say that time is the third cause that makes my son grow and also makes the tree grow. But notice that time is an abstract thing that's always there and always moves at the same rate. So it can't really cause my son to grow at this particular moment or the tree to grow at this particular moment. It's a background condition rather than a cause in and of itself. So now we've got four possibilities and we've got examples of each. The question that we have to face is, fine, all four are possible. How do you tell which of these possibilities is the one that applies in a particular case? That's going to be tricky. So the problem is, how can we tell which of the four possibilities applies in a particular case? And one simple rule is that when A causes B, A has to come before B. So if the first possibility is instantiated, then you have to have A coming before B. But if the second possibility is instantiated, then you have to have B coming before A. Now, in the last two, you can have them on any temporal relation you want. But if A comes before B, then you know that B doesn't cause A, and if B comes before A, then you know that A doesn't cause B. So, for example, exercise is correlated with weight loss. Could it be that the weight loss causes the exercise? Well, it's possible, I suppose, but if the exercise occurs before the weight loss, then we know that it's the exercise that causes the weight loss because the exercise occurs before the weight loss occurs. And we can use that temporal relation to decide what causes what, at least in some cases, because sometimes when you're dealing with a constant factor like CO2 variations or pollution variations over a long period of time, and if pollution causes acid rain, you don't know exactly which part of the pollution is causing which part of the acid rain, and the parts are occurring over a long period of time. So you can't tell which comes first. But at least in cases where you can, like the exercise and the weight loss, then you can say which causes which. Now, when they're not in temporal order like that, you have to use a different method. The second method of determining what causes what is manipulation. This method is used in a lot of scientific experiments where they manipulate one factor to see whether that factor causes something else. When you do those types of experiments, you have to make a lot of assumptions or test a lot of background conditions to make sure that there's no independent factor that's causing the effect. But in the right circumstances, it can work. If you want more detail about which circumstances need to be met, then there are books by Woodward and by Pearl that spell this out in great detail. But here, we're not going to go into any great detail. We're just going to give you the basic idea. And the basic idea is that you manipulate A and then look to see whether B changes according to the change in A. And you manipulate B and look to see whether A changes in accordance with the change in B. And that's going to help you determine what causes what. Because if when you manipulate A, B changes, then that's an indication that A causes B. Because if B caused A, then manipulating A wouldn't have an effect on B. Think about it this way. You put the wood into the engine of a steam train, and the wood affects the motion of the train because it affects the way the engine works. And then the train produces steam. But the steam doesn't cause the train to move, it's caused by the train. So if you manipulate the steam, like with wind blowing the steam around, that's not going to change the train. So, similarly, if you change A and B changes, but you change B and A doesn't change, then that's a pretty good indication that A causes B. And that's going to rule out the second one, right? That can't be true if A causes B. The third one, that says that C causes them both, so it's going to rule that out. And the fourth one, it's not just an accidental correlation if A causes B. So if you do that manipulation, you can find out that it really is the first case that holds, at least if all the other conditions are met. Now, you can also do it the other way around. If you manipulate B and A changes, but you manipulate A and B doesn't change, then you know that B causes A. But you also know that A does not cause B, because if it did, then when you manipulated A, B would change. And you know that it's not just some third cause, and you know that it's not just accidental. So now you've isolated the second condition as the one that holds if when you manipulate B, A changes, but when you manipulate A, B doesn't change. Again, this only holds when certain circumstances are in place. And I'm not going to go into detail and spell out what those are, but this is the basic idea behind a lot of experiments in science. Here's an example. Long time ago, they discovered that smoking correlated with lung cancer. And that led a lot of people to say that smoking causes lung cancer. But just imagine that you're a manufacturer of cigarettes. What are you going to do? Well, they were pretty inventive. They said, it's not the smoking that causes the lung cancer. It's the lung cancer that causes the smoking. Because when people have certain types of incipient lung cancer, that is lung cancer that's about to develop into full-blown lung cancer, it makes them want to smoke. It creates a discomfort in their lungs that's relieved by the smoking. And that explains why people who smoke more have more lung cancer. So we think that A causes B, the smoking causes the lung cancer. They're claiming that B causes A, the lung cancer causes the smoking. How do you tell? Well, you can't look at the temporal relation because the smoking is going on at the same time when the lung cancer is developing. So you got to do a manipulation. You set it up in a lab. You take a bunch of animals, in this case it was monkeys, who don't have lung cancer. You check them first, and then you force them to smoke. You put a cigarette in their mouth so that when they're breathing, they're smoking. And sure enough, they developed a lot of lung cancer. No surprise there. Poor animals. And that showed that it was lung cancer that was caused by smoking instead of causing smoking. Why? Because we didn't manipulate the lung cancer. It didn't affect the smoking, but we manipulated the smoking, and that affected the lung cancer, and that shows that it was the smoking that caused the lung cancer. Here's another example, which was kind of a mystery for a while. An economist friend of mine told me about this. Turns out that back in the 1960s, there was a positive correlation between having a television in the home and performance in school. Students were more successful in school if they had a television in their house. Some people actually claim that television was making them better students. But in the 90s, it was the other way around. In the 90s, kids who had televisions in their home did not do as well on average as kids who had no televisions in their home. So there was a negative correlation. So how could there be a positive correlation between television and school success in the 1960s, but a negative correlation between television and school success in the 1990s? In order to decide between those hypotheses, you can't manipulate it. You can't go back and change the rate at which they're watching television and change their school performance and so on. You need to have some background information about the societies of the time and the kind of people who had televisions. Well, back in the 1960s, it was largely the more affluent, higher socioeconomic status people who had televisions because they were quite expensive and not that common. And those people typically are correlated with high school success anyway. High socioeconomic status and high school success have been correlated. And so it's that correlation that's explaining why in the 1960s, the students who had televisions in their homes did better in school. But in the 1990s, things had turned around. Parents were worried about their children watching too much television. And some parents actually kept televisions out of the home so that their kids would read more. They had more books and less television. And those kids were doing better in school. No surprise there. So in the 1990s, there were a lot of people who kept the televisions out. That produced greater school performance. And so you got different correlations in different times. And the only way to tell what was causing what was by looking at the background circumstances and knowing something about the societies in which these effects are occurring. There's a lot more to say about causation, and we can't say it all here. You really ought to take a whole course about causation in its many different forms. But we can help you avoid some of the most common fallacies. Here we'll look at two common fallacies. The first one is simply confusing an accidental correlation with a causal relation. Sometimes this is called post hoc ergo propter hoc, or some people pronounce it post hoc ergo propter hoc. And what it means in Latin is after this, therefore, because of this. And the idea is that they're correlated, one occurs after the other, and you conclude the second one must occur because of the first one. It's really just an accidental correlation, and it's a fallacy to conclude that it's a causal relation. And of course, the classic example occurred one time in a hotel with my son. We got onto the elevator, and I reached for the button. I wanted to push the button for the floor that we wanted to go to. But my son said, "No, Daddy, no, don't do it." I said, "Okay." And then he reached up and pushed the button. And just as he pushed the button, the fire alarm went off. And he started crying because he had made the fire alarm go off. But of course, he was just committing the fallacy of post hoc ergo propter hoc. The fire alarm didn't go off because he pushed the elevator button. It just happened to go off after he pushed the elevator button. Now that might seem like a silly mistake that only a child would make, but you'll be surprised how many times you can find this mistake being made in serious discussions in newspapers. Just take a look for yourself. Now the second common fallacy that I want to describe is confusing a cause with an effect. Here are some examples. I'm a golfer, and sometimes I go out and play golf and my back is just killing me. And I'm thinking, it must be why I'm playing so bad. I can't hit the ball. I keep knocking it off to the side. And I blame it on my back. So I think it's the pain in my back that's causing my bad swing. When actually, it's my bad swing that's causing the pain in my back. I'm like twisting around the wrong way, and that's causing a backache. So I think that it's the pain in my back that's making me swing badly. It's actually the bad swing that's causing the pain in the back. So that's just an everyday example. Here's an example in football, American football we're talking about here. It was noticed that there was a correlation between the number of forward passes and how often the team was losing. Teams that had a lot of forward passes were losing more often. So some coaches concluded, well, we ought not to pass the ball so much because passing the ball causes you to lose. That's not what was going on. What was going on is that in the last quarter of the game, the team that was behind would get desperate. They needed to score a lot of points quickly, and running the ball wasn't going to do that. So they tried passing the ball, and they would pass more and more and more in order to catch up. And that meant it was the fact they were losing the game that caused them to pass the ball so often. It wasn't passing the ball often that was causing them to lose the game. So again, they were confusing cause with effect. Here's a third example. It turns out that many schizophrenics smoke and take drugs and alcohol. And so there's a correlation between schizophrenia and drug and alcohol use, including nicotine from smoking. Some people concluded it must be that drugs and nicotine cause schizophrenia. No, that's not what's going on. That's the fallacy of confusing cause and effect. What's really going on is that their schizophrenia is causing them to smoke and drink more and to take drugs. So again, what people get confused about is they think that one thing causes another when it's really the other thing that causes the first thing. They're getting the relation backwards and confused. And that's something that you need to really be on the lookout for as you try to figure out what causes what in your everyday life. Because if you make that mistake, you're going to get confused. You're not going to know what manipulations will change what features in your life. And that's why causal relations are important, to figure out how to get around in the world and bring about the changes that you want. So watch out for these fallacies and do the best you can to figure out how the world works. But after seeing how hard it is to establish causal relations, you might be wondering whether this lecture has really caused you to learn anything at all. So, I leave you with this cartoon. Hi. So far in this course, we've discussed a wide variety of inductive arguments. First of all, we looked at statistical generalization from a sample. Then we looked at application of a generalization down to a particular case. Then we looked at inference to the best explanation, an argument from analogy. Then last week, we turned to causal reasoning, which involved the positive, necessary, and sufficient condition tests. And in addition, at the very end, we looked at concomitant or concomitant variation, which involved a kind of manipulation in drawing conclusions about what causes what. So we've seen a lot of kinds of induction. And that's got to raise the question, what's in common to all the different types of induction that makes them induction? Well, we saw that inductive arguments, unlike deductive arguments, are defeasible, and they don't even aim at being valid. Instead, they just try to be strong. But strength comes in different degrees, and we haven't really learned anything yet about what exactly strength is. Well, it turns out that one way of understanding inductive strength is that an argument is strong in proportion to the probability that its conclusion is true given its premises. So inductive strength can be understood in terms of probability. And so for this week, we're going to turn to the notion of probability, which will help us understand inductive arguments. But probability is important in a lot of other ways too. I mean, just think about going on a picnic tomorrow. You want to know what the probability of it raining is, because if the probability of rain is very high, you might not want to go on your picnic. Instead, stay inside. Okay, so probability affects our beliefs and it affects our decisions. And that makes it important to understand probability and try to figure it out. But that's a problem, because if you just rest on your intuitions about probability, you're going to get messed up. You're going to make mistakes. Almost everybody messes up probability until they start thinking about it a little bit more seriously. Let me give you a few examples where people get confused about probability. 7, all right. Whatever it is. 7, all right. Another 7, unbelievable. Cool. 3 7s in a row. And 7's a winning number, so that's great, but you know, the odds of getting 4 7s in a row are really slim, so I bet the next one's not going to be a 7, right? No. Just because the first 3 were a 7 doesn't tell you the next one's not going to be. Sure, it's unlikely to get 4 in a row, but once you got the first 3, then the likelihood of getting the 4th 7 is just the same as the likelihood of getting a 7 on any roll whatsoever. Some people make that mistake. They think that just because they got 3 in a row, it's not going to come up that way again the 4th time. And other people make the opposite mistake. They say, hey, the dice are hot tonight. I got 3 7s in a row. Next one I'm going to get a 7 too. I'm going to put all my money on 7. Don't do it. You'll lose your money. Because even if the first 3 are 7s, dice don't get hot. The odds of getting a 7 on the 4th one are exactly the same after you've gotten 3 7s as if you didn't get 3 7s. And both of these mistakes, 3 7s so the next one's not going to be 7, 3 7s so the next one's going to be 7, they're both mistakes because the odds on the 4th roll are not affected by the odds on the first 3 rolls. And people who think otherwise, they're just going to get fooled by gamblers. It's not just in gambling too, it's also in basketball. People think, oh, he's hot. He's made a lot of shots in a row. He's hot. He's going to make the next one. And then they'll tell that player, you take the shot because you're hot tonight. Well, that's a little more controversial in basketball. But some statistics suggest that people don't really have hot hands in basketball. They just make the percentage that they make. And you're going to get strings, but that doesn't mean you're hot in any way. Like I said, that's controversial. But with dice, at least, we know the dice do not get hot. And so don't waste your money making that mistake. That's called the gambler's fallacy. And don't do it. Okay, deck of cards. And here I am. I'm going to shuffle the cards. Okay, there we go. There we go. I'm going to shuffle the cards again. We got these cards all shuffled, and now I'm going to deal out 2 hands. Okay, 9, a queen, an 8, a queen, a 5, a queen, a jack, a queen, a 4, an ace. Whoa, look at those hands. That's amazing. You think they're about equally probable? What's the likelihood of that hand coming up? Most people would say, that's pretty slim. It's unlikely that you're going to get a hand with 4 queens and an ace. What about this hand? That's the kind of hand I get all the time when I play poker. So most people are going to think that kind of hand is a lot more likely. But actually, they're equally probable. Getting exactly this hand and exactly that hand have the same probability. The reason people think this one is less likely than this one is that you get that kind of hand a lot in poker, namely a hand that's junk, that's useless. You get a winning hand like this not very often in poker. And so people think that this one is less likely than this one because this hand is more representative of the type of hand that I get when I'm playing and that most people get when they're playing. But that's what's called the representativeness heuristic. You think it's more probable because it's more representative of the kind of thing that you encounter in experience. Another famous example of the representativeness heuristic comes from Kahneman and Tversky. It's about Linda the bank teller. They tested a large number of subjects. What they did is simply describe Linda. Linda is 31 years old, single, outspoken, and very bright. As a student, she majored in philosophy. She was deeply concerned with issues of discrimination and social justice, and she also participated in anti-nuclear demonstrations. They asked their subjects to rank the following statements with respect to probability. Which one is more probable than which of the others? Linda is a teacher in an elementary school. Linda works in a bookstore and takes yoga classes. Linda is active in the feminist movement. Linda is a psychiatric social worker. Linda is a bank teller. Linda is an insurance salesperson. And Linda is a bank teller and is active in the feminist movement. And when people ranked all of these, they tended to put Linda is a bank teller and is active in the feminist movement as more likely than Linda is a bank teller. But that can't be. Just think about it. It's got to be less likely that she's a bank teller and active in the feminist movement than simply that she's a bank teller. Because in every possible state of affairs where she's a bank teller and active in the feminist movement, she's also a bank teller. So there have to be some possibilities where she's a bank teller but not active in the feminist movement. So it has to be more likely that she's a bank teller than that she's both a bank teller and also active in the feminist movement. And why do people make this mistake so often? It's largely because when they trust their intuitions about probability, those intuitions are based on what they take to be representative. Someone with a background like Linda, who is deeply concerned with issues of discrimination and social justice, are likely to be active in the feminist movement, whereas bank tellers are not typically known for being active in the feminist movement. So it would be more typical for her to be both than for her to just be a bank teller. And so they base their probability judgment on the representativeness heuristic, and that's what leads to the common mistake. One final common mistake about probability is illustrated by what has come to be known as the Monty Hall problem, or sometimes the 3-door problem. Here's the setup, which comes from an old TV show called Let's Make a Deal. There are 3 doors on the stage. Let's call them door A, door B, and door C. And behind one of the doors is a car. And if you get the right door, you get to keep the car. But behind the other 2 doors is a goat. And if you get those doors, you go home with a goat. Now, we're assuming that you'd rather have a car than a goat. You might be one of those weird people, but let's assume you want a car and not a goat. Imagine that you pick door A, and then the host, Monty Hall, opens door C and reveals behind door C a goat. Now you know that there's door A and door B left. One of them has a car, one of them has a goat. And Monty Hall turns to you and he offers you the chance to switch from door A, the one you picked, to door B. And the question is, should you switch? And this has actually caused a lot of controversy. Some people think you should switch, some people think you shouldn't switch. I'm not going to tell you because that's going to be one of our exercises. And the point of this lecture is just to show you that you can't trust your intuitions because so many people will get it wrong in the Monty Hall case, in the representativeness heuristic, and so many people commit the gambler's fallacy that you need to take probability seriously. And in the next lecture, we'll start looking at some definitions of what it is, and the lectures after that will look at rules for probability because you need that kind of thing if you can't trust your intuitions. We need to start our study of probability with a little terminology. How do we talk about probability? We learned early in the course in the second week about guarding terms, where people say things like, well, it might be the case that a meteor is going to hit your house, so you need meteor insurance. But might's just possibility, and that's different from probability. If you ask, how probable is it that a meteor is going to hit your house, the answer is going to be pretty low. But how do you say how low it is? One way to talk about probability is to say the number of times that it might happen out of the number of times that occur. So you might say 3 times out of 10. This horse will win the race 3 times out of 10. In 10 races, it'll win 3 times. You can also do that in terms of 3 in 10, or simply there's a 30% chance. 3 times out of 10, 30% chance, same thing. But the way we're going to put it for the rest of these lectures is to talk about a probability of 0.3. Probabilities range from 0 to 1. 1 means it's absolutely certain that it's true. If you say the probability is 1, that means it's gonna happen. 0 means there's no chance it's gonna happen. It's certain that it won't happen, that it's not true. So every probability has to be between that. Between it's absolutely certain that it won't happen, and it's absolutely certain that it will happen. When you're somewhere in the middle, you're between 0 and 1, you got different levels of probability. That's the way we talk about it. Now, probabilities come in many different kinds. The first kind of probability we're going to call a priori probability because you figure it out prior to experience, prior to any kind of experimentation. So take, for example, a coin. It's got tails, it's got heads, you flip it, and what do you get? Well, you can't see, but that time I actually got tails. What's the probability it'll come up tails? We tend to just assume that it's a fair coin, which means that the probability of coming up tails is equal to the probability of coming up heads. So if they're equal, when you add them together, you should get 1 because it's absolutely certain that you're going to get either heads or tails, one or the other. And that means that you assume the probability is 0.5. But all that's just assumption. You're just assuming that the outcomes are equally likely. Now let's turn from coins to dice. A little bit more complicated. 6 sides. You roll one of them, and if you get a 2, as I just did, then the odds of getting a 2 when there's 6 sides, if you assume they're all equally probable, is going to be 1 out of 6. What if you roll 2 of them, like we did when we were discussing the gambler's fallacy? Oh my gosh, I got 7 again. Pretty cool. And what's the likelihood of that? Well, how many ways are there to get 7 on a pair of dice? You can get 1 and 6, you can get 2 and 5, you can get 3 and 4, but you can also get 4 and 3, 5 and 2, 6 and 1. So there's 6 ways to get a 7 on 2 dice, and there are 36 possibilities, 6 times 6. So the probability of getting a 7 when you roll 2 die are 6 out of 36, or 1/6. But notice that we're just assuming that these dice are fair. It gets a little more complicated when you have to give up that assumption. So let's start with coins. No tricks up my sleeve. It's a normal coin. Heads, tails. What are the odds of getting heads? Well, two possibilities, heads or tails. If we assume they're equally probable, the odds of getting a heads are 1 and 2. We can figure out the probability just by assuming that heads and tails are equally likely, and that's a priori probability. But now, let's get violent. If you take the coin and you put it in your pliers like this, protect the desk, then you get your hammer and you start bending it. You bend the coin, okay? Good. See? Now it's bent. Okay, now let's check the probability again. Here's our bent coin. Now we flip it. What are the odds that it's going to come up heads? Heads. 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 Pretty good. Heads. Well, I can't get it to do it, but sometimes it'll come up tails, and we don't know how often. Looks like most of the time it comes up heads, but sometime it'll come up tails. How often? We don't know. The only way to figure that out is to flip it hundreds and hundreds of times and see what percentage come up. That's because once you bend the coin, it's not an a priori probability. You can't just assume that the coin has equal chances of landing heads or tails. You have to turn it into a statistical probability and look at the frequency of the actual flips for that particular bent coin. Here's one more example of the difference between a priori probability and statistical probability. One of my favorite games, Pass the Pigs. I highly recommend it. It's a really fun game. Now, what about this? You roll the pigs, and sometimes you get a snouter or a leaner or a jowler or a razorback or a trotter. They're different results. And, ooh, there we go, a double razorback. That's pretty good. And you roll them. Ooh, look at that, a leaning jowler. That's a lot of points there. And you have to roll them along a lot of different times in order to get the probabilities. And we actually did that. We did 1,817 rolls. We got one side up 1,174 times, trotter 150, razorback 441, snouter 39, leaning jowler 13. So what are the odds of getting a leaning jowler on one roll of a Pass the Pig? 13 out of 1,817. Now notice that you could never do that a priori, just by assuming probabilities. You have to do an actual experiment and look at the frequencies, because this probability is not an a priori probability, it's a statistical probability. And the nice thing about statistical probability is you can apply it to a lot of things besides coins and dice, right? What's the probability it's going to rain tomorrow? Well, how do they figure that out? They do a lot of observations of when it rains, under what kinds of circumstances, and they ascribe a probability on the basis of how many times it's rained in similar circumstances in the past. And what's the probability this batter is going to get a hit in baseball? Well, they look at his batting average over the previous part of the season, especially under certain circumstances versus right-handers pitchers versus left-handed pitchers, and you get a probability that he's going to get a hit this time. The same for cricket. If you've got a bowler, it's a spin bowler or a speed bowler, well, this batter might be better against one than the other, and you can figure the probability against the different types of bowlers. So in sports, you use statistical probabilities a lot. And in life, you use statistical probabilities a lot. When you try to decide what kind of car to buy, and you want to know what's the likelihood that this particular car will break down in the first year, you go to Consumer Reports and you see how many cars of this sort break down in the first year. So we use statistical probabilities for a lot of different areas. Really, a priori probabilities are only applicable when you can assume that the outcomes are equally likely. And that's the real difference between a priori probability and statistical or empirical probability. One of them is just based on assumptions that the outcomes are equally likely. That's a priori probability. The other is based on empirical evidence about how often things happen, the frequency of events in the world. That's statistical or empirical probability. But no matter which kind of probability you're talking about, a priori or empirical, they still have to follow the same general rules. And it's those rules that we're going to study for the next few lectures. All the different kinds of probability are governed by the same basic rules. But what are these basic rules? We're going to look at 4 basic rules. The first one governs simply negation. So you toss a coin and you get tails. What's the probability that you get tails? We said 1 in 2, or 0.5. Now, what's the probability that you do not get tails? Well, that means that's the probability that you get heads, so it's also 0.5. It's 1 minus the 0.5 probability of tails gives you the 0.5 probability of not getting tails, that is, of getting heads. Well, that's really simple because there are only 2 possibilities. What about a die? You roll a die and you get a 2. What's the probability that you'd get a 2? Well, it's 1 in 6. What's the probability that you would not get a 2? Well, not getting a 2 is getting either 1 or 3 or 4 or 5 or 6. So there are 5 possibilities of not getting a 2, and that means that that's 5 times out of 6 you do not get a 2. So the probability of not getting a 2 is 1 minus the probability of getting a 2. The probability of getting a 2 is 1 in 6. So the probability of not getting a 2 is 5 in 6. So our rule is basically that the probability that an event will not occur is 1 minus the probability that the event will occur. And we can put that in symbols like this. You put PR for probability, and then in parentheses you put what it's a probability of. We're going to use H for hypothesis, or the event that we're testing the probability for. And the little squiggle or tilde means not, just like it did when we were talking about propositional calculus a few weeks ago. So the probability of not the hypothesis is equal to 1 minus the probability of the hypothesis. That's basically the rule for probabilities of negations. And we explained why it holds. Because certainty is 1, the thing happening and the thing not happening have to add up to 1 because it's got to either happen or not happen. So 1 minus the probability that it happens has got to be the probability that it does not happen. So I hope now the rule makes sense and that you can apply it in a couple of exercises. The rule for the probability of conjunctions is a little more complicated. One reason is that there are really 2 cases we have to keep separate. We're going to look first at the case of independent events, and we have to begin by saying what it means to call them independent. To call them independent is simply to say that the probability of one does not affect the probability of the other. So if you flip a coin or roll a die and get a certain number, and then you pick up the coin or the die and you flip it or roll it again, then the second result is not affected by the first result. So those are independent events. And with cards, if you take a deck of cards and you pick out a card, 2 of spades, then you take that 2 of spades and you put it back in the deck, you shuffle, it's going to be independent whether you get it again, because what you picked out the first time doesn't affect what you pick out the second time. But if you take a deck of cards and you pull out the king of spades and you take that card and you throw it away and don't put it back in the deck, then it affects all the probabilities of the remaining cards, because now you have fewer cards than you had before. So that's the difference between independent events and dependent events. So we're going to look at independent events first and look at the rule for the conjunction of independent events. And the rule for this case is pretty simple. If two events are independent, then the probability that both events will occur in that order, because we're talking about this one and then that one. We'll talk a little bit more about that later, but we're assuming that. The product that they both will occur is the product of the probability of the first event times the probability of the second event. And notice that the both occur is tied to the product, or multiplying the two probabilities together. And the reason for that is that it's less likely that they will both occur than that one of them will occur separately. And when you multiply the two probabilities between 0 and 1, you're going to get a lower probability that they both occur than for either one of them occurring, all by itself. We can restate this rule symbolically using the symbols that we used before for the probability of negation. Namely, the probability of hypothesis 1 and hypothesis 2 both being true is the probability of hypothesis 1 times the probability of hypothesis 2. Now let's apply it to some cases. Suppose you flip a coin and you get heads. You flip another coin and you get heads again. What's the probability of getting heads twice on two flips of the coin? Well, the probability is 0.5 for the first flip of getting heads. It's 0.5 for the second flip of getting heads. And then the probability of getting both is going to be 0.5 times 0.5, or 0.25. So the probability of getting two heads in a row is 0.25 on two flips of a fair coin. A little more complicated example uses cards. Here we have a standard deck of cards. Ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, Jack, Queen, King. So there are 13 different types of cards, and there are 4 different suits: spades, hearts, diamonds, and clubs. So we can remember that the probability of having one of these types of cards chosen, assuming that they're shuffled properly, is 1 out of 13, and the probability of getting a particular suit, say a club, is 1 out of 4, because there are 13 clubs out of 52 cards. Clubs are one suit out of 4, so the probability of picking a club is 1 in 4, and the probability of picking a particular card, say a 3, is 1 in 13. Again, a deck of cards. Suppose I pull out a 4, and then I pull out a club. Now, in a standard deck of cards, there are 13 cards. We're assuming no jokers. So the odds of getting a 4 are 1 in 13. There are 4 suits: spades, hearts, diamonds, and clubs. So the odds of picking a card that's a club is 1 in 4. What's the probability of picking a 4 and then picking a club? Well, it's going to be 1 in 13 times 1 in 4. And that means it's going to be 1 in 52. So the odds of that combination occurring, right, in that order is going to be 1 over 13 times 1 over 4 equals 1 in 52. That example shows you how to calculate the probability of a conjunction with independent events. But what if the events are not independent? That is, what if the probability of one affects the probability of the other? Here's a question. Joe can run a mile in less than 5 minutes about half the time. When he runs in each time, half the time he's under 5 minutes, half the time he's over 5 minutes. So what's the probability he can run a mile in less than 5 minutes on a given occasion? 0.5. But what's the probability he can run 1 mile in under 5 minutes and then run another mile in under 5 minutes right after that? Well, if you did this calculation, you would have 0.5 times 0.5, and that means 0.25. But you know that's not right, because he's going to be dead tired after the first mile. There's no way that the probability of running the second mile in under 5 minutes is just as high, whether or not he would just finish running a mile. So those events are not independent, and that example shows you why you need a new formula to calculate the probability of a conjunction when events are not independent, but instead their probabilities depend on each other. The same distinction between independence and dependence applies to our old friend cards. So just to simplify matters, let's start with a very limited deck. It's just got 4 aces. It's got the ace of spades, the ace of hearts, the ace of diamonds, and the ace of clubs. And notice that the ace of hearts and the ace of diamonds are red, and the ace of spades and the ace of clubs are black. So, knowing that, out of these cards, if we shuffle them and don't look at them, what's the probability of picking a red ace? Well, 1 in 2, right? Because 2 of them are red out of the 4. Now, sorry. Oh, a red one. I picked a red one. Now, let's put it back in the deck and shuffle them together. Okay? What's the probability now of picking another red ace? Again, 1 in 2. So if you look at the possibilities all laid out, the first pick is in the columns, right? So the leftmost column is if you pick an ace of spades on your first pick. Second column is ace of hearts on your first pick. Third column is ace of diamonds on your first pick. Fourth column is ace of clubs on your first pick. And then your second pick is the rows. And again, it's either spades, hearts, diamonds, or clubs. So there's 16 possible combinations of picks here in order. And how many of them are picks where you have 2 red aces? Well, this is one, this is one, this is one, and this is one. So the 4 possibilities in the middle are the possibilities where you've picked an ace that's red, both on your first pick and also on your second pick. So the odds of doing that are 4 out of 16, or 1 out of 4, or 0.25, just like we calculated using the formula. But what if there's no independence? Let's start with the same 4 aces. Okay? And what's the probability of picking a red ace? Still 1 in 2. So let's suppose I pick the ace of hearts, throw it away, do not put it back in the deck, and now I've only got 3 aces left. What's the probability of picking a second red ace without looking? Well, it's going to be 1 in 3, because one of them is red and the other 2 are not. There are 3 cards left. One of them is a red ace. The probability is 1 out of 2 times 1 out of 3 equals 1 out of 6, instead of the 1 out of 4 that we had when they were independent and you put the card back. So we need a different formula to generalize for this case where there's dependence. Okay? And this formula is going to use the conditional probability, which is just a fancy way of saying what I just mentioned to you, right? The conditional probability of picking a red ace on the second pick, given that I picked a red ace on the first pick and threw it away, is 1 in 3. Is how many times does X occur picking a red ace on the second pick out of the cases where I picked a red ace on the first pick and threw it away? And that's going to be your 1 in 3. So that's the conditional probability. And now the formula. The probability of both of 2 events occurring is the product of the probability of the first event occurring times the conditional probability of the second event occurring, given that the first event occurred. That's where you use the conditional probability. Now notice when the events are independent, that conditional probability of the second event occurring, given that the first event occurred, is just going to be the same as the probability of the second event occurring. because the first event doesn't affect the second event. So that first formula for independence is just an instance of this formula where the conditional probability of the second given the first is identical with the probability of the second. So that's why it's a generalized formula. It actually includes the first formula. But when they're independent, it's just simpler to think of the first formula alone. We can also symbolize this rule. We can say that the probability of hypothesis 1 and hypothesis 2 is equal to the probability of hypothesis 1 times the probability of hypothesis 2 given hypothesis 1. And that straight up and down line in this formula is what indicates conditional probability. This little formula here means the probability of hypothesis 2 given hypothesis 1. So you can use this rule to calculate the probability of any old conjunction, whether they're independent or not. But when they are independent, you might want to use that simpler rule, which was the first version of the probability of conjunction. Our next rule for probability concerns the probabilities of disjunctions, that is, the probability that either one thing or another will happen. And as with the case of the probability of conjunctions, we have two cases. We need a different rule when these two events are mutually exclusive than when they're not mutually exclusive. We're going to look first at cases that are mutually exclusive. And what that means is simply that they cannot occur together. The probability of them both occurring is 0. It can't happen. Now, the formula for that simpler case says that if two events are mutually exclusive, then the probability of either one event or the other event occurring is simply the sum of the probability of the first event occurring and the probability of the second event occurring. And we can symbolize it using the same symbols we've used before as the probability of hypothesis 1 or hypothesis 2 is equal to the probability of hypothesis 1 plus the probability of hypothesis 2. Simple enough. Let's look at an example. What's the probability that I will pick either an ace of diamonds or an ace of hearts out of this deck? Well, the probability I'll pick an ace of diamonds is 1 in 4. The probability that I'll pick an ace of hearts is 1 in 4. So the probability that I'll pick either one or the other is 1 in 4 plus 1 in 4, which is 2 in 4, which is 0.5. 2 times out of 4, 0.5. So this formula makes perfect sense when it's exclusive, when you cannot pick both an ace of diamonds and an ace of hearts on a single pick. Here's another example. It's a special case. We've been talking so far about permutations, which are ordered sets. So the two events in a conjunction would be flipping heads first and then tails second. We can also look at combinations where order doesn't matter. Flipping one heads and one tails out of two flips, but it doesn't matter what the order is. Then we have heads and tails in two flips, which means either a heads and then a tails, or a tails and then a heads. So we've got a disjunction. And we can figure out the probability of this combination, which is unordered, by looking at the disjunction of those two possibilities. Here's a chart showing the possibilities. If you take heads on flip 1, you're in the left-hand column. Tails on flip 1, you're in the right-hand column. Heads on flip 2, you're on the top row. Tails on flip 2, you're on the bottom row. Which of these, for the two flips, includes a heads and a tails where the order doesn't matter? And the answer is the upper right has tails on flip 1 and heads on flip 2, and the lower left has tails on flip 2 and heads on flip 1. So it's those two possibilities, this one and this one, out of the four that include the combination, one heads and one tails in any old order. And the disjunction is calculated by saying, what's the probability of this 0.25, 1 in 4, and the probability of this 0.25, 1 in 4, and you add them together, because the probability of doing either one or the other is going to be the sum, just like the formula says. Next, we have to look at the general formula that applies whether or not the two events are mutually exclusive. And that's pretty simple. We're going to call it 3G for the generalized version of Rule 3. And what it says is that the probability of either one event occurring or the other event occurring is the sum of the probability of the first event occurring plus the probability of the second event occurring minus the probability that they both occur. Or, in symbols, the probability of H1 or H2 is equal to the probability of H1 plus the probability of H2 minus the probability of the conjunction of H1 and H2. So we're going to have to use that previous rule for conjunction to figure out what gets subtracted. But the more basic question is, why are we subtracting in the first place? And you can think about that in this example. What's the probability of getting heads on either the first flip or the second flip in two flips of a fair coin? Well, one way to figure this out might be to say, well, what's the probability of getting it on the first flip? Well, that's 0.5. What's the probability of getting it on the second flip? Well, that's 0.5. So let's add them together. And the probability of getting it on either the first flip or the second flip is 0.5 plus 0.5 equals 1. So it's absolutely certain that we're going to get a heads on either the first flip or the second flip of two flips of a fair coin. But you know that's not right, because sometimes you get two tails in a row. So that can't be the right way to calculate the probability. That's why you need to subtract the conjunction, because otherwise you're going to get the wrong answer. The right way then is 0.5 heads on the first flip, 0.5 heads on the second flip, minus the probability of both. But the question is, why do you have to subtract? And this little chart should show you why you have to subtract. Because the probability of getting heads on the first flip is the left-hand column. That's the upper one. You get heads on the first flip. The lower one, you get heads on the first flip. The probability of getting heads on the second flip is given by the top row. The first one, you get heads on the second flip. The second one, you get heads on the second flip. So if you want to add them together, you're adding together this one, and you're adding it to this one. That gives you 0.5 of getting heads on the first flip. Then you add it to the probability of this one plus this one, and that gives you 0.5 of getting heads on the second flip. But then if you add them together to get the probability of getting heads on either the first flip or the second flip, you've double counted the one in the upper left in red. You counted it in the probability of the first flip and also in the probability of the second flip. And you don't want to double count it, because then you'll get the wrong answer. So I hope this chart illustrates why, in order to generalize the formula for disjunction, we need to subtract the probability that both of the events will occur. Here's another example. Out of a standard deck of cards, what's the probability of picking either a 6 or a club? Well, we know that there are 4 sixes and 13 different types of cards, so the probability of picking a 6 is 1 in 13. What's the probability of picking a club? Well, there are 13 clubs and 4 suits, so the probability of picking a club is 1 in 4. And if we add those probabilities together, we'll get 4 plus 13 makes 17 out of 52 cards, but that's not right because you just double counted the 6 of clubs. You counted it as a club and you also counted it as a 6. So in order to get the probability of picking either a 6 or a club, you need to add the probability of getting a 6, 1 in 13, to the probability of getting a club, 1 in 4, and subtract the probability of them both happening, namely getting a 6 of clubs, 1 in 52, because otherwise you'll be double counting that 6 of clubs. So now I hope you understand the rationale behind this generalized version of the rule for probabilities of disjunctions, and I hope you'll be able to do a few exercises using that rule. The 3 rules that we've studied are going to be enough to calculate the probabilities for any combination of propositions in propositional logic, because we've covered negation and then conjunction and then disjunction. And if you use them in various combinations, you can cover all of propositional logic. But it's still useful to look at one particular case, namely the probability of something happening in a series. Let's look at a simple example involving a very short series, only 2 events, and contraception. Assume that you want to prevent contraception and that you use 2 different methods. What's the probability of conception being prevented by using 2 methods at once? And let's assume that the probability is 0.9 of the first method working alone, and the probability is 0.9 of the second method working alone. How do you calculate the probability of preventing conception when you use both methods? Well, one move might be to say, let's add them together. 0.9 plus 0.9 is 1.8. So maybe the probability of preventing conception using them both is 1.8. No way, of course not. The maximum probability is 1. Probabilities vary between 0 and 1. So 1.8 probability just doesn't make any sense. That can't be right. Another possibility is to say we're going to multiply them. The probability of preventing conception by using both methods is 0.9 times 0.9, which is 0.81. That can't be right either. Why not? Because that would mean that there's less chance of preventing conception by using both methods, namely 0.81, than there was using one of the methods alone, 0.9. If you use both methods, the probability of preventing conception ought to go up. So how do we calculate the probability of one of these contraceptive methods working and preventing conception when we use them both? The right way to do this is to first of all look at the probability of one of these methods failing. So instead of looking at the probability of it working being 0.9, we say the probability of it not working is 1 minus 0.9 or 0.1. Now, what's the probability that they both fail? Well, the probability that they both fail is then going to be 0.1 times 0.1, which is 0.01. And now we can say, what's the probability of them not both failing? That's going to be 1 minus 0.01 or 0.99. So that's how we calculate the probability of preventing conception when you use both methods. Let's state this method in a formal rule. The probability that an event will occur at least once in a series of independent trials is 1 minus the probability that it will not occur in that series. Notice that we're assuming that the trials are independent. This rule is only going to work when the trials are independent. And what you do is you take the probability that it will not occur and subtract it from 1. And that gives you the probability that the event will occur at least once in the series. Or symbolically, it's 1 minus the probability of not h raised to the n, the number of trials. Because to get the probability that it will not occur in any of those trials, you have to raise it to the power of the number of trials. So in our case, it was 0.1 times 0.1 equals 0.01. But if you use 3 methods, it would be 0.1 times 0.1 times 0.1. That means 0.1 raised to the third power. Or if you use 4 methods, it'll be 0.1 times 0.1 times 0.1 times 0.1, 0.1 raised to the fourth power. So you can see how you can generalize from our simple case of 2 contraceptive methods to use this formula to determine the probability of an event occurring in a series of independent trials. So one more quick example. What's the probability of getting heads on a coin at least once if you flip it 5 times? There's 1, 2. That didn't flip. I'm going to do that again. There we go. 3, 4, 5. Now, I didn't show you whether it got heads or tails. What's the probability that one of those was a heads? Well, what's the probability for each flip that it was not a heads? 0.5. There are 5 flips. Raise it to the 5th power. 0.5 times 0.5 times 0.5 times 0.5 times 0.5. You can figure that out on a calculator. I'm not even going to try to do it in my head right now. And then you subtract that from 1, and it gives you the probability that you get at least 1 heads in 5 independent flips. And notice what it does is if it's 6 flips, it's going to be even more likely. And 7, it's going to be more likely because you're going to be raising 0.5 to the 6th power or the 7th power in order to apply the rule. So that's just another example of how you take this rule regarding series and calculate the probability of the event occurring at least once in a series of independent trials. Coins and dice provide a nice, simple model of how to calculate probabilities, but everyday life is a lot more complicated, and it's not taken up with gambling. At least, I hope your life is not taken up with gambling. So in order to make probabilities more applicable to everyday life, we need to look at slightly more complicated methods. Now, because these methods are more complicated, this lecture is going to be an honors lecture. It's optional. It will not be on the quiz, so don't get worried about that. But it is still useful, and it's fascinating, and it'll help you avoid some mistakes that a lot of people make and that create a lot of problems. So I hope you will stick with it and listen to this lecture, and there will be exercises to help you figure out whether you understand the material or not. But don't get too worried, because it's not going to be on the quiz. The real problem that we'll be facing in this lecture is the problem of tests. We use tests all the time. We use tests to figure out whether you have a certain medical condition. We use tests to predict the weather or to predict people's future behavior. We have certain indicators of how they're going to act, either commit a crime or not commit a crime, but also whether they're going to pass, do well in school, or fail. We always use these tests when we don't know for certain, but we want some kind of evidence or some kind of indicator. The problem is none of these tests are perfect. They always contain errors of various sorts. And what we're going to have to do is to see how to take those errors of different sorts and build them together into a method and then a formula for calculating how reliable the method is for detecting the thing that we want to detect. This problem is a lot like a problem we faced earlier when we were talking about applying generalizations to particular cases, because here we're going to be applying probabilities to particular cases. So it'll seem familiar to you in certain parts, but you'll see that this case is a little trickier. The best examples occur in medicine. So just imagine that you go to your doctor for a regular checkup. You don't have any special symptoms, but he decides to do a few screening tests. And unfortunately, and very worryingly, it turns out that you test positive on one test for a particular form of cancer, a certain kind of medical condition. Well, what that means is that you might have cancer. Might, great. You want to know whether you do have cancer. But of course, finding out for sure whether or not you have cancer is going to take further tests. And those tests might be expensive, they might be dangerous, they're going to be invasive in various ways. So you really want to know what's the probability, given that you tested positive on this one test, that you really have cancer. Now, clearly that probability is going to depend on a number of facts about this type of cancer, about the type of test, and so on. And I am not a doctor. I am not giving you medical advice. If you test positive on a test, go talk to your doctor. Don't trust me, because I'm just making up numbers here. But let's make up a few numbers and figure out what the likelihood is of having cancer given that you tested positive. So let's imagine that the base rate of this particular type of cancer in the population is 0.3%. That is 3 out of 1,000, or 0.003. And to say that's the base rate, or it's sometimes called the prevalence of the condition in the population, that's simply to say that out of 1,000 people chosen randomly in the population, you'd get about 3 that have this condition. It's just a percentage of the general population. So that's the condition. What about the test? Well, the first thing we want to know is the sensitivity of the test. The sensitivity of the test we're going to assume is 0.99. And what that means is that out of 100 people who have this condition, 99 of them will test positive. So this test is pretty good at figuring out from among the people who have the condition which ones do. 99 of those 100 people who have the condition will test positive. The other feature is specificity. And what that means is the percentage of the people who don't have the condition who will test negative. The point here is that you're not going to get a positive result for people who don't have the condition, right? Because you want it to be specific to this particular condition and not get a bunch of positives for people who have other types of conditions or no medical condition at all. So the specificity we're going to assume in this particular case we're talking about is also 99%. Now, what we want to know is the probability that you have the cancer, the condition, given that you tested positive on the test. But notice that the sensitivity tells you the probability that you will test positive given that you have the condition. We want to know the opposite of that, the probability that you have the condition given that you tested positive. And that's what we have to do a little calculation to figure out. But before we do that calculation, I want you to think about these figures that I've given you: the prevalence in the population, the sensitivity of the test, the specificity of the test, and just make a guess. Just start out by writing down on a piece of paper what you think the probability is that you would have the cancer given that you tested positive on the test. Take a minute and think about it and write it down. But we don't want to just guess about medical conditions, about probabilities that really matter as much as this one do. Instead, we want to calculate what the probability really is. So let's go through it carefully and show you how to use what I'll call the box method in order to calculate the real likelihood that you have the condition given that you got a positive test result. What we need to do is to divide the population into 4 different groups. The group that has the condition and tested positive, the group that has the condition and tested negative, the group that doesn't have the condition and tested positive, and the group that doesn't have the condition and tested negative. And this chart will show you a nice simple way of organizing all of that information, because this row, the top row, tells you all the people who tested positive. The bottom row tells you the people who tested negative, then the left column gives you the people who do have the medical condition, in this case, some kind of cancer, and the right column tells you the people who do not have that condition. Now, what we need to do is to start filling it out with numbers. Now, the first thing we need to specify is the population. In this case, we want to start with a big enough population that we're not going to have a lot of fractions in the other boxes. So let's just imagine that the population is 100,000. Make it 1 million or 10 million. It doesn't matter because we're going to be interested in the ratios of the different groups. We can use that 100,000 to fill out the other boxes if we know the prevalence or the base rate. Because the base rate tells you what percentage of that 100,000 actually do have the condition and don't have the condition. We imagined, remember, we're just making up numbers here, but we imagined that the prevalence of this condition is 0.3%. And that means out of 100,000 people, there will be 300 who do have the medical condition. Well, if there are 300 who have it and there are 100,000 total, we can figure out how many don't have the medical condition by just subtracting, which means 99,700 do not have the medical condition. Okay? Now we've divided the population into our two columns, the ones that do and the ones that don't have the medical condition. The next step is to figure out how many are going to test positive and how many are going to test negative out of each of these groups. For that, we first need the sensitivity. The sensitivity tells us the percentage of the cases that have the condition who will test positive. So the people who have the condition are the 300. The ones who test positive are going to go up in this area. And we know from the sensitivity being 0.99 or 99% that the number in that area should be 99% of 300 or 297. And of course, if that's the number that tests positive, then the remainder are going to test negative, and that means that we'll have 3, which shouldn't surprise you because if 99% of the cases that have it test positive, then 1% will test negative, and 1% of 300 is 3. Good, so we got the first column done. Now, the next question is going to be the specificity. We can use the specificity to figure out what goes in that next column. If the specificity is 99, and we know that 99,700 people do not have the condition out of our sample of 100,000, well, that means that 99% of 99,700 are going to test negative because the specificity is the percentage of cases without the condition that test negative. And that means that we'll have 98,703 among the people who do not have the condition who test negative. How many are going to test positive? The rest of them. So 99,700 minus 98,703 is going to be 997. And of course, that shouldn't be surprising again because 1% of 99,700 is 997. And we only got 2 boxes left to fill out. How do you fill out those? Well, this box in the upper right is the total number of people in this population of 100,000 who test positive. And so we can get that by adding the ones that do have the condition and test positive and the ones that don't have the condition and test positive. Just add them together and you get 1,294. And you do the same on the next row because that blank is the area that has all the people who test negative and 3 people who have the condition test negative, 98,703 people who do not have the condition test negative. So the total is going to be 98,706. And we can check to make sure that we got it right by just adding them together. 1,294 plus 98,706 is equal to 100,000. Phew, we got it right. Okay, so now we've divided the population into those people who have the condition, those people who don't have the condition, and we know how many of each of those groups test positive and how many of each of those groups test negative. But the real question is, what's the probability that I have cancer or the medical condition given that I tested positive? How do we figure that out? Well, the total number of positive tests was 1294, and the people who tested positive who really had the condition was 297. So it looks like the probability of actually having the condition given that you tested positive is 297 out of 1294, or 0.23. That's 23%, less than 1 in 4. Is that what you guessed? Most people, including most doctors, when they hear that the test is 99% sensitive and 99% specific, will guess a lot higher than 1 in 4.
Oh my gosh! I'm a doctor and I never would have thought that.
Now don't worry, she's not a physician, she's a metaphysician.
But in this case, the probability really is just 1 in 4 that you have that medical condition. Now, how did that happen? The reason was that the prevalence or the base rate was so low that even a small rate of false positives, given the massive numbers of people who don't have the condition, will mean that there are more false positives, 3 times as many, as there are true positives. And that's why the probability is just 1 in 4, actually a little less than 1 in 4, that you have the medical condition even when you tested positive. I want to add a quick caveat here in order to avoid misinterpretation. Because the point here is that if you have a screening test for a condition with a very low base rate or prevalence, and you don't have any symptoms that put you in a special category, then you need to get another test before you jump to any conclusions about having the medical condition. Because if you have that other test, then the fact that you tested positive on the first test puts you in a smaller class with a much higher base rate or prevalence, and now the probability is going to go up. Most doctors know that, and that's why after the first test they don't jump to conclusions and they order another test. But many patients don't realize that, and they get extremely worried after a single test, even when they don't have any symptoms. So that's the mistake that we're trying to avoid here. Now that's surprising, but it actually applies to many different areas of life. It applies, for example, to medical tests with all kinds of other diseases, not just cancer or colon cancer, but pretty much every disease where the prevalence is extremely low. It applies also to drug tests. If somebody gets a positive drug test, does that mean they really were using drugs? Well, if it's a population where the base rate or prevalence of drug use is quite low, then it might not. Of course, if you assume that the prevalence or base rate is quite high, then you're going to believe that drug test. But you need to know the facts about what the prevalence or base rate really is in order to calculate accurately the probability that this person really was using drugs. Same applies to evidence in legal trials. Take eyewitnesses, for example. It's very tricky. Someone's trying to use their eyes as a test for what they see. They might identify a friend, or they might just say, that car that did the hit and run accident was a Porsche. Well, how good are they at identifying Porsches? If they get it right most of the time, but not always, and sometimes they don't get it right when it is a Porsche, then we've got the sensitivity and specificity of what they identify, and we can use that to calculate how likely it is that their evidence in the trial really is reliable or not. Another example is the prediction of future behavior. We might have some kind of marker that a certain group of people with that marker have a certain likelihood of committing crimes. But if crimes are very rare in that community and every other, then a test which has a pretty good sensitivity and specificity still might not be good enough when we're talking about something like crime that's actually very rare and has a very low prevalence or base rate in most communities. And the same applies to failing out of school. Are SAT scores or GRE scores going to be good predictors of who's going to fail out of school? Well, if very few people fail out of school so that the prevalence and base rate is very low, then even if they're pretty sensitive and specific, they might not be good predictors. So this same type of problem arises in a lot of different areas. And I'm not going to go through more examples right now, but we'll have plenty of examples in the exercises at the end of this chapter. I want to end, though, by saying a few things that are a bit more technical about this method. First, there's a lot of terminology to learn, because when you read about using this method in other areas for other types of topics, then you'll run into these terms, and it's a good idea to know them. So first, the cases where the person does have the condition and also tests positive are called hits or true positives. Different people use different terms. The cases where the person tests positive but they don't have the condition are called false positives or false alarms. The cases where a person really does have the condition but tests negative are called misses or false negatives. And the cases where the person does not have the condition and the test comes out negatives are called true negatives, because they're negative and it's true that they don't have the condition. If we put together the false negatives and the true negatives, we get the total set of negatives. And if we put together the true positives and the false positives, we get the total set of positives. And of course, we have the general population, and within that population, a percentage that have the condition and a percentage that don't have the condition. Now, what's the base rate? The base rate in this population is simply the set that have the condition divided by the total population, which is box 7 divided by box 9. If we use E for the evidence and H for the hypothesis being true that the condition really does exist, then that's the probability of H. And the sensitivity is going to be the total number of true positives divided by the total number of people with the condition, because it's the percentage of people who have the condition and test positive. Okay? So that's the probability of E given H, and it's box 1 divided by box 7. The specificity, in contrast, is the ratio of it being a true negative to the total number of people who do not have the condition. That is, the probability of not E, that is, not having the evidence of a positive test result, given not H, given that you're in this second column where the hypothesis is false because you don't have the condition. So that's box 5 divided by box 8. That's the specificity. So we can define all of these in terms of each other. The hits divided by the total with that condition is going to be the sensitivity. And you can use this terminology to guide your way through this box. And the big question is again going to be, what's the solution? What's the probability of the hypothesis having the condition given the evidence, that is, a positive test result? That's going to be box 1 divided by box 3. And as we saw in the case that we just went through, that gives you the probability of having the medical condition or colon cancer given a positive test result. That's called the posterior probability or in symbols, the probability of the hypothesis given the evidence. So I hope this terminology helps you understand some of the discussions of this if you go on and read about it in the literature. This procedure that we've been discussing is actually just an application of a famous theorem called Bayes' theorem after Thomas Bayes, an 18th century English clergyman who was also a mathematician and proved this extremely important theorem in probability theory. Now, some of you out there will use the boxes and it'll make sense to you. But some Courserians, I assume, are mathematicians and they want to see the mathematics behind it. So now, I want to show you how to derive Bayes' theorem from the rules of probability that we learned in earlier lectures. So for all you math nerds out there, here goes. You start with rule 2G. Apply it to the probability that the evidence and the hypothesis are both true. And by the rule, that probability is equal to the probability of the evidence times the probability of the hypothesis given the evidence. You have to have that conditional probability because they're not independent. Then, you simply divide both sides of that by the probability of the evidence. A little simple algebra. And you end up with the probability of the hypothesis given the evidence is equal to the probability of the evidence and the hypothesis divided by the probability of the evidence. Now we can do a little trick. This was ingenious. Substitute for E something that's logically equivalent to E, namely the evidence and the hypothesis or the evidence and not the hypothesis. Now if you think about it, you'll see that those are equivalent because either the hypothesis has to be true or not the hypothesis is true. One or the other has to be true, and that means that the evidence and the hypothesis or the evidence and not the hypothesis is going to be equivalent to E. So this is equivalent to this. And because they're equivalent, we can substitute them within the formula for probability without affecting the truth values. So we just substitute this formula in here for the E up there. And we end up with the probability of the hypothesis given the evidence is equal to the probability of the evidence and the hypothesis divided by the probability of the evidence and the hypothesis or the evidence and not the hypothesis. Now that's not supposed to make much sense, but it helps with the derivation. The next step is to apply Rule 3 because we have a disjunction. And notice that disjuncts are mutually exclusive. It cannot be true both that the evidence and the hypothesis is true and also that the evidence and not the hypothesis is true because it can't be both H and not H. So we can apply the simple version of Rule 3, and that means that the probability of E and H or E and not H is equal to the probability of E and H plus the probability of E and not H. We're just applying that Rule 3 for disjunction that we learned a few lectures ago. Now we apply Rule 2G again because we have the probability of a conjunction up in the top. And since these are not independent of each other, we hope not if it's a hypothesis and the evidence for it, then we have to use the conditional probability. And using Rule 2G, we find that the probability of the hypothesis given the evidence is equal to the probability of the hypothesis times the probability of the evidence given the hypothesis divided by the probability of the hypothesis times the probability of the evidence given the hypothesis plus the probability of the hypothesis being false, that is the probability of not H, times the probability of the evidence given not H, or the hypothesis being false. Now that's a mouthful, and it's a long formula, but that's the mathematical formula that Bayes proved in the 18th century, and that provides the mathematical basis for that whole system of boxes that we talked about before. But if you don't like the mathematical proof, if If that's too confusing for you, then use the boxes. And if you don't like the boxes, use the mathematical proof. They're both going to work. Just pick the one that works for you. In fact, you don't have to pick either of them, because remember, this is an honors lecture, it's optional, and it won't be on the quiz. But if you do want to try this method and make sure that you understand it, they'll have a bunch of exercises for you where you can test your skills. We've talked about using probability to determine what to believe, such as whether to believe that a certain form of contraception will work or will probably work, or whether to believe that you have cancer when a doctor has done a test and you got a positive result, which can be pretty scary, but you still have to figure out whether to believe that you really do have cancer. Now, probability can be very useful in the formation of beliefs, but it's also extremely useful in making decisions. So in this lecture, we want to talk about the use of probability to make decisions or choices. There are three kinds of decisions or choices that we need to discuss. First of all, decisions with certainty. Second, decisions with risk. And third, decisions with ignorance, or as those are sometimes called, decisions with uncertainty. And we'll talk about the first two, and then I'll just say a few words about the third. First, let's look at decisions with certainty. A decision with certainty is one where you know exactly what's going to happen. You know what the effects are going to be, and you know it definitely. It's not that it's probably going to happen. You know what's going to happen. You know the good effects and the bad effects. So there's no uncertainty. Everything's certain. For example, suppose you go to a restaurant, an Italian restaurant, with a friend of yours, and you have to decide whether to order pasta or pizza. Some really nice eggplant parmesan on top of pasta that you like at this restaurant. They also have really good mushroom pizza. So you have to think about that. But you know that if you order the eggplant parmesan pasta, then they're going to bring it to you. And you know that if you order the mushroom pizza, they'll make one for you. And you've got enough money for both of them, so there's no uncertainty. You know what you're going to get. Still might be a difficult choice because, well, you might not be sure whether you feel more like the eggplant parmesan pasta tonight or the mushroom pizza. And there's going to be also potentially a conflict of values. Maybe the eggplant parmesan pasta costs more than the pizza, in which case you have to decide, well, even though I like it more, do I want to spend that money right now? You got a conflict between what you feel like and how much it's going to cost. Or there might be a conflict with your friend. Your friend wants to buy the mushroom pizza and split it with you because he doesn't want an entire pizza himself. But you really feel like the eggplant parmesan. And so now you've got a conflict between your loyalty to your friend. You want to support your friend and help your friend get what he wants. And yet you feel like the eggplant parmesan yourself. So these decisions can be very difficult in some cases, but there's no uncertainty. You still know that if you order the eggplant parmesan, you're going to get eggplant parmesan. And if you order the pizza, you're going to get pizza. Right? There's no uncertainty at all. No, of course there's uncertainty. You might order the pizza and it comes burned. Yuck! Oh, I hate burned pizza. And you might order the eggplant parmesan and it turns out that they really just messed up the sauce and it's got way too much salt in it tonight. Maybe they have a new chef back in the kitchen who's going to mess up one but not the other. It's not really certain that when you order it, you're going to get what you wanted or that you're going to like it. Now, this is just a fact about life. There's nothing really certain in this life. You might think that you know exactly what's going to happen, but there's always at least some chance that it's not going to turn out the way you thought. And so, what do you do about that? Well, some people just stipulate. If I order the pizza, I'll get the pizza, and it'll be good pizza. Well, you can, of course, stipulate that, but then it just makes the whole situation unrealistic, because in real life, you're never going to know for certain. So another possibility is to say we're just going to ignore these slight chances that the pizza is going to come back burned. I've been at this restaurant 100 times before. They've always done it just right. And so what are the odds they're going to burn it this time? Pretty slim. 99% chance they're going to do it the right way. Well, you might want to say, I'm just going to ignore the 1% chance of getting burned because it's not going to make any difference. I still want the pizza, or I still want the eggplant, whichever. The other thing you might do is say, look, nothing's certain, but the probabilities are balanced. They go on both sides. After all, there's a chance of burning the pizza. There's also a chance of burning the eggplant. So in some cases, it might make perfectly good sense to ignore these uncertainties because they're not going to affect your decision-making process. Still, it's important to realize that in life, throughout life, in all areas of life, there's always going to be some uncertainty, and that means there's going to be a probability that, if you look at it seriously, is going to play into the decision-making process. So, the kinds of cases that we want to focus on are the cases of risk, where there is a probability of failure and a probability of success for the different plans that you have to choose among. All realistic examples, then, are actually decisions under risk, especially the most important ones. So what is a decision under risk? It's simply a case where you're not absolutely certain what's going to happen. It's not definitely this effect will occur, that effect will occur. You'll get your pizza, it'll taste good. You'll get your pasta, it'll taste good. Instead, there's a probability of each outcome. There's a probability that the pizza will get to the table. There's a probability that the pizza will taste good. There's a probability that the pizza will never make it to the table but get dropped by the waiter, or that the pizza will taste horrible because it was burned. Then you have a decision under risk. And how do we make these decisions under risk? Well, there are a lot of different theories, but one pretty common one is to apply expected value theory. Now, we're going to see that there are lots of different values and it's hard to see how to handle them all, but let's start with a really simple case. Let's assume for now that all that matters is money. One common way, perhaps the most common way of figuring this out, is to calculate the expected monetary value or the expected financial value. And that calculation is pretty simple. It's the probability of winning times the net gain if you do win, minus the probability of losing times the net loss if you do lose. And here we're talking about gains and losses in terms of money. But why do we say net loss and net gain? Well, imagine you buy a lottery ticket and you win $20 million and they send you a check for $20 million. Well, how much did you win? Sounds like you won $20 million, but not really. You never got that dollar back that you paid for the ticket. So really, you only won $19,999,999. Now that's pretty trivial if you just won the lottery. No big deal. But now, imagine a different circumstance where you're playing poker. You bet $10, and the opponent raises it to $20, and you're bluffing, so you want to bet big, so you bet $200. Put that all in the pot too. And your opponent backs down, and you pull in the entire pot. How much has it got in it? $230. Well, did you win $230? No, because you put in $210. You only won $20. The net winnings are how much you pull in minus how much you put in before you pulled in your winnings. So it's 230 minus the 210 you put in. You only gained 20. A lot of people forget that in poker, and they end up thinking that they win a lot by bluffing, when actually they didn't win as much as they thought they did. In any case, we have to look at the net gain and the net loss when applying this formula for expected financial value. Let's do a few examples of calculating expected financial values. And let's do them with a deck of cards because we're familiar with that. There are 13 different cards and 4 different suits: spades, hearts, diamonds, and clubs. So we have to remember that to calculate the probabilities. Let's imagine that you can make this bet. If you bet $1, you'll win $5 net if you pick a spade. Now notice that it's net, so that means either you put $1 in and then you take $6 out and your net gain is 5. Or you say, if it's not a spade, I'll give you $1, and if it is a spade, you give me $5. Either way, if you pick a spade, you're going to be $5 up. What's the expected financial value of this bet? Well, we know that the odds of picking a spade is 1 in 4. That's the odds of winning, because if you pick a spade, you win. And the net gain is $5. So to calculate the expected financial value, we need to multiply this 1/4, the odds of picking a spade, times 5, the number of dollars that you win net if you win. And then we have to subtract the odds of losing 3/4, because if you pick a heart, a diamond, or a club, then you'll lose. And what do you lose? You lose $1. So 1/4 times 5 is 5/4. 3/4 times 1 is 3/4. Subtract 3/4 from 5/4, you get 2/4, and that, of course, is a half. So the expected financial value of this bet is 1/2. Now, compare that bet to another bet. In this bet, if you bet $1, you're going to win 10. That sounds pretty good. Instead of winning 5, you're going to win 10. But you only win $10 net if you pick an ace. And there are 13 cards, so we have to redo the calculations. And the probability of picking an ace is 1 in 13. The amount you win is 10. That's your net winnings, remember. You have to subtract the probability of losing, 12 in 13, because you're going to lose if it's any card other than an ace. And the amount you'll lose is $1 net. 10 times 13 is 13/10. Subtract 12/13 times 1, which is 12/13, and you get negative 2/13. Notice that's negative 2/13. That means the expected financial value of that bet is negative. You ought to expect to lose money over the long run if you play that kind of bet a lot. Third example. This time, you can bet $1 and win $51 net if you pick an ace of spades. But you can't pick any old ace or any old spades. It's got to be the ace of spades. So now what's the financial value of that bet? The expected financial value is probability of winning, 1 over 52, times the amount you win net, which is 51, minus the probability of losing, 51 over 52, times the amount you lose net, if you lose. 51 times 1 over 52 is 51 50-seconds. 51 50-seconds times 1 is 51 50-seconds. Subtract them, and you get 0. So in this bet, the expected financial value of the bet is 0. Okay? Now we can compare these 3 bets by asking, which bet should you make? Well, the first bet was favorable. A bet's favorable if its expected value is greater than 0. And that means that it's in your interest to bet, at least if your only interest is money. A bet's unfavorable if its expected value is less than 0. And a bet is neutral or fair if its expected value is 0. And if you have a bet that's favorable, a bet that's unfavorable, and a bet that's neutral, it shouldn't be surprising that the one you should pick is the one that's favorable, where the expected value is greater than 0, if you're going to bet at all. And that's the next question that we have to turn to. In the previous lecture, we saw that if you're going to bet, then you ought to pick a favorable bet over an unfavorable bet, and even over a neutral or fair bet. But the next question is, do you want to bet at all? And there, we have to look at other values besides money. Let's consider this case. Suppose that you can't just bet $1. This game's not for fun. These are serious gamblers. Your minimum bet is $100,000. And now, if you draw a spade, you win $1 million net. Cool. Well, what's the expected financial value? 1 chance in 4 of picking a spade. The amount you win net is $1 million. You have to subtract the probability of losing, 3 out of 4, because you lose if you pick a heart, a diamond, or a club, times the amount you bet, which is 100,000. Pretty neat. This bet's got an expected financial value of $175,000. Now that sounds like a great bet, but is it really a great bet? It is favorable, but it's only favorable financially. Imagine that $100,000 is all the money you got in the world. It's what you use to pay your rent with. It's all your retirement money. And if you lose it, you're going to be out on the street with nothing. Then, should you bet this money? No, absolutely not. It just doesn't make sense to take that kind of risk with this money if you're going to be out on the street if you lose, because you got 3 chances in 4 of losing. Sure, you might win, you might be better off, but you got an awful lot to lose. And that's why you shouldn't make this bet, because there's just too much to lose. Now, what does that mean? Think about what it means that there's too much to lose. It's not that there's too much money to lose, because you've just calculated the financial value of the bet. What really is the loss is security. You're not going to have a place to live. You're not going to know how to make ends meet or buy your next meal. That's the problem, is there are lots of other values besides money. And in these situations where we say you've got too much to lose, it's those other considerations in addition to money that make it a bad bet. Now let's look at the other side. In some cases, you don't have too much to lose, you've got too much to win. That is, the amount that you win just might not add up in the way that you thought it would. This is the phenomenon called diminishing marginal utility. And what that means is that each increment decreases as you get more and more and more of those increments. You just don't need that much. One example is hamburgers. If you're really hungry and you don't have anything to eat, you might want a hamburger. But what about 2 hamburgers? Is 2 hamburgers twice as good as 1 hamburger? Well, not really. I mean, maybe you want 2 hamburgers. That'd be nice, but it's not twice as good. And what about 3 hamburgers? Is that 3 times as good as 1 hamburger? And what about 4 or 5 or 6 or 7 or 8 or 9 or 10? What about 10 hamburgers? Are 10 hamburgers 10 times as valuable to a hungry person as 1 hamburger? No, because you're going to get full before you ever eat that 10th hamburger. So the marginal utility of a hamburger goes down. The first one might be very valuable to a hungry person with nothing to eat. The second one's a little less, the third one's a little less, the fourth one's a little less, and the difference between 9 and 10 might be totally negligible because they're all going to go bad before you eat all 10 of them. The same thing happens in lotteries. Let's compare 2 lotteries. In the first lottery, if you buy 1 ticket for $100, then you have 1 chance in a million of winning $300 million. That sounds like a pretty good bet. Compare it to this lottery. If you buy 1 ticket for $200, then you have a 1 in 2 million chance of winning $1 billion. Which of these lotteries has a higher expected financial value? The one with the larger expected financial value is lottery B. Does that mean that you ought to spend the extra money to play in lottery B instead of lottery A? Well, that depends, I suppose. How much more valuable is $1 billion to you than 300 million? 300 million is a lot of money. I could buy pretty much anything I ever wanted if I had $300 million. I'm not sure why I would want all that extra money. It's like the 10th hamburger. I wouldn't really need it. So, which of these lotteries should you pick if that's the way you see the relationship between the winnings? Well, even though the expected financial value is greater in lottery B, you might reasonably pick lottery A because you have a bigger chance of getting the 300 million. And the difference between 300 million and a billion doesn't matter that much to you. Not everybody's going to share that value judgment, but if it doesn't really matter much to you whether you have 300 million or a billion, then it makes sense to go for lottery A. And this shows, yet again, that there's more to life than expected financial value. The other values in life are captured in the notion of overall value. The actual overall value, or sometimes called utility of an act, is simply all of the good and bad effects that the act actually has, the values of those effects, positive values and negative values calculated together. And the expected overall value of the bet or of an action, sometimes called the expected utility of the act, is all of the good and bad effects of the act multiplied by the probability of each of those effects. So you bring not just the values into play, but also the probabilities. And if you're really going to decide what you ought to do, you shouldn't be looking just at money. You should be looking at all the different values, including security, as we mentioned, or how much good the money's really going to do you if you're going to have $300 million anyway. There's lots of other things to consider. The problem is, how do you calculate that? How are you going to actually calculate overall value or expected overall value? Here's an example to show how hard it is. Imagine that you have a friend that you'd love playing with after school, and you then get an offer of a job, and you can make a bunch of money by doing the job after school, but then you won't get to play with your friend. Well, how are we going to figure this out? Let's calculate the expected overall value. What's the probability that if you take the job, you won't be such good friends with them anymore because you won't be playing as much? And then you'll lose your friend. And what's the value of that friend? You got to multiply the probability of losing your friend by the value of that friend. Whoa. How are you going to do that? How do you put a dollar value on that friendship? How do you figure out the probability that your friend's going to leave you and not be as close anyway as he was before? Well, you just can't do that. You can't really put it into numbers like that. Now, some economists have very sophisticated techniques for taking preferences and attaching values to those preferences and then multiplying by probabilities. And so I don't want to say it cannot be done, but the point here is just it's a lot more difficult than figuring out whether you want to make a bet in a simple little poker game or even whether you want to put your money into the lottery. When we start talking about real decisions about friends and about other values in life, some of them cannot be reduced to money, and then it's hard to put a number on them and it's hard to do the actual calculations. So I don't want to suggest that any of this decision theory regarding expected utility is going to actually be applied in real life. Another reason that's worth mentioning is that third kind of decision that I mentioned at the beginning of the lecture, namely decisions with ignorance. Sometimes you don't even know the probabilities. And if you don't know the probabilities, you can't enter the probabilities in the formula for expected utility or expected financial value or expected overall value. If you don't know the probabilities, how are you going to calculate? You can't. Now, there are lots of tricky rules that people have proposed for decisions under uncertainty or decisions with ignorance, as I call them, but none of those are really conclusive. And there's big disputes about which one is the right rule. So a lot of this discussion is going to be inconclusive. You might have wished that I would come in here and tell you, here's how you figure out exactly what to do in every area of your life. Well, I'm sorry, but I just can't do it, and nobody else can either. Nonetheless, if you think in terms of the various factors that we've been discussing, financial value, other kinds of values, probabilities of the different outcomes, maybe at least you'll be able to avoid some of the worst mistakes that people make in decisions.
Although we're going to be focusing on fallacies in Unit 4, today I want to start off by talking about something that might or might not be a fallacy. But in any case, it exposes a linguistic phenomenon that's called vagueness and that does create fallacies. Okay, so what is the thing I'm going to talk about today? Well, it's a phenomenon I call the argument from the heap, or sometimes called the Sorites argument, after the Greek word soros, which means heap. What's the argument from the heap? Well, let me give you an example. Consider the following argument. This is an example of the argument from the heap. Premise 1, a person who owns only 1 penny is poor. Premise 2, a person who owns only 1 penny more than a poor person is also poor. Conclusion, therefore, a person who owns a gazillion pennies is poor. Now, why should we believe that those premises support that conclusion? Well, think of it this way. If premise 1 is true, then a person who owns only 1 penny is poor. But if premise 2 is true, then it's going to follow that a person who owns 2 pennies is also poor, right? Because they own only 1 penny more than a poor person. And anyway, that's obviously right. A person who owns only 2 pennies is clearly poor. And then it's going to follow by premise 2 that a person who owns 3 pennies is also poor, right? Because they only own just 1 penny more than a poor person. So they're also going to be poor. And by premise 2, it's also going to follow that a person who owns 4 pennies is poor. Now, I hope you can see the pattern here. You can see where this is going. We can keep on applying premise 2 to our results, and we'll get that a person who owns 4 pennies is poor, a person who owns 5 pennies is poor, a person who owns 6 pennies is poor, and we can go on and on and on to 1,000,000 pennies, 1,000,000,000 pennies, 1,000,000,000,000 pennies, 1,000,000,000,000 pennies, and even a gazillion pennies. Now, there's a name for that kind of reasoning, which is common in mathematics. It's called the principle of mathematical induction. The principle of mathematical induction says that arguments of the following form are valid. Where premise 1 says the number 0 belongs to some category F, in our example, the category of numbers such that anyone who owns that number of pennies is poor. If X belongs to F, then X plus 1 belongs to F, that's premise 2. So in other words, that's saying that if a particular number of pennies is such that anyone who owns just that number of pennies is poor, then adding 1 to that particular number of pennies will also leave the person poor. And the conclusion is of the form all natural numbers belong to F. In other words, no matter how many pennies you own, you're still going to be poor. Right? All natural numbers belong to the category of numbers such that a person who owns that number of pennies is poor. That's the principle of mathematical induction, stated quite generally. Now, that principle, I'm quite confident, is correct. Right? Arguments of that form are valid. If arguments of that form weren't valid, then a whole lot of mathematics that mathematicians accept today would be false. And I don't believe it is. So, the principle of mathematical induction, I'm prepared to say, is correct. But then, what's going on in this argument? Right? If the principle of induction is correct, then it looks like the argument is valid. So if the argument is valid, that means there's no possible way for the premises to be true while the conclusion is false. So, is premise 1 true? Is it true that a person who owns only 1 penny is poor? Seems quite obviously yes. Premise 1 is true. A person who owns only 1 penny has got to be poor. And there's nowhere in the world where 1 penny makes you rich. What about premise 2? If you own just 1 penny more than a poor person, could you avoid being poor by owning just 1 penny more than a poor person? I don't see how you can. Right? 1 penny can't make the difference between being poor and not being poor. So it looks like premise 2 is true. But if the argument is valid and both of the premises are true, then that means the argument is sound. And remember, in a sound argument, the conclusion has to be true. So let's consider the conclusion. A person who owns a gazillion pennies is poor. Is that true? Well, no, it's not true. I wish I owned a gazillion pennies. Owning a gazillion pennies does not leave you poor. Someone who owns a gazillion pennies is very, very wealthy. So the conclusion seems to be obviously false. So what's going on here? Well, in logic, this is what we call a paradox. A paradox is an argument in which all of the premises of the argument seem to be obviously true, as in our argument from the heap. The argument seems to be obviously valid, again, as in our argument from the heap, but the conclusion seems to be obviously false, again, as in our argument from the heap. So our argument from the heap is one example of a paradox. There are many other examples. Now, some paradoxes are fallacies because despite appearances, even though they appear to be valid, they're really not. Really, they're arguments in which the premises don't support the conclusion, despite appearances. So some paradoxes are fallacies. But the question is this particular paradox a fallacy? Is the argument from the heap a fallacy? Or is it just a paradox? And if it is a paradox, what's the solution? Should we say that a person could avoid being poor even though they own only 1 penny? Should we say that you could avoid being poor by owning just 1 penny more than a poor person? Or should we deny the principle of mathematical induction? Or should we say that even if you own a gazillion pennies, you're still poor? How should we solve this paradox? I'll leave that for you to think about. Hello, and welcome to Unit 4 of our course. In the last 2 units, we've been focused on rules for good arguments. Specifically in Unit 2, we were focused on rules by means of which to evaluate and explain the validity of deductive arguments. And in Unit 3, we were focused on rules by means of which to evaluate and explain the strength of inductive arguments. Now, in Unit 4, we're not going to focus on good arguments, we're going to focus on bad arguments. Specifically, we're going to focus on a kind of bad argument that's called a fallacy. So what's a fallacy? Well, a fallacy is a kind of bad argument, as I said, but not all bad arguments are fallacies. Some arguments are bad because their premises are false. But that's not why fallacies are bad. Of course, a fallacy could have false premises also, but that's not what makes an argument a fallacy. What makes an argument a fallacy is that its premises, whether they're true or false, don't support its conclusion. They're not the right kind of premises to support the conclusion that the argument draws, whether they're true or false. So that's what makes a fallacy. Let me give you some examples, show you what I have in mind. So consider this argument. The majority of violent crime in the United States is committed by men who earn less than $30,000 a year. By the way, that's true. Conclusion that the argument draws from that. Therefore, when you see a man who earns less than $30,000 a year, he is likely to be a violent criminal. Okay. Now, that's a bad argument. But it's not a bad argument because its premise is false. Actually, its premise is true. So what makes it a bad argument? What makes it a bad argument is that its premise doesn't support its conclusion. Right? The premise says that most of the things that fall into one category, the category of perpetrators of violent crime in the United States, also fall into a second category, the category of men who earn less than $30,000 a year. But then the conclusion says that most of the things that fall into that second category, the category of men who earn less than $30,000 a year, also fall into that first category, the category of perpetrators of violent crime. And that conclusion isn't supported by the premise. Just because the majority of things in one category also fall into a second category, it doesn't mean that the majority of things in that second category also fall into that first category. So that argument is a fallacy. And it's a fallacy, it's a bad argument, even though its premise is true. So that's one example of a fallacy. Here's another example of a fallacy. Consider this argument. Premise 1. If the national government increases spending, investors will lose confidence in the national currency. Premise 2. Investors have lost confidence in the national currency. Conclusion, the national government must have increased spending. Okay. Now, since the premises don't specify which nation we're talking about, we could imagine that there's some nation of which both of the premises are true. Right? We don't need to get into the details of which nation that would be, but imagine that there's some nation of which both of the premises are true. But even if both of the premises are true concerning that nation, they don't support the conclusion. So this argument is a fallacy. It's a bad argument, not because the premises are false, but because even if the premises are true, they still don't support the conclusion. Right? The premises say if one thing is true, let's say if national government increases spending, then a second thing is also going to be true. Investors will lose confidence. Then the second premise says that that second thing is true, that investors have lost confidence, but the conclusion says, so the first thing must be true. But that doesn't follow, right? Remember how conditionals work. Just because a conditional is true and its consequent is true, it doesn't follow from that that the antecedent of the conditional is true. You can see that from looking at the truth table for the conditional. So this is an example of an argument in which the premises don't support the conclusion, even if the premises are true. So this argument is also a fallacy. Now, here's an example of a bad argument that's not a fallacy. Look at this one. Most of the crude oil in the world is in Texas. So that's premise 1. Premise 2, Texas is going to secede from the United States. So, conclusion, domestic oil availability in the United States is going to plummet. Okay, now this argument, although it's a bad argument, is not a fallacy. It's not a fallacy because the premises really do support the conclusion. If both of those premises are true, then the conclusion has got to be true, right? If most of the crude oil in the world is in Texas and Texas is going to secede from the United States, then domestic oil availability in the United States really is going to plummet. Thankfully for domestic oil availability in the United States, though, those two premises are not true. In fact, neither of them is true. So, in any case, I'm quite confident that neither of them is true. So this is a bad argument, not because the premises don't support the conclusion. They do support the conclusion. This is a bad argument because the premises aren't true. Okay, so I've given you examples of bad arguments that are fallacies and a bad argument that's not a fallacy. But for a complete list of fallacies, anyhow a nearly complete list of fallacies, I recommend the URL. This URL is the entry on Wikipedia for a list of fallacies, and it's a very long and nearly complete list of fallacies. So you can look at that list, think about the different kinds of fallacies there are, and we're going to describe them in more detail in this unit of the course. In this week in particular, in week 9 of the course, we're going to focus on fallacies that result from the misuse of expressions that are vague or ambiguous. Okay, see you next time. Hello, and welcome to Unit 4 of our course. In the last 2 units, we've been focused on rules for good arguments. Specifically in Unit 2, we were focused on rules by means of which to evaluate and explain the validity of deductive arguments. And in Unit 3, we were focused on rules by means of which to evaluate and explain the strength of inductive arguments. Now, in Unit 4, we're not going to focus on good arguments, we're going to focus on bad arguments. Specifically, we're going to focus on a kind of bad argument that's called a fallacy. So what's a fallacy? Well, a fallacy is a kind of bad argument, as I said, but not all bad arguments are fallacies. Some arguments are bad because their premises are false. But that's not why fallacies are bad. Of course, a fallacy could have false premises also, but that's not what makes an argument a fallacy. What makes an argument a fallacy is that its premises, whether they're true or false, don't support its conclusion. They're not the right kind of premises to support the conclusion that the argument draws, whether they're true or false. So that's what makes a fallacy. Let me give you some examples, show you what I have in mind. So consider this argument. The majority of violent crime in the United States is committed by men who earn less than $30,000 a year. By the way, that's true. Conclusion that the argument draws from that: therefore, when you see a man who earns less than $30,000 a year, he is likely to be a violent criminal. Okay. Now, that's a bad argument. But it's not a bad argument because its premise is false. Actually, its premise is true. So what makes it a bad argument? What makes it a bad argument is that its premise doesn't support its conclusion. Right? The premise says that most of the things that fall into one category, the category of perpetrators of violent crime in the United States, also fall into a second category, the category of men who earn less than $30,000 a year. But then the conclusion says that most of the things that fall into that second category, the category of men who earn less than $30,000 a year, also fall into that first category, the category of perpetrators of violent crime. And that conclusion isn't supported by the premise. Just because the majority of things in one category also fall into a second category, it doesn't mean that the majority of things in that second category also fall into that first category. So that argument is a fallacy. And it's a fallacy, it's a bad argument, even though its premise is true. So that's one example of a fallacy. Here's another example of a fallacy. Consider this argument. Premise 1. If the national government increases spending, investors will lose confidence in the national currency. Premise 2. Investors have lost confidence in the national currency. Conclusion: the national government must have increased spending. Okay. Now, since the premises don't specify which nation we're talking about, we could imagine that there's some nation of which both of the premises are true. Right? We don't need to get into the details of which nation that would be, but imagine that there's some nation of which both of the premises are true. But even if both of the premises are true concerning that nation, they don't support the conclusion. So this argument is a fallacy. It's a bad argument, not because the premises are false, but because even if the premises are true, they still don't support the conclusion. Right? The premises say if one thing is true, let's say if national government increases spending, then a second thing is also going to be true. Investors will lose confidence. Then the second premise says that that second thing is true, that investors have lost confidence, but the conclusion says, so the first thing must be true. But that doesn't follow. Right? Remember how conditionals work. Just because a conditional is true and its consequent is true, it doesn't follow from that that the antecedent of the conditional is true. You can see that from looking at the truth table for the conditional. So this is an example of an argument in which the premises don't support the conclusion, even if the premises are true. So this argument is also a fallacy. Now, here's an example of a bad argument that's not a fallacy. Look at this one. Most of the crude oil in the world is in Texas. That's premise 1. Premise 2, Texas is going to secede from the United States. So, conclusion, domestic oil availability in the United States is going to plummet. Okay, now this argument, although it's a bad argument, is not a fallacy. It's not a fallacy because the premises really do support the conclusion. If both of those premises are true, then the conclusion has got to be true. Right? If most of the crude oil in the world is in Texas and Texas is going to secede from the United States, then domestic oil availability in the United States really is going to plummet. Thankfully for domestic oil availability in the United States, though, those two premises are not true. In fact, neither of them is true. So, in any case, I'm quite confident that neither of them is true. So this is a bad argument, not because the premises don't support the conclusion. They do support the conclusion. This is a bad argument because the premises aren't true. Okay, so I've given you examples of bad arguments that are fallacies and a bad argument that's not a fallacy. But for a complete list of fallacies, anyhow, a nearly complete list of fallacies, I recommend the URL. This URL is the entry on Wikipedia for a list of fallacies, and it's a very long and nearly complete list of fallacies. So you can look at that list, think about the different kinds of fallacies there are, and we're going to describe them in more detail in this unit of the course. In this week in particular, in week 9 of the course, we're going to focus on fallacies that result from the misuse of expressions that are vague or ambiguous. Okay, see you next time. Although we're going to be focusing on fallacies in Unit 4, today I want to start off by talking about something that might or might not be a fallacy. But in any case, it exposes a linguistic phenomenon that's called vagueness and that does create fallacies. Okay, so what is the thing I'm going to talk about today? Well, it's a phenomenon I call the argument from the heap, or sometimes called the Sorites argument, after the Greek word soros, which means heap. What's the argument from the heap? Well, let me give you an example. Consider the following argument. This is an example of the argument from the heap. Premise 1, a person who owns only 1 penny is poor. Premise 2, a person who owns only 1 penny more than a poor person is also poor. Conclusion, therefore, a person who owns a gazillion pennies is poor. Now, why should we believe that those premises support that conclusion? Well, think of it this way. If premise 1 is true, then a person who owns only 1 penny is poor. But if premise 2 is true, then it's going to follow that a person who owns 2 pennies is also poor, right? Because they own only 1 penny more than a poor person. And anyway, that's obviously right. A person who owns only 2 pennies is clearly poor. And then it's going to follow by premise 2 that a person who owns 3 pennies is also poor, right? Because they only own just 1 penny more than a poor person. So they're also going to be poor. And by premise 2, it's also going to follow that a person who owns 4 pennies is poor. Now, I hope you can see the pattern here. You can see where this is going. We can keep on applying premise 2 to our results, and we'll get that a person who owns 4 pennies is poor, a person who owns 5 pennies is poor, a person who owns 6 pennies is poor, and we can go on and on and on to 1,000,000 pennies, 1,000,000,000 pennies, 1,000,000,000,000 pennies, 1,000,000,000,000 pennies, and even a gazillion pennies. Now, there's a name for that kind of reasoning, which is common in mathematics. It's called the principle of mathematical induction. The principle of mathematical induction says that arguments of the following form are valid. Where premise 1 says the number 0 belongs to some category F, in our example, the category of numbers such that anyone who owns that number of pennies is poor. If X belongs to F, then X plus 1 belongs to F, that's premise 2. So in other words, that's saying that if a particular number of pennies is such that anyone who owns just that number of pennies is poor, then adding 1 to that particular number of pennies will also leave the person poor. And the conclusion is of the form all natural numbers belong to F. In other words, no matter how many pennies you own, you're still going to be poor. Right? All natural numbers belong to the category of numbers such that a person who owns that number of pennies is poor. That's the principle of mathematical induction, stated quite generally. Now, that principle, I'm quite confident, is correct. Right? Arguments of that form are valid. If arguments of that form weren't valid, then a whole lot of mathematics that mathematicians accept today would be false. And I don't believe it is. So, the principle of mathematical induction I'm prepared to say is correct. But then, what's going on in this argument? Right? If the principle of induction is correct, then it looks like the argument is valid. So if the argument is valid, that means there's no possible way for the premises to be true while the conclusion is false. So, is premise 1 true? Is it true that a person who owns only 1 penny is poor? Seems quite obviously yes. Premise 1 is true. A person who owns only 1 penny has got to be poor. And there's nowhere in the world where 1 penny makes you rich. What about premise 2? If you own just 1 penny more than a poor person, could you avoid being poor by owning just 1 penny more than a poor person? I don't see how you can. Right? 1 penny can't make the difference between being poor and not being poor. So it looks like premise 2 is true. But if the argument is valid and both of the premises are true, then that means the argument is sound. And remember, in a sound argument, the conclusion has to be true. So let's consider the conclusion. A person who owns a gazillion pennies is poor. Is that true? Well, no, it's not true. I wish I owned a gazillion pennies. Owning a gazillion pennies does not leave you poor. Someone who owns a gazillion pennies is very, very wealthy. So the conclusion seems to be obviously false. So what's going on here? Well, in logic, this is what we call a paradox. A paradox is an argument in which all of the premises of the argument seem to be obviously true, as in our argument from the heap. The argument seems to be obviously valid, again, as in our argument from the heap, but the conclusion seems to be obviously false, again, as in our argument from the heap. So our argument from the heap is one example of a paradox. There are many other examples. Now, some paradoxes are fallacies because despite appearances, even though they appear to be valid, they're really not. Really, they're arguments in which the premises don't support the conclusion, despite appearances. So some paradoxes are fallacies. But the question is this particular paradox a fallacy? Is the argument from the heap a fallacy? Or is it just a paradox? And if it is a paradox, what's the solution? Should we say that a person could avoid being poor even though they own only 1 penny? Should we say that you could avoid being poor by owning just 1 penny more than a poor person? Or should we deny the principle of mathematical induction? Or should we say that even if you own a gazillion pennies, you're still poor? How should we solve this paradox? I'll leave that for you to think about. In the last class, we talked about the argument from the heap, otherwise known as the Sorites argument. Today, I want to describe the linguistic phenomenon that gives rise to that argument, gives rise to the paradox, explain what that linguistic phenomenon is and why it gives rise to the paradox. The phenomenon is what's known as vagueness. So, what's vagueness? Well, here's a definition along with some examples. So, an expression is vague when there's no precise boundary between the cases to which that expression correctly applies and the cases to which it does not correctly apply. So here's some examples. Poor, as we just saw in the last lecture. Bald, tall, accomplished, famous. Here, consider. What is the precise boundary line between baldness and non-baldness? Is there some precise line where if you have fewer hairs on your head than that, then you're bald, but if you have more hairs on your head than that, then you're not bald? No, there's no precise line. Baldness is vague. You can be more bald by having fewer hairs on your head. You can be less bald by having more hairs on your head. But baldness is vague. There's no precise line between baldness and non-baldness. How about tall? Is there some precise line where if you're taller than that, then you're tall, but if you're shorter than that, then you're not tall? No. Again, there's no precise line. There's some people are taller than others, but there's no precise line where if you exceed that height, then you're tall. How about being accomplished? Is there some precise amount of accomplishment that you have to achieve in order to count as an accomplished person? No. Accomplished, again, is a vague expression. There's no precise amount of accomplishment that's required in order for you to be an accomplished person. Clearly, some people are accomplished, but it's not clear exactly what the outlines of that category are. Some people are clearly included in that category. Some people are clearly not included in that category. But where exactly does the boundary line fall? That's not clear. It's vague. And again, famous. How many people have to know who you are in order for you to be famous? Is Walter famous? Well, someone might say, sure, Walter's famous. Tens of thousands of students are taking his course. Yeah, but someone might say, no, Walter's not famous. Tom Cruise is famous. So, how many people have to know who you are in order for you to be famous? It's not clear. It's vague. So those are some examples of vagueness, examples of expressions that fit the definition of vagueness. Now, why do these expressions give rise to paradox, give rise to the Sorites paradox, the argument from the heap? Here's why. If there's no precise boundaries between cases to which an expression correctly applies and cases to which it incorrectly applies, cases to which it does not correctly apply, then it's going to seem obviously true that making a minuscule change, just having a minuscule difference from a case to which an expression correctly applies or correctly doesn't apply, isn't going to make the difference between whether or not the expression correctly applies. Right? Having someone be just ever so slightly taller than a short person isn't going to make that person tall. If they're ever so slightly taller than a short person, they're still going to be short. If they're ever so slightly less famous than a famous person, they're still going to be famous. Right? It's going to seem that way as long as the boundary line between cases of correct application and cases of incorrect application is not clear. But the problem is that a series of minuscule differences or minuscule changes can add up to a big change. So there could be a big change between two people, but if you just look at the minuscule changes, it'll look like, well, if one person isn't famous, then the other one must not be famous. If one person isn't rich, then the other person must not be rich. Again, because the minuscule differences are so minuscule that they seem not to involve crossing any threshold from cases of correct application to cases of incorrect application. Right? That the differences are too small to allow for you to cross that threshold. Well, the reason is that the threshold isn't a precise one. So that's why it seems like when you have minuscule differences, they're not going to allow you to cross that threshold. If the threshold is fuzzy, then a minuscule difference isn't going to be enough to cross it. But you add up a whole bunch of minuscule differences and you get a big difference, a difference that is big enough to cross the threshold. So that's why vagueness leads to paradox. And here are some examples. Suppose someone says, well, a person with no hair is bald. I mean, clearly someone with no hair at all is bald. But someone with one more hair than a bald person is still bald, right? It seems like if the only difference between you and me is that you have one more hair than I do, then if I'm bald, you must also be bald, right? Someone who has only one more hair than a bald person is bald. But from those two premises, it follows by the principle of mathematical induction that someone with a billion hairs on their head is bald. I mean, I don't even know if it's possible to have a billion hairs on a human head, but if it is, presumably someone who did have a billion hairs on their head would not be bald. And yet, that conclusion follows validly from our two premises. Consider this other example. Someone who's only a meter in height is short. Right? A meter, for those of you who live in the United States, is about 39 inches. So someone who's only a meter in height is a short person. Now you might think, well, someone who's only 1 millimeter taller than a short person is also short. If two people differ in height by 1,000th of a meter, then if one of them is short, you think the other one's got to be short too. But from those two premises, again, it follows by the principle of mathematical induction that someone who's 5 meters tall is short. And that, I can assure you, is not true. Someone who's 5 meters tall, again, for the benefit of people living in the United States, someone who's 5 meters tall is about 195 inches tall. So that would be very, very tall. That would be taller than Dwight Howard. Okay, so again, why does this paradox arise? It arises because vagueness makes the second premise appear to be true. Vagueness makes it seem as if a minuscule difference between two things can't cross the threshold from correct application of an expression to incorrect application of an expression. So that's why the paradox arises. Okay, next time we'll see how the phenomenon of vagueness, how vague expressions can generate not just paradoxes, but also fallacies. See you next time. In the last lecture, we discussed the phenomenon of vagueness and saw why that phenomenon can lead to paradox. In this lecture, and the ones to follow, I want to show how the phenomenon of vagueness can lead not just to paradox, but also to fallacies. Today, we're going to talk about a particular kind of fallacy called a conceptual slippery slope fallacy that results from the phenomenon of vagueness. So what's a conceptual slippery slope fallacy? Well, let me give you a definition. A conceptual slippery slope fallacy is an argument that exploits the vagueness of the category that's involved in the argument in order to argue that there's no significant difference between things that belong to that category and things that don't belong to that category. Okay, so let me give you some examples of this definition. So here's one example. Consider this argument. Premise 1. A person who is 1 meter in height is short. Premise 2. A difference of 1 millimeter is not a significant difference. Certainly not a significant difference in human height. Maybe it's a significant difference in some things, but not in human height. Premise 3, a person who is 2 meters in height is tall. Conclusion, there's no significant difference between being short and being tall. Okay, now notice this is different than the argument from the heap. The argument from the heap would have gone from the premise that a person who's 1 meter in height is short to the conclusion that a person who's 2 meters in height or 5 meters in height or any height at all is also going to be short. That's not what this argument is saying. This argument allows that there's a difference between being short and being tall, but the difference just isn't significant because the difference is made up of a series of differences, each one of which is not significant. Right? The difference between being 1 meter in height and being 2 meters in height is made up of a series of 1 millimeter differences, and 1 millimeter differences are not significant differences in human height. So the argument concludes the 1 meter difference in human height between a 1 meter person and a 2 meter person, that 1 meter difference in human height is itself not a significant difference. So there is no significant difference, the argument concludes, between being short and being tall. Okay, now that's a fallacy. And it's a fallacy not because its premises are false. Actually, its premises are, I think, not false. I think its premises are true. It's a fallacy because the premises don't support the conclusion. Remember, that's what makes it a fallacy, is that the premises don't support the conclusion, even if they are true. Why don't the premises support the conclusion? Well, here's why. The conclusion says that a height difference of 1 meter is not significant. And the premises say that a height difference of 1 millimeter is not significant. And of course, a height difference of 1 meter is made up of a series of 1,000 height differences of 1 millimeter. But just because a millimeter height difference is not significant, and a meter height difference is made up of 1,000 1 millimeter height differences, it doesn't follow that a 1 meter height difference is not significant. Differences that are significant can be made up out of a bunch of differences that are individually insignificant. So that's why this argument right here is a fallacy. Consider another example to illustrate the same point. A person who owns only 1 penny is poor. A difference of 1 penny is not a significant difference in human wealth, right? You don't become significantly wealthier or less wealthy by gaining or losing a penny. And a person who owns a gazillion pennies is not poor, they're rich. Well, from those 3 premises, this argument concludes, there's no significant difference between being poor and being rich. Okay, once again, the argument starts off with 3 premises, each of which is quite plausibly true. I think it is true. But then it draws a conclusion that's ridiculous. Well, why? Well, it's because the argument is one in which the premises don't really support the conclusion. So even if the premises are true, they don't support the conclusion. They don't give us good reason to believe that the conclusion is true. And that's because even if the difference between being poor and being rich is made up out of a series of 1 penny differences, and even if a 1 penny difference is insignificant, it doesn't follow that the difference between being poor and being rich is insignificant, right? A difference that's made up out of a bunch of insignificant differences can still itself be significant. Just because its components are insignificant doesn't mean that it is insignificant. Compare this to the following point. Just because each person in a group is not powerful, does that mean that the group is not powerful? No. Sometimes composites, collections, can have properties, can have features, can belong to categories that their individual members don't have, don't belong to. Right? So even if each individual member of a group is not powerful, that doesn't mean the group is not powerful. And similarly, even if each 1 penny component of the difference between poverty and wealth is not a significant difference, that doesn't mean that the complete difference, the series of 1 penny differences, is not a significant difference. So that's why this is a fallacy, right? These arguments, which we'll call conceptual slippery slope arguments, are arguments in which the premises could all be true. There are many conceptual slippery slope arguments in which the premises are all true, but the premises don't support the conclusion. And what makes the argument tempting is the vagueness of the category that the argument makes use of, the category of tall, the category of poor, whatever category it is that the argument makes use of. If it's a vague category, then you can construct a conceptual slippery slope argument that uses that category. In the next lecture, we'll see how vague categories can give rise to other slippery slope arguments as well. In the last lecture, we saw how the phenomenon of vagueness gives rise to a kind of fallacy that we called a conceptual slippery slope. Today, we're going to see how that same phenomenon of vagueness gives rise to another kind of fallacy. This kind of fallacy we're going to call the fairness slippery slope. It's also a kind of slippery slope argument, but it concerns fairness. Okay, so what's a fairness slippery slope argument? Well, here's the definition. A fairness slippery slope argument is one that exploits the vagueness of a category to argue that it's unfair to treat cases that fall into that category differently from cases that don't fall into that category. So, what's an example of that? Here's one example. So, suppose I argue as follows. Premise 1, a person who scores 100% on the exam passes. Right? If any score passes, 100% must pass. So, let's suppose a person who scores 100% on the exam passes. Well, a difference of 0.01% is not a significant difference. Therefore, the argument concludes, it's not fair to fail someone who scores a 10% on the exam. In fact, it's not fair to fail someone who scores a 0% on the exam. Now, how does that thinking go? Well, it goes like this. If a person who scores 100% passes, and there's no significant difference between a person who scores 100% and a person who scores 99.99%, then it's not fair to fail someone who scores 99.99%. But then for the same reason, it's also not going to be fair to fail someone who scores 99.98%. And then, for the same reason, it's not going to be fair to fail someone who scores 99.97%, and so on, all the way down the scale. Right? It can't be fair to fail them because there's no significant difference between that score and a score that's 0.01% higher. So that's a fairness slippery slope argument. Now, why is this a fallacy? Well, it's a fallacy because it assumes that it can't be fair to fail someone whose score is not significantly different from a passing score. Right? If a score of 70% is passing, then, by premise 2, a score of 69.99% is not significantly different from that, but it doesn't follow, just because 69.99% is not significantly different from 70%, it doesn't follow that it's not fair to fail someone who got a 69.99%. It could perfectly well be fair to fail them, for all the two premises say. Right? Fairness doesn't necessarily go with significant differences. It could go, let's say, with predictable differences. Right? If I tell you in advance that the minimum score for passing the test is 70%, then even though there's not a significant difference between 69.99% and 70%, still, you knew in advance that 70% was the minimum score for passing the test. So if you get a 69.99%, it might be fair to fail you, even though that score is not significantly different from 70%. Okay, so that's why fairness slippery slope arguments are fallacies. They're fallacies because they assume something that might not be true, which is that it can't be fair to fail someone who has a score that's not significantly different from a passing score. So that's why these are fallacies. Let's look at another example. So premise 1, a 9-month-old human fetus, let's say a human fetus that's almost to its due date, or maybe on its due date, has a right to live. I think we might all agree with that. Premise 2, a difference of 1 minute of prenatal development is not a significant difference. We might all agree with that too. Conclusion of this fairness slippery slope argument, it's not fair to deny a fertilized egg the right to live. Okay, but once again, that doesn't follow from the premises, right? I'm not saying it's not true. The conclusion of that argument might, for all I'm going to say today, might very well be true. My point is not whether it's true or false. My point is that the conclusion is not supported by the premises. And the reason it's not supported by the premises is because this argument assumes, again, that it can't be fair to deny a prenatal life the right to live if it's not significantly different from a prenatal life that does have the right to live. Again, it assumes that differences in fair treatment have to be significant differences. And again, that might very well not be true. So that's why this is a fairness slippery slope argument. That's why this is a fallacy. Okay, now let me say in general, when someone gives a fairness slippery slope argument in ordinary life, they usually don't lay it out in the way that I'm laying out these arguments. Usually what they do is say something like, well, where do you draw the line? Where that question is not understood so much as a sincere question as rather a pointed question. It's a question they're asking of which is simply an attempt to make a point. They're simply trying to make a point that there's no reasonable way to draw a line that needs to be drawn. So in asking that question, someone is in effect assuming that because little differences are not significant, it can't be fair to treat those slightly different cases, those insignificantly different cases, differently. So when you hear someone ask, where do you draw the line? Often you should beware, because a fairness slippery slope fallacy might be lurking in the midst. Okay, see you next time. In the last two lectures, we saw how the phenomenon of vagueness gives rise to a couple different kinds of fallacy, the conceptual slippery slope fallacy and the fairness slippery slope fallacy. Today, I'd like to describe another kind of fallacy that arises because of the phenomenon of vagueness. We're going to call this the causal slippery slope fallacy. So, what's a causal slippery slope fallacy? Well, here's the definition. Causal slippery slope fallacy, or causal slippery slope argument, right, because all fallacies are arguments. A causal slippery slope argument is one that exploits the vagueness of a category to argue that a particular event that you're considering, maybe a course of action that you're considering performing, or maybe just an event that you're imagining. A particular event will lead to a calamity that's causally connected to that event by a series of steps. So sometimes this is called a domino argument. Sometimes it's called a parade of horrors. The idea is there's a series of steps that eventually leads to some calamity. And so we should cut off that series of steps before it begins. We should prevent it from ever beginning, because if we allow it to begin, then it'll eventually lead to some calamity. That's the form that a causal slippery slope argument takes. So what are some examples of causal slippery slope arguments, and why are they fallacies? Well, here's some examples. So consider this. Premise one, if we let doctors euthanize patients under any circumstances whatsoever, it's likely, not certain, but likely, that we'll eventually let doctors kill patients who are depressed or in severe pain, independently of whether or not their condition is terminal or hopeless. Premise two, if we let doctors kill patients who are depressed or in severe pain, then it's very likely that we'll eventually let doctors kill patients who are a nuisance. Premise three, doctors should not be allowed to kill patients who are a nuisance, right? Simply being a nuisance shouldn't license a doctor to kill you. In conclusion, doctors should not be allowed to euthanize patients. Okay, so there's a causal slippery slope argument. What it tells us is that if we allow euthanasia, then that's going to have a certain likely consequence, which in turn would itself have a certain consequence, which would be unacceptable. So we shouldn't allow euthanasia because of the indirect consequences of allowing euthanasia. Now, why is that not a good argument? Why is that a fallacy? Here's why it's a fallacy. Just because one event is likely to have a certain result, and that result is likely itself to have a certain result, it doesn't follow that the first event is likely to have that last result. Right? Consider this example. Suppose that dating leads to marriage with a 66% probability. Right? 66%, I'm just making this up obviously, but let's suppose that 66% of couples who date end up getting married. Now let's suppose that 66% of married couples get divorced. And let's suppose that 66% of divorced couples end up not being on speaking terms with each other. Okay, so it's likely that if you're dating, you'll get married. It's likely that if you get married, you'll get divorced. And it's likely that if you get divorced, then you won't be on speaking terms with each other. Let's suppose. Does it follow from that it's likely that if you're dating, then eventually you won't be on speaking terms with each other? From the premises I just gave, it doesn't follow from the fact that you're dating right now that you'll eventually end up not being on speaking terms with each other. It doesn't even follow that it's likely that you'll end up not being on speaking terms with each other. Right? Just because each event in the chain is likely given the one before it, it doesn't mean that the last event in the chain is likely given the first event in the chain, because the probability could reduce at each point in the chain. And if the probability reduces just a couple times, it could go from something could go from being likely to being unlikely. Here's another example of a causal slippery slope argument. Okay, let's suppose I say, premise one, if we allow the distribution of birth control in colleges, then it's likely that we will allow it in high schools, eventually. Premise two, if we allow the distribution of birth control in high schools, then it's likely that eventually we'll allow it in elementary schools. Premise three, we should not allow the distribution of birth control in elementary schools. Conclusion, we should not allow the distribution of birth control in colleges. Now again, why is that a fallacy? Why don't the premises support the conclusion? Just because each step in that series is likely given the preceding step, it doesn't follow that the last step in the series is likely given the first step in the series. In other words, just because it's likely that we'll allow distribution of birth control in high schools given that we allow it in colleges, and it's likely that we'll allow it in elementary schools given that we allow it in high schools, it doesn't follow from that that it's likely that we'll allow it in elementary schools given that we allow it in colleges. Likelihood is not transitive in that way. That's why causal slippery slope arguments are fallacies. That doesn't mean that their conclusions are never true. Their conclusions could well be true, but again, what we're talking about here is whether or not a causal slippery slope argument gives good support for its conclusion. And the point I'm making today is that it doesn't. A causal slippery slope argument, while it might be arguing for a true conclusion, doesn't give a good reason for accepting that conclusion. Okay, so that wraps up the topic of vagueness and the fallacies to which vagueness gives rise. In the next lecture, we'll talk about a different phenomenon, something that we call ambiguity, and we'll consider the fallacies to which ambiguity gives rise. See you next time. Today, we're going to talk about the phenomenon of ambiguity and how that phenomenon, like the phenomenon of vagueness, can give rise to fallacies. Okay, so first, what's ambiguity? Well, here's a definition, along with some examples. Ambiguity is when an expression has more than one acceptable interpretation, more than one correct interpretation. So, some examples of this. There are cases where a single word has more than one correct interpretation. So consider the word bank. In English, a bank could be a financial institution, an institution in which you can deposit money, invest money, on which you can write checks and so forth. Or a bank could be the edge of a river bank. Consider the word cardinal. Cardinals are members of the papal hierarchy. They're below the pope, but they're higher than priests. So that's one interpretation of cardinal, but there's another interpretation of cardinal. Well, actually, there are several other interpretations of cardinal. A cardinal could be a kind of red finch, a particular kind of bird. A cardinal could also be a St. Louis baseball player, a player for the St. Louis baseball team. And there's also a use of cardinal as an adjective, not as a noun. These are examples of single words that have more than one acceptable interpretation in English. But sometimes you have a whole phrase or a sentence that has more than one acceptable interpretation. So for instance, consider the sentence, "She is an Asian historian." Well, there are two perfectly good interpretations of that sentence, depending on the situation in which it's used. It might be saying that she is an Asian person who is a historian, or it might be saying that she's a historian of Asian history. She studies the history of Asia. Consider the sentence, "Police kill man with axe." Well, there are at least two different ways of understanding that sentence. It could be understood as saying that there's this man with an axe and the police killed him, or it could be understood as saying that the police killed that man and they killed him by using an axe. Again, two acceptable but very different interpretations of the same sentence. Okay. So why does this phenomenon of ambiguity, which I should stress is very widespread, not just in English, but in every spoken language, why does this phenomenon of ambiguity give rise to fallacies? Here's why. If an expression has two acceptable interpretations, and we switch between those two interpretations in the course of a single argument, we switch between them mid-argument, then we can construct an argument that might seem valid, but it isn't valid. Let me give you some examples to illustrate this possibility. So here's one example. Suppose I reason as follows. Well, Jones, I'm told, was sentenced to 9 years in the violin case. Now you might think, well, our criminal justice system is not supposed to sentence anyone to spend time inside a violin case, and therefore Jones's sentencing was a breach of justice. What's very likely to be going on in this example is that the interpretation of sentence to 9 years in the violin case is different in the first premise than it is in the second premise. In the first premise, when I say Jones, I'm told, was sentenced to 9 years in the violin case, I don't mean that Jones was sentenced to spend time inside the violin case. I mean that Jones was sentenced to spend 9 years in prison, and he was sentenced to do that in a particular criminal case that I'm referring to as the violin case. Maybe it was a case in which an expensive violin was stolen, and it was stolen through armed robbery, and Jones was found guilty of armed robbery of the violin and then sentenced to spend 9 years in prison. So that's what I probably mean when I say something like premise 1. But premise 2 interprets the phrase sentenced to 9 years in the violin case in another way. It interprets that phrase as saying Jones was sentenced to spend 9 years of his life inside a violin case. Okay, now clearly premise 1, when properly understood, could very well be true, and premise 2, when properly understood, could very well be true. But the reason the conclusion doesn't follow from those two premises, the reason this is a fallacy, is because the correct understanding of sentenced to spend 9 years in the violin case in premise 1 is different from the correct understanding of that same phrase in premise 2. So premise 1 and premise 2 together don't imply anything about Jones's sentencing being a breach of justice or being a violation of the rules of our criminal justice system. That phrase means something different in the two premises. So that's why we have a fallacy here. Superficially, the argument might look valid, but actually it's a fallacy. It's not a valid argument. Here's another example. Suppose I say, Amelia Bedelia was told to dress the chicken for dinner. Right? Those of you who are familiar with the Amelia Bedelia stories, these are children's stories about a servant who's given a set of instructions and interprets them all differently than the way they're intended. So one of her instructions was to dress the chicken for dinner. And clearly, the woman who told Amelia Bedelia to dress the chicken for dinner was understanding the word dress in a particular way, such that it's a way of preparing a chicken to be cooked for dinner. Well, Amelia Bedelia hears the instructions and then goes off looking for some dinner clothes that are just small enough to fit the chicken. And turns out she can't find dinner clothes that are small enough to fit the chicken. Right? Their family just doesn't have dinner clothes that are that small in their house. So Amelia Bedelia could not find dinner attire small enough to fit the chicken. So you might conclude from those two premises that Amelia Bedelia was not able to do as she was told. She wasn't given the resources to follow her instructions. But that's false. What happened is that Amelia Bedelia misunderstood the instructions. The instructions were intended to be understood in one way, and Amelia Bedelia understood them in a different way. And so, while this argument might superficially appear to be valid, in fact, it isn't valid at all. Again, this argument trades on an ambiguity in the phrase dress. Dress the chicken for dinner. Right? There's two possible interpretations of that phrase. The instructions that Amelia Bedelia was given had one interpretation that was correct, but Amelia Bedelia's understanding of those instructions relied on the alternative interpretation, the interpretation that was incorrect. And so it seems to Amelia Bedelia as if she couldn't carry out her instructions, but that's because she misunderstood the instructions. She gave them one interpretation when they were supposed to have the other. Okay, so these are some examples of ambiguity and how ambiguity can give rise to fallacies. In the next lecture, we'll talk about a couple different kinds of ambiguity, and we'll look at examples of each of those kinds. See you next time. Today, I want to talk about two different kinds of ambiguity, and I want to explain how each of these different kinds of ambiguity can give rise to fallacies. I call them semantic and syntactic ambiguity. So what are these two different kinds of ambiguity? Let's look at some examples. So here are examples of semantic ambiguity. Semantic ambiguity is when a particular word has two different interpretations. The two different interpretations are two different interpretations of that one word. So, one example is, consider the newspaper headline, Gandhi stoned in rally in India. Well, there are two different interpretations of the verb stoned, right? One interpretation is people threw stones at Gandhi at the rally in India. Another interpretation is Gandhi was using illicit drugs at the rally in India. So those are two different interpretations of the word stoned, and they give rise to two different interpretations of what someone is saying when they say Gandhi stoned in rally in India. Consider the sentence, Iraqi head seeks arms. Okay, that sentence actually has two words that are ambiguous. There's the word head and there's the word arms. Head could be interpreted to mean a part of the body, right, the head, or it could be understood to mean part of the body politic, right, the head of the body politic, the Iraqi president, or the head of state, or the head of their defense department, or their military department, but the head of some organization. That's to say, the leader of some organization. So the word head could be interpreted to mean the leader of some organization. It could also be understood to mean the head, the top of the body. Arms. Well, arms, of course, could be understood to mean arms, right, these appendages, or they could be understood to mean weapons. So that sentence has two words, each of which is semantically ambiguous. And then there's the sentence, Meredith is in a terrible state. Well, of course you might mean, when you say Meredith is in a terrible state, you might mean she's in a terrible psychological state. She's very depressed, she's very upset, she's very angry. Or you might mean that she's in a state, like one of the United States or one of the states of some other country, but she's in a state which is a terrible state. We don't need to name those. Okay, so these are examples of sentences that contain semantic ambiguity, semantically ambiguous expressions. Let's see how some of these give rise to fallacies. So consider this argument. Premise 1, Gandhi stoned in rally in India. Premise 2, drug users are not qualified to lead. Conclusion, Gandhi not qualified to lead. Okay, now superficially that might look like a valid argument, right? Gandhi falls into a certain category, stoned in the rally in India. People who fall into that category are not qualified to lead, so Gandhi's not qualified to lead. But here's the thing. That first premise as I said just a moment ago, has two acceptable interpretations. It could be understood as meaning people threw stones at Gandhi in the rally in India, or it could mean Gandhi was using illicit drugs at the rally in India. Now, if it means the second thing, then this argument is valid. Gandhi is not qualified to lead, at least given the truth of the two premises. And I'm not going to comment on the truth or falsehood of the second premise. But the most plausible interpretation of that first premise is not that Gandhi was using illicit drugs at the rally in India, it's that people threw stones at Gandhi at the rally in India. And so, on that interpretation, just because people threw stones at Gandhi at the rally in India, that doesn't mean Gandhi was using drugs. And so it doesn't mean that Gandhi falls into the category that the second premise is talking about. And so on that interpretation of premise one, the argument is not valid. It's a fallacy. Okay, so there's an example of how the semantic ambiguity of the expression stoned can give rise to a fallacy, right? An argument that superficially seems valid, but it seems that way superficially only because we're assigning the wrong interpretation to the word stoned. Okay, here's another example of how semantic ambiguity can give rise to a fallacy. So consider this argument. Meredith is in a terrible state. Meredith is in Texas. Therefore, Texas is a terrible state. Okay. Now, apart from the question of whether or not the conclusion is true, I'd like you to notice that if the first premise is understood as it most plausibly is understood, as meaning that Meredith is in a terrible psychological state, let's say she's depressed, or she's very anxious, or she's upset, if that's the correct way to understand the first premise, then the argument is a fallacy. I mean, superficially, it might seem valid. Meredith is in a terrible state. Meredith is in Texas, so Texas must be a terrible state. Well, superficially, that might seem valid, but it seems that way only because we're relying on one interpretation of the phrase state, terrible state. The correct way to understand premise one is on the other interpretation, the interpretation according to which a terrible state is a terrible psychological state, not a terrible political or geographical state. So when we say Meredith is in a terrible state, we're just saying that she's in a terrible psychological state. So from the fact that Meredith is in a terrible psychological state and the fact that she's in Texas, we can't infer anything about whether or not Texas, the state of Texas, is a terrible state. Nothing follows. Okay, so those are some examples of how semantic ambiguity gives rise to fallacies. Now, I said there was another kind of ambiguity, syntactic ambiguity. So what's that, and how does it give rise to fallacies? Syntactic ambiguity is when you have a phrase that can be given two different interpretations where the two different interpretations differ in the grammar, in what grammatical categories are assigned to different parts of that phrase. So let me give you some examples to illustrate the idea. Consider the sentence, the government asks us to save soap and waste paper. Right? Clearly, there are two different interpretations of that sentence. It might be saying that the government asks us to save two things, soap and waste paper, or it might be understood as saying that the government is asking us to do two things. First, to save soap, and secondly, to waste paper. Those are two different interpretations, and they differ not in the meaning of any particular word, they differ in how you're supposed to understand the nature of the government's request. Is the government asking us to do two things, one involving saving and one involving wasting? Or is the government asking us to do one thing involving saving, but saving two different kinds of things, soap and waste paper? So that's an example of syntactic ambiguity. Here's another example. Tuna biting off Washington coast. Again, there are two different ways to interpret this sentence. You can interpret it, perhaps most plausibly, as saying to fishermen, look, if you're interested in fishing for tuna, you should fish off the Washington coast, because if you fish off the Washington coast, you'll find that the tuna there are biting. Right? So you'll be able to catch tuna if you fish off the Washington coast. Another interpretation of that same sentence, somewhat less plausible, is to say that the tuna are biting off the Washington coast. The Washington coast is itself disappearing as the tuna bite it off. Right? And those two different interpretations differ according to whether biting is understood as a verb or biting off is understood as a verb phrase that relates tuna to the Washington coast. Okay. Finally, consider this example. Police can't stop gambling. Okay, there are two different ways of understanding this sentence. Again, two different correct interpretations, two different possible interpretations. One is a saying that there's gambling taking place and the police just can't stop it. No matter what the police do, the gambling will continue to take place because the gamblers are gambling in hidden places where the police can't find them, or the gamblers are gambling in places where the police don't have a warrant to search, but the gambling is going on and the police just can't do anything to stop it. Or the sentence could be understood as saying, the police themselves are gambling and they just can't stop. No matter how hard they try, they can't stop themselves from gambling. Okay. Two different interpretations of the sentence, police can't stop gambling. Now notice how these examples of syntactic ambiguity can give rise to fallacies. Let's consider some examples. So, consider the following argument. Police can't stop gambling. Anyone who can't stop gambling needs therapy. Therefore, the police need therapy. Now, superficially, this argument might look valid. Right? It might seem to be saying the police fall into this category of people who can't stop gambling, and anyone who falls into that category needs therapy, so the police need therapy. But that's relying on one interpretation of the sentence, the police can't stop gambling, and that's not the interpretation that's probably correct. The interpretation that's probably correct is that gambling is going on and the police can't do anything to stop it from going on. And if that's the correct interpretation of premise one, then the argument is invalid. The argument is a fallacy, right? That fact that the police can't stop gambling from going on, and that anyone who can't stop themselves from gambling needs therapy, from those two premises, that doesn't support the conclusion that the police need therapy, right? It might support the conclusion that the inveterate gamblers that the police can't stop from gambling need therapy, but it doesn't support the conclusion that the police need therapy. So that's an example of how the syntactic ambiguity in the sentence, police can't stop gambling, can give rise to a fallacy. Here's another example. Consider, premise one, the government asks us to save soap and waste paper. Premise two, it's wrong to waste recyclable resources like paper. So conclusion, the government's request is unreasonable. Okay, now superficially, again, this argument might appear to be valid because it might appear that, well, the government is asking us to do a couple of different things and it's wrong to do one of those two things, so the government's request is unreasonable. But that interpretation of premise one, according to which the government is asking us to do a couple of different things, like saving soap and wasting paper, that's not the most likely interpretation of that premise. The most likely interpretation of that premise is an interpretation according to which it's saying that the government is asking us to do one thing, to save, but it's asking us to save a couple different things, soap and waste paper. And then, from the fact that the government is asking us to save waste paper, and that it's wrong to waste recyclable resources like paper, well, it doesn't follow at all that the government's request is unreasonable. And those two premises don't at all support the conclusion. And so, given the most likely interpretation of premise one, this is a fallacy. This is a bad argument. It's a bad argument, but superficially it might seem like a good argument, again, because of the syntactic ambiguity in the phrase, save soap and waste paper. Okay, so those are some examples to illustrate how semantic ambiguity and syntactic ambiguity can each give rise to fallacies. In the last couple of lectures, we've been talking about the phenomena of ambiguity, semantic ambiguity, and syntactic ambiguity. And we've shown how these phenomena can give rise to fallacies. Well, the fallacies to which ambiguities give rise are what we'll call fallacies of equivocation. Today we're going to talk about fallacies of equivocation. So, what's a fallacy of equivocation? Well, here's how we define it. A fallacy of equivocation is a fallacy that results when an argument appears to be valid only because it switches between two different interpretations of an ambiguous expression. Right? So, a fallacy of equivocation, since it's a fallacy, it can't be valid, but it appears to be valid, and it appears that way only because it switches between the two different interpretations. Okay, so we've already seen a bunch of examples. Today, I just want to present a couple more examples of fallacies of equivocation. So here's one. Consider this argument. 6 is an odd number of legs for a horse. That's true. Horses typically have 4 legs. Odd numbers cannot be divided by 2. That's true also. That's just the definition of an odd number. 3, 5, 7, 9, 11. These are all odd numbers because they can't be divided by 2. Therefore, the argument concludes, 6 cannot be divided by 2. Okay. That's a fallacy. It might appear to be valid because when you look at the first premise and it says 6 is an odd number of legs for a horse, you might think, oh, well, that means 6 is an odd number, right? Because it's an odd number of legs for a horse, which means it's an odd number of legs, which means it's an odd number. And since odd numbers can't be divided by 2, you might think you can conclude that 6 cannot be divided by 2. But of course, that's wrong. That conclusion is false, and it's not supported by the premises when properly understood. When the first premise says 6 is an odd number of legs for a horse, that doesn't imply 6 is an odd number. The correct interpretation of odd number as it occurs in the first premise is different from the correct interpretation of odd number as it occurs in the second premise. The phrase odd number can have a couple different interpretations. On one interpretation, it means a number that's not divisible by 2. On the other interpretation, it means an unusual number. This argument appears to be valid only because it switches between those two interpretations from premise 1 to premise 2. 6 is an unusual number of legs for a horse, and of course, odd numbers, numbers that are not divisible by 2, of course, by definition, can't be divided by 2, but it doesn't follow that 6 can't be divided by 2. 6 is an odd number in the first sense of being an unusual number of legs for a horse, but it's not an odd number in the second sense. It's not an odd number in the sense of a number that's not divisible by 2. So that's an example of a fallacy of equivocation. Here's another example. Man is the only rational animal. I believe it was Aristotle who said the ancient Greek equivalent of that. No woman is a man. That seems true. Therefore, no woman is a rational animal. Okay, now, superficially, it might look like that argument is valid. But in fact, that's a fallacy. That's not a valid argument. Why? Well, because the expression man can be given two different interpretations, and this argument switches between those two different interpretations. Right? So, on one interpretation of man, it just means an adult male human. And on that interpretation, it's true that no woman is a man. Premise 2 is true when the word man is understood that way, is given that interpretation as just adult male human. But sometimes the word man is used more generally to mean human being. And when it's used that way, while premise 1 might be true, premise 2 certainly isn't true. It certainly isn't true that no woman is a human being. All women are human beings. So, while premise 1 might be true on that more general interpretation of the word man, premise 2 is not true on that more general interpretation of the word man. So, the reason this argument is a fallacy is because there's no single interpretation of the word man on which premise 1 and premise 2 could possibly both be true. right? There are two interpretations of the word man. On one of those interpretations, premise 1 might be true. On the other of those interpretations, premise 2 is true, but there's no interpretation on which both premise 1 and premise 2 could possibly be true. And by the way, I should mention, for those who use the word man to mean something very general like human being, that they would then have to feel comfortable saying things like, man nurses his young for up to 2 years, or man gestates his fetuses for 9 months. I wonder. Anyhow, so those are examples of some fallacies of equivocation. Next week, we'll be talking about very different sorts of fallacies, fallacies of relevance. See you next week. Welcome to week 10 of our course. In this week, we'll be studying fallacies of relevance and vacuity. Now, before I say what fallacies of relevance and vacuity are, let me make an important distinction between the fallacies of relevance and vacuity that we'll be studying this week and the fallacies of vagueness and ambiguity that we studied last week. The important distinction that I have in mind is this. Fallacies of vagueness and ambiguity are very hard to avoid, whereas fallacies of relevance and vacuity are quite easy to avoid once you recognize what they are. The reason that fallacies of vagueness and ambiguity are very hard to avoid is because it's very easy to make those fallacies given the pervasiveness of vagueness and ambiguity in the language that we speak. Now you might think, well, but why should there be vagueness and ambiguity in the language that we speak? I mean, why don't we just speak a language that does away with vagueness and ambiguity? In fact, there are a lot of communities that try to purge their technical language of vagueness and ambiguity. Like in scientific communities, they might try to use a language that doesn't have the same amount of vagueness and ambiguity that we have in ordinary language. But why don't we purge vagueness and ambiguity from ordinary language? Is it just a bother to purge ordinary language of vagueness and ambiguity, and that's why we don't do it? Well, no, I think there's actually a deeper reason. I think there's a reason why it's important for ordinary language to have vagueness and ambiguity in it. And as long as ordinary language does have vagueness and ambiguity in it, it's going to be very hard for us to get rid of fallacies of vagueness and ambiguity. We can do it, but we have to keep a watchful eye out for cases where we're using phrases that are ambiguous or vague in our arguments. Okay, so why is it important for ordinary language to have expressions that are vague or ambiguous? Well, let me give you some examples. Suppose we're planning a vacation, and we're planning a vacation to an island in the Caribbean. Let's say Jamaica. And we're trying to figure out when the best time would be to go. And we think, well, we don't want to go in the summertime because it'll be too hot there. We want to go in the wintertime because then we get maximum relief from the cold that we experience where we live right now. So let's say we decide, okay, we want to go to Jamaica in the wintertime. Okay, fine, in the wintertime. But when in the wintertime is the best time to go? Well, it's going to depend on a number of things. It's going to depend on exactly when the kids have vacation from school. It's going to depend on exactly when our workload is going to be the lightest at work. It's going to depend on when we save up the money for the vacation. So we have to think about when would be the best time in the wintertime to go. But if you ask us, do we have any plans for travel? Well, we could say, yeah, we plan to go to Jamaica this winter. Well, when this winter, you might want to know? December 24th or December 28th or December 31st? When? Well, we might say we don't know exactly when, but sometime this winter. Okay, now our answer to you is vague. We say sometime this winter. Not clear exactly when. Well, you might say, okay, but even that could be made precise. You could say, well, we plan to travel to Jamaica between the following dates, December 21st and March 21st. Well, but our plans aren't even that precise, because maybe when we look at all the availability, it'll turn out that March 22nd is the best day to go. Or maybe March 23rd, or maybe December 20th. Right? So we can't even make our plans as precise as all that. So if we're going to answer your question, we have to give you a vague answer. We can't give you a precise answer. We could try to give you a precise answer in probabilistic terms. We could say, well, there's a high probability that will go in January or February, there's a lower probability that will go in December or March, and there's a very low probability that will go in early December or late March. But wait a second. Even there, our answer wasn't precise. We were talking about a high probability, a lower probability. What exactly counts as a high probability? Is it a probability greater than 50%? So it's hard for us to answer your question with any precision. So if we can't answer your question with any precision, should we just remain completely uninformative? And when you ask, do we have any plans for travel, we should just say, we don't know. Well, that seems unhelpful. It seems much more helpful to give you a vague answer. Yeah, we're planning to go to Jamaica sometime this winter. That's much more helpful than giving you a response of the form, we don't know. Or, of course, we could just make up a precise answer and say, yes, we plan to go to Jamaica on December 28th, but then we'd be lying, because we have no idea whether or not we plan to go to Jamaica on December 28th. Or if not lying, in any case, we'd be saying something that we haven't the foggiest idea whether or not it's true. So, in order for us to answer your question helpfully, we have to give a vague answer. And that's just one example out of many I could have produced of a case where, in order to be conversationally cooperative, we have to say something vague. So vagueness is important to ordinary language. So is ambiguity, because one of the ways that we generate ambiguity is through metaphor and through figurative language generally. If I say, the White House said today that the conflict in Afghanistan is expected to decrease over the next 12 months. Well, you might say, what do I mean the White House said? Does the White House have any organ that allows it to speak? No, the White House is just a building. Buildings can't speak. Well, sure, you could say buildings can't speak, but when I say the White House said, I meant a particular office said. Oh wait, you might object, an office said? What do you mean, a room with walls and a ceiling said something? Well, no. A room with walls and a ceiling didn't say something, but a particular person or group of people who work in that room with walls and a ceiling said something. Oh, which people were those? Well, I don't know. I don't know if it was President Obama who said it, or if it was his White House press spokesperson, or if it was some other member of the administration. But I don't need to know in order to answer your question helpfully when I say the White House said it. So, there I'm using the phrase the White House in a different sense than it's literally intended, right? The literal meaning of the White House is to refer to a particular building. Now I'm using the phrase the White House to refer to a particular group of people who said something, but I can't be any more specific than that. I don't know which among those people said it, so I just say the White House said it. Okay, so these are examples of how vagueness and ambiguity are actually useful to ordinary language. They're useful to the language that we speak in day-to-day life. So we can't get rid of them, and we shouldn't get rid of them. They're useful. But the problem is, as long as they exist in ordinary language, it's going to be very easy to make fallacies of vagueness and ambiguity. And so we're going to have to look out for such fallacies when they occur. Now, the fallacies that we'll be talking about this week, fallacies of relevance and vacuity, they are not like that. Fallacies of relevance and vacuity are much easier to root out once we know what they are. There's nothing about our ordinary language that tempts us into making fallacies of relevance and vacuity. Once we've identified what they are, we should be able to eliminate them. So what are fallacies of relevance and vacuity? Well, I'll start out today by giving you some definitions, and then in subsequent lectures, we'll talk about particular examples. So, fallacies of relevance and vacuity. First, what's a fallacy of relevance? A fallacy of relevance is a fallacy that results when an argument's premises are not relevant at all to supporting its conclusion. Now, examples of these sorts of fallacies are what we're going to call ad hominem arguments, appeals to authority, and appeals to popular opinion. And we're going to be discussing all of those in subsequent lectures. What's an example of a fallacy of vacuity? Well, first let me give you a definition. Fallacy of vacuity is a fallacy that results when you can't be justified in accepting the premises of an argument unless you're already independently justified in accepting the conclusion. So in other words, even if the argument is sound, the premises can't give you a good reason for accepting the conclusion because you already have to have a good reason for accepting the conclusion in order to accept the premises in the first place. And examples of those are what we're going to call circularity, begging the question, and self-sealing. And again, in subsequent lectures, we'll look at examples of all of those. Okay, see you next time. Today we're going to talk about a particular kind of fallacy of relevance known as an ad hominem argument. Now, those of you who know Latin will know that ad hominem means to the person. But what kind of a fallacy is an ad hominem fallacy? Well, as is suggested by the name, an ad hominem fallacy is one that begins with premises about a particular person who's making an argument and ends with a conclusion that's critical of that person's argument. It's critical of that person's argument solely on the basis of premises having to do with that person, him or herself. I'll give you a simple example to show you what I mean. So suppose Takahashi has just given an eloquent presentation of some evidence that normalizing U.S. relations with Cuba would result in massive benefit to both nations. Both the United States and Cuba would be much better off if relations between the two countries were normalized. Okay, now, you might argue as follows. Well, Takahashi has just given this eloquent presentation, but Takahashi owns a cigar import business which stands to profit from the normalization of relations between the U.S. and Cuba. Therefore, we should disregard Takahashi's presentation. Okay, now that's an example of an ad hominem argument, right? You're arguing from a premise about Takahashi, him or herself, right, that she stands to profit from normalization of relations, to the conclusion that whatever evidence was given in her presentation, we just shouldn't listen to it. We shouldn't bother with that evidence, because after all, Takahashi stands to profit. Okay, that's an example of an ad hominem argument. Now, there are three kinds of ad hominem argument that I think it's worth distinguishing. And those three kinds of ad hominem argument correspond to three different things that a person is doing whenever they give an argument. Let's think about what you're doing when you give an argument. Well, when you give an argument, let's say when you give an argument to a particular audience, right, you're trying to persuade them of something. First of all, your behavior implies that you're entitled to put forth claims about the issue in question, right? So if I give an argument, let's say I give an argument to the effect that housing prices in the southeastern states in the United States are going to rise by over 10% over the coming year. Well, one thing I'm doing when I give that argument is implying by my behavior that I'm entitled to have an opinion about that. I'm entitled to put forth claims about that. I have whatever knowledge it would take to be in a position to put forth claims about that. Right? If I'm completely ignorant about the housing market and its vicissitudes, then I shouldn't be making any such claims at all. If I'm completely ignorant about the vicissitudes of the housing market, then I'm in no position to be making any such argument. So one thing I'm doing when I make an argument is that I'm implying that I'm entitled to put forth claims about the issue in question. The second thing I'm doing when I make an argument is implying that certain premises, namely the premises that I'm giving in my argument, support the conclusion that I'm offering. Right? That the premises that I'm giving are true and bear some relation of support to that conclusion. Maybe the argument from those premises to that conclusion is a valid argument, maybe it's just a probabilistically strong argument, but in any case, the premises offer some support for the conclusion. That's another thing I'm implying when I give the argument. And then, of course, the third thing is I'm claiming the conclusion is true. So those are three things that I'm doing whenever I give any argument, whenever I try to prove any point. I'm doing at least those three things. And corresponding to each one of those three things, there's a kind of ad hominem argument that denies that I've successfully executed that thing. Okay, so let's look at the three kind of ad hominem arguments corresponding to these three things that I'm doing whenever I give an argument. Okay, so the first kind of ad hominem argument is what I call a silencer. That's an argument that begins with some premises about a person who's making a point, giving an argument, and ends with a conclusion to the effect that we should disregard that person's argument altogether. It's not that the person's argument is valid or invalid or that their conclusion is true or false or what. Just we shouldn't pay any attention at all, right? Because the person isn't entitled to give any argument on this issue. So we shouldn't even worry about whether their argument is valid or invalid or whether their conclusion is true or not because the person isn't entitled to speak on the issue. That's what a silencer argument does. Okay? So a silencer argument basically denies that it really is entitled to put forth claims about the issue, that they really have successfully executed what they would have to have done in order for one to be true. Okay. A second kind of ad hominem argument is called a dismisser. A dismisser begins with premises about a particular person who's making a point or giving an argument, and ends with a conclusion to the effect that that person's reasons, the reasons they're giving in defense of that point, are not good reasons. A dismisser doesn't say that the conclusion of their argument is false. A dismisser just says their reasons are no good. So don't pay any attention to their argument because the premises given in support of their conclusion don't actually support their conclusion. Maybe the premises are false or maybe they're just irrelevant to the conclusion, but don't pay any attention because, after all, their conclusion, whether true or false, is unsupported by their argument. So that's what a dismisser does. A dismisser, in short, is an argument to the effect that the person that you're attacking hasn't successfully executed task 2 that they have to perform whenever giving an argument. They might imply that certain premises support a conclusion on the issue, but they're wrong. Those premises don't actually support that conclusion. Maybe because they're false or maybe because they're irrelevant to the conclusion. Okay. Finally, the third kind of ad hominem argument is called a denier. Now, a denier is an argument that begins with some premises about a particular person who's making a point and ends with a conclusion that denies the conclusion of that other person's argument. In other words, whatever you have to say about their entitlement to speak on the issue, whatever you have to say about the truth of their premises or the relevance of their premises, a denier claims that the conclusion that they reach is false. So a denier says that the person hasn't successfully executed task 3 that's associated with giving an argument. They claim that the conclusion is true, but their claim is wrong. Okay, so those are the three kind of ad hominem arguments corresponding to the three things that a person is doing whenever they're giving an argument. Next time, we're going to look in more detail at each of those kinds of ad hominem arguments. In particular, next time, we'll examine silencer arguments, and then we'll look at dismissers and deniers. See you next time. In the last class, we talked about ad hominem arguments, and we distinguished three varieties of ad hominem arguments. Today, we're going to talk about the first variety of those three, the variety that we call silencers. Now, I should point out that while ad hominem arguments are typically fallacies, not all of them are fallacies. And the same holds true of silencers. While silencers are typically fallacies, not all of them are fallacies. So what I'm going to do today is first give a definition of silencers, then give some examples of silencers that are not fallacies, and finally we'll talk about silencers that are fallacies, which are the most common kind of silencers. Okay, so first, what's a silencer? Well, a silencer is an ad hominem argument that begins with some premises about a particular person who's making a point, and it ends with a conclusion to the effect that we should disregard that person's argument altogether. The conclusion is not the person's argument is an argument for a false conclusion, or their premises are false, or their premises don't support their conclusion. The conclusion is just we shouldn't pay any attention to their argument at all. Now, I can give a couple of examples of silencers that are actually good arguments, that are not fallacies. But in order to give these examples, I have to describe environments that tend to operate in a very strictly regulated framework. So I'll start by giving some examples of silencers that are not fallacies, and then we'll look at silencers that are fallacies. So first, here's a silencer that's not a fallacy. So suppose you're in a court of law during a criminal trial, and the accused is on the witness stand. The person who's accused of some heinous crime is on the witness stand. Let's say the accused has been accused of murder. And as always, the defense gets to call some witnesses and the prosecution gets to call some witnesses, and there's a procedure that governs the progress of criminal trials. Right? Criminal trials operate according to a certain procedure. Now suppose that someone bursts into the room, someone who hasn't been called by either the defense or the prosecution, someone bursts into the room and then yells at the top of their lungs, "I saw the accused murder the victim. Therefore, the accused is guilty of the crime with which she is charged." Okay, now, this person who's just burst into the courtroom and presented this argument, this person might be presenting an argument that's sound. Indeed, it might be that the person saw the accused murder the victim. And it might be that the accused is guilty of the crime with which she is charged. So the argument that's being presented by the intruder, the person who bursts into the courtroom, might be a perfectly sound argument. But that doesn't mean we should listen to it. In fact, at least in American criminal trials, it's very likely that the judge would instruct the jury to disregard the outburst in the courtroom, because that has not been presented as evidence by either the prosecution or the defense. Criminal trials have to operate according to a certain procedure. If the procedure is violated, then a mistrial is declared, or there has to be some way of fixing the violation of the procedure. And for someone to just burst into the courtroom, not called there by either the prosecution or the defense, and to yell out that they saw the accused murder the victim and therefore the accused really is guilty of the crime with which she is charged, well, the argument that they're giving might be sound. It might be that the premise is true and the conclusion is true, and of course the premise supports the conclusion, but that doesn't mean we should listen to it. In fact, the jury will very likely be specifically instructed to disregard the outburst. So there's an example of a silencer that is not a fallacy. If I say the outburst was inappropriate and violates the procedure of the criminal trial, therefore we should disregard it. Right? There I'm giving an argument. The argument is a silencer. It starts off with a premise about the person who made the outburst, namely that their making the outburst was in violation of the procedure of the criminal trial, and it ends with a conclusion to the effect that we should disregard their argument. So what I've just given right now is a silencer, but that's a silencer that's actually a good argument. In that context, we should ignore the outburst. Okay, or certainly the jury should ignore the outburst. Okay, so that's an example of a silencer that's not a fallacy. It's a good argument. Here's another example of a silencer that's not a fallacy. So suppose in a particular session of our national legislature, a bill, proposed law is being debated by different legislators. And suppose someone bursts into the legislative assembly and makes the following outburst. This bill will throw millions of working citizens into dire poverty. Any bill that throws millions of working citizens into dire poverty should not be passed into law, and therefore this bill should not be passed into law. Now again, it's possible, let's suppose, that the argument that this person is giving is a sound argument. It's possible that the premises are both true and that the conclusion is true and that the premises support the conclusion. But even if it's a sound argument, given the way legislative sessions are supposed to operate, we shouldn't listen to the argument that this person is given because the way they gave it violates the protocol of legislative sessions. Right? So I might argue as follows. I might say, this person's outburst violates the protocol of our legislative session. Therefore, we must disregard their argument. That's an example of a silencer, and yet it's not a bad argument. It might very well be true, given the rules governing legislative activity, that we do need to disregard this outburst. That doesn't mean that we don't need to think about the considerations that the person adduced. We might need to think about the considerations that the person adduced, but that would be for other reasons than that the person adduced them. So this is an example of a silencer that's actually a good argument. It's a good argument for the conclusion that we should ignore the outburst that the person made into the legislative session. Okay, so now I've given a couple of examples of silencers that are good arguments. But notice, these silencers occur in very special circumstances. Let's say during a criminal trial or during a legislative session, during some occasion that's governed by a bunch of procedural rules and regulations. But ordinary life isn't like that. In ordinary life, our conversations aren't governed by that thick network of procedural rules and regulations. Of course, there are rules and regulations that govern ordinary conversation, rules and regulations concerning etiquette, being reasonably polite and considerate to one another. Those rules and regulations are few enough and far between that we still leave room for people outside our conversation to burst out with consideration. But those regulations are not as many and not as complicated as the rules and regulations that govern legal proceedings and legislative sessions. In ordinary life, when do we encounter silencers? Well, often we encounter silencers of the following form. We'll encounter a silencer to the effect that we shouldn't listen to someone's argument because, after all, that person has a criminal record. Or we shouldn't listen to someone's argument because, after all, that person is a philanderer. Or we shouldn't listen to someone's argument because, after all, we all know what that person is like. That person is just weird. And so we just shouldn't listen to their argument. So often in ordinary life, we encounter silencers that are fallacies. They tell us not to listen to the argument that a person is giving, not because that argument, the act that they performed of giving that argument, violates the strict rules and regulations governing our proceedings. We shouldn't listen to their argument because that person is weird, or that person has some event in their history that should make us look askance at them. Now, those silencers typically are fallacies, and yet those are the kinds of silencers that we find most commonly in everyday life. Okay, so that's our discussion of silencers. Next time, we'll talk about dismissers. See you next time. In the last class, we talked about an ad hominem argument called a silencer. And we said that while there are some silencers that are good arguments, a lot of them that are given in everyday life are bad arguments. They're fallacies. Today I want to talk about another kind of ad hominem argument, an ad hominem argument called a dismisser. I want to say what dismissers are. I want to give some examples of dismissers that actually are pretty good arguments, but then I want to give some examples of dismissers that occur in everyday life that are bad arguments. Okay, so let's start by defining what dismissers are. So, as I said, a dismisser is a kind of ad hominem argument. It begins with premises about a particular person who's making a point, and it ends with a conclusion to the effect that that person's reasons for that point are not good reasons. Right? So a dismisser is not a silencer. It's not saying the person has no right to speak about the issue. It's not saying that we should just disregard anything they have to say about the issue. Fine, they're entitled to speak about the issue. Maybe we should listen to what they have to say about the issue, but we should not regard the reasons that they give as good reasons. That's the point of a dismisser. Now, as I said, there are some dismissers that are good arguments. Let's consider a couple of examples. First, consider the following argument. Right? Let's suppose we've just watched an advertisement in which a coalition of companies in the fossil fuel industry are giving an argument in the ad to the effect that climate change is a hoax. In fact, there's no significant man-made climate change taking place in the environment today. Now, we might argue as follows. Okay, premise: the fossil fuel industry is eager to operate under as little environmental regulation as possible. Right? That's true of all companies that are interested in turning a profit. Conclusion: therefore, any reason that the members of the fossil fuel industry give in support of the conclusion that climate change is a hoax are unlikely to provide strong support for that conclusion. Okay, now that argument, I claim, is a good one. It's a dismisser where you're arguing from the interests of the fossil fuel industry to the conclusion that we should take whatever reasons they give in defense of their conclusion that climate change is a hoax. We should take those reasons with a grain of salt. We should be suspicious of them. Now, of course, that's not to say for a moment that we should simply deny those reasons or deny the conclusion that climate change is a hoax. That's a substantive question. It requires climatological expertise to answer. But while we leave it open as a possibility that the argument being made by members of the fossil fuel industry is in fact a sound argument, we only leave it open as a possibility. We recognize that what's very likely to be true, given their interests, is that the argument that they're making is not a good argument. Possibly it is. We have to investigate. But based on what we know now about the interests of the fossil fuel industry, it very likely is not a good argument. Okay, so let's give another example of a dismisser that's a good argument. Let's suppose the head of a particular bureaucracy is arguing that cuts to that bureaucracy's operating budget would be absolutely devastating. In fact, given the centrality of that bureaucracy's mission, it's in fact crucial that their operating budget be at least maintained and preferably significantly grown. Okay, now we might give the following dismisser argument. We might say, look, the head of that bureaucracy is eager to have as large an operating budget as possible under her control. That's her job, is to gather as many resources as possible and harness them in the service of whatever purposes she sets out to achieve. But from that we could draw the conclusion that any reasons that she gives in support of the conclusion that her department, her bureaucracy, needs to maintain or grow its current budget, those reasons are unlikely to provide strong support for that conclusion. Again, that leaves it open. Perhaps the conclusion is true. Perhaps even the reasons provide strong support for that conclusion. And certainly she's entitled to have an opinion on the issue. She's entitled to sound off on the issue. But we should be suspicious of her argument given the interest that she has, given her powerful personal interest in increasing the size of her operating budget. We should be very suspicious of the reasons that she gives. We should assume that they're false unless we have good reason to believe that they're true. We should assume that they don't support her conclusion unless we have good reason to believe that they do. Okay, so these are some examples of dismisser ad hominem arguments that are actually pretty good arguments. But more often than not, dismissers are given in everyday life that are not good arguments, that are fallacies. We might dismiss someone's reasons for a particular conclusion, not because we detect that that person's own interests, let's say their professional interests or their financial interests, determine that they would give this argument in favor of this conclusion, but rather because that person has some feature that maybe we don't like. Maybe we think they're too smart by half, or maybe there's something about them that strikes us as suspicious. We can't quite put our finger on it, but maybe they just seem vaguely, I don't know, European. Something like that. And we on account of that feature, we suspect that whatever argument they're giving is not a good argument. Okay, those are examples of dismissers that are fallacies. Let's consider some examples of those now. In the last two lectures, we talked about two different kinds of ad hominem arguments. There were silencers and dismissers. In this lecture, we're going to talk about the third and final kind of ad hominem argument that we'll be discussing in this course. These are called deniers. So let's start off with the definition of deniers, and then we'll give some examples of deniers that actually are good arguments, followed by some examples of deniers that are fallacies. Okay, so first, what's a denier? Well, a denier is a kind of ad hominem argument that begins with premises about a particular person who's making a point, right? That's what makes it an ad hominem. And it ends with a conclusion denying the point that that person is making, denying the conclusion of that person's argument. It's not saying the person isn't authorized or entitled to speak on the issue. It's not saying that the reasons the person presents in favor of their conclusion are somehow defective, false, insufficiently supportive of the conclusion. Rather, it's saying independently of any of that, the conclusion is false. The conclusion that that person is coming to is false. So that's how a denier works. Let me give you some examples of deniers that are actually good arguments. So here's one. Suppose that Arthur performs the following speech act. I don't know why Arthur would do this, but let's just suppose he does. He says, "I am an inveterate liar, and most of the time I speak falsely, including now. Therefore, this very statement is false." Okay, now, if that's what Arthur says, then we can conclude that the point that Arthur is making, the conclusion that Arthur is drawing from his argument, is not true. Because the conclusion that he's drawing from his argument is, this very statement is false. But the problem is, if it's true that this very statement is false, then that means that that statement really is false, in which case it's not true. So it can't be true that this very statement is false. In other words, Arthur's conclusion, the conclusion that Arthur reaches at the end of his argument, is not true. Now, we just proved that. So, we just proved that by thinking about the performance that Arthur gave, where he was making a speech act with that content. He said, I'm an inveterate liar. Most of the time I speak falsely, even now. Therefore, this very statement is false. When Arthur says that, we can prove that the conclusion that he's reaching is not true. So there's an example of a denier. It starts with a premise about a particular person, in this case, Arthur, and it's a premise about what Arthur does, and it ends with a conclusion to the effect that the conclusion that Arthur drew is not true. So it denies the conclusion that Arthur drew. So there's an example of a denier ad hominem argument, but that argument actually is a good one. If Arthur issues that particular verbal performance, then the conclusion that he draws is not true. Okay, so there's an example of a denier that's a good argument. Here's another example of a denier that's a good argument. Suppose that Sybil is arguing in front of, let's say, her university's honor court that her classmate Susan cheated on some exam that both Sybil and Susan took. Now, I might argue as follows. Look, in her argument, Sybil did provide a lot of evidence that Susan cheated on the exam. But though Sybil's evidence may seem compelling, in fact, Sybil herself is an unrepentant cheater who repeatedly tries to hide her tracks. She tries to disguise her cheating by planting evidence of cheating on innocent classmates. Therefore, I conclude, Sybil's conclusion itself, to the effect that Susan cheated, Sybil's conclusion is probably not true. Susan probably did not cheat, despite the evidence that Sybil has presented against her, because Sybil does have this track record of planting evidence on innocent classmates. Okay, there also is an example of a denier argument. It starts with a premise about a particular person, in this case Sybil, and it ends with a conclusion to the effect that Sybil's own conclusion is false, or at least probably false. So it doesn't say Sybil isn't authorized to speak on the issue of cheating. It doesn't say that Sybil's evidence doesn't support her conclusion. It just says that regardless of Sybil's entitlement to speak on the issue and the support that her evidence lends to her conclusion is false, or at least probably false. So that's another example of a denier argument. And there again, we have a denier argument that seems like a pretty good argument. It's not deductively valid, but it's a pretty strong argument nonetheless. It's a strong inductive argument nonetheless. Okay, so those are examples of good denier arguments. But we have to search far and wide to find examples of good denier arguments. What we find more often, especially when we look through the media, are examples of bad denier arguments in which we conclude that someone else's argument leads to a false conclusion, and we draw that conclusion based on features of the person that are really irrelevant to the truth of the conclusion that they're arguing for. We'll see some examples of that right now. In the last few lectures, we've been looking at the varieties of ad hominem argument. And in particular, we've looked at a bunch of examples of ad hominem fallacies and the different kinds of ad hominem fallacies. Today, I want to start on a new but related topic. The new topic is appeals to authority. So first, let me define appeals to authority and make it clear precisely how appeals to authority are related to ad hominem arguments. So first, what's an appeal to authority? So an appeal to authority is a kind of argument that begins with premises about a particular person who's making a claim and ends with a conclusion that endorses that person's claim. In a way, you could think of an appeal to authority as the opposite of an ad hominem argument, right? Remember, an ad hominem argument is one that starts with premises about a particular person who's making a claim and then ends with a conclusion that is opposed to that person's claim. In an appeal to authority, you start with the same sorts of premises, but you end with a conclusion that is in favor of that person's claim. Okay, so here's an example of an appeal to authority. It's a particularly egregious example, not one that anyone would be consciously guilty of making, but still an example to give us the rough idea. So, premise one, Takahashi has just given an eloquent presentation of evidence that normalizing U.S. relations with Cuba will result in benefit to both nations. Premise two, Takahashi's presentation was extremely eloquent and she was very well dressed. Conclusion, we should accept Takahashi's conclusion to the effect that normalizing relations between the United States and Cuba will result in benefit to both countries. Okay, so that's an example of an appeal to authority. It's an argument that begins with premises about a particular person, in this case premises about how eloquent Takahashi was and how well dressed she was. Right? So we start off with premises like that and we end with a conclusion, so we should believe her. We should accept her conclusion because after all, she was so well dressed and eloquent. Okay, now as I said, that's a very egregious example of an appeal to authority. But appeals to authority all have that structure. They start with premises about a particular person, and they end with a conclusion to the effect that what that person said is especially credible, should get special weight. Okay, so appeals to authority, like ad hominem arguments, come in three kinds, corresponding to the three jobs that someone is doing whenever they give an argument or whenever they try to prove a point. Remember, the three things that someone is doing whenever they give an argument or try to prove a point are these. First, they're implying that they are entitled to put forth claims about the issue. Right? If I'm putting forth claims about an issue, then my behavior implies that I'm entitled to do so. Second, the person who's putting forth claims about an issue, is making an argument about an issue, is implying that the premises that they're giving actually do support the conclusion that they're drawing. Right? I wouldn't be giving certain premises in support of my conclusion unless I believed that those premises really did support that conclusion. So, for me to give certain premises in support of a conclusion is to imply that those premises really do support that conclusion. I might not be saying that the premises support that conclusion, but my behavior clearly implies that I think so. Okay, finally, of course, when you give an argument in favor of a certain conclusion, you're claiming that the conclusion is true. That's part of the point of arguing for a conclusion. You're trying to prove the conclusion, establish it, claim that it's true. Okay, well, corresponding to these three things that people do when they give arguments, there are three different kinds of appeals to authority that we can make. Right? We can make a kind of appeal to authority that I call an amplifier. An amplifier is an argument that begins with premises about a particular person who's making a point and ends with a conclusion to the effect that we should place great weight or place great credence on the point that the person is making, right? That person is somehow especially entitled to speak on the issue, that they have some special authority that makes their argument deserving of our attention. That's an amplifier. Or we could give an appeal to authority argument that I call a supporter. A supporter is an argument that begins with premises about a particular person who's making a point and ends with a conclusion to the effect that the reasons that the person is giving in support of their point are especially compelling reasons. And finally, there's a kind of appeal to authority that I call an affirmer. When you give an affirmer, you're giving an argument that begins with premises about a particular person who's making a point, and you end with a conclusion that affirms the point that person is making, a conclusion that supports that person's conclusion, insists that that person's conclusion is true, or at least very probably true. Okay, so these are three different kinds of appeals to authority, and again, they correspond, just as the three different kinds of ad hominem argument corresponded to the three different things that someone is doing when they give an argument, right? The three different kinds of ad hominem argument were three different ways of arguing that the person who was making a point hadn't successfully executed one of these three jobs. The three different kinds of appeals to authority are three different ways of arguing that a particular person who's making an argument has successfully executed one or another of these three different jobs. Okay, so those are the three kinds of appeals to authority. In the next lecture, we'll talk about amplifiers. We'll give some examples of amplifiers that are good arguments, and then some examples of amplifiers which, occurring more routinely, are bad arguments. Okay, see you next time. In the last class, we distinguished three kinds of appeals to authority, and today I want to talk about the first of those three kinds, a kind of argument that we'll call amplifiers. What's an amplifier? We'll define it, and then we'll consider a couple of examples. First, we'll consider examples of amplifiers that are actually good arguments, and then we'll look at some amplifiers that are bad arguments. Okay, so first, here's the definition. What's an amplifier? An amplifier is an argument that begins with premises about a particular person who's making a point, and it ends with a conclusion to the effect that we should place great weight or lend great credence to the person's point, right? Whatever the person is saying, they have a special entitlement. They're especially authoritative to say it. Okay, so that's an amplifier. Now, I said sometimes amplifiers are good arguments. To see an example of a couple of amplifiers, both of which are good arguments, I'd like you to look at the following clip.
And the funny part of it is, Marshall McLuhan, you don't know anything about Marshall McLuhan's work.
Really? I happen to teach a class at Columbia called TV, Media, and Culture. So I think that my insights into Mr. McLuhan, well, have a great deal of validity.
Oh, do you?
Okay, now, in that clip, we saw a person who was a Columbia University professor arguing as follows, implicitly arguing as follows. I teach a class on media and popular culture at Columbia University. Therefore, you should lend great credence to my views on the issues of which I speak. That seemed to be the argument that the person was making. That's why he brought up the fact that he teaches a class on media and popular culture at Columbia University in order to lend credence to his views on the topic. Okay, now it's true that if someone is a Columbia University professor who teaches a particular topic, that does tend to establish some credibility that they might have on that topic. But while that might be a good amplifier argument, it doesn't prove that its conclusion is true, and to see that it doesn't prove, not conclusively anyway, that its conclusion is true, we need to look at the rest of that clip and consider another amplifier argument that occurs in the rest of that clip, right here.
Because I happen to have Mr. McLuhan right here. So, yeah, just let me, come over here a second.
Oh,
Tell him.
I heard what you were saying. You know nothing of my work. You mean my whole fallacy is wrong. How you ever got to teach a course in anything is totally amazing.
Boy, if life were only like this.
Okay, so what's happening there? What's happening there is that Marshall McLuhan himself appears. Now, Woody Allen, like the rest of us, can reason as follows. Marshall McLuhan himself is the world's most noted living expert on popular media and culture, or at least he was at the time that that movie was made. Therefore, we should lend great credence to whatever it is that Marshall McLuhan says on that topic. Unfortunately, since what Marshall McLuhan says on that topic is directly opposed to what the Columbia University professor says on that topic, the conclusion of our first amplifier argument is a conclusion that gets overridden by this second amplifier argument. Okay, so you have two amplifier arguments that occur in that clip that I just showed. Both amplifier arguments are good arguments. They're not sound arguments, they're not deductively sound, but they're inductively strong. But as we saw in Unit 3 of the course, an inductively strong argument can still have a false conclusion. This is a case where we have two inductively strong arguments. They can't both have a true conclusion. One of them must have a false conclusion. And it appears that our second amplifier argument overrides our first. So here's a case where we have two good amplifier arguments. But good amplifier arguments are pretty few and far between. More often in daily life, we find bad amplifier arguments. Today we're going to talk about another kind of appeal to authority that we call a supporter. We're going to define what supporters are, give a couple of examples of good supporter arguments, and then talk about some bad supporter arguments, some supporter fallacies. So first, what are supporters? Well, supporters are arguments that begin with premises about a particular person who's making a point, and they end with a conclusion to the effect that the person's reasons for their point are especially compelling, especially good reasons. Maybe the reasons are likely to be true, or maybe they're especially likely to support the conclusion, but in whatever way, they're especially good reasons. Okay, now sometimes supporter arguments are good arguments. Let me give a couple of examples. So suppose I argue as follows. Premise 1, Warren Buffett has argued that confidence in the dollar will rise and therefore the price of gold will soon fall. Premise 2, when Warren Buffett speaks, investors listen and believe. Therefore, conclusion, confidence in the dollar will probably rise. Right? So the reason that Warren Buffett gave in support of his conclusion that the price of gold will fall, namely that confidence in the dollar will rise, that reason is especially likely to be true. Why is it especially likely to be true? Well, I'm saying it's especially likely to be true because Warren Buffett said it was especially likely to be true. And when Warren Buffett says it, that makes it true because investors listen to what he says and they believe in him. And if investors all believe that other people are going to be confident in the dollar, then investors will all be confident in the dollar. Okay, so there's an example of a supporter argument. I start off with premises about a particular person. In this case, Warren Buffett. I start off with a premise to the effect that he's listened to by investors. Investors believe what he says. And I end up with a conclusion that the reason Warren Buffett gives in support of his conclusion that the price of gold will fall, that reason is an especially good reason. In this case, it's especially likely to be true that confidence in the dollar will rise. So there's an example of a supporter argument that's a good argument. Here's another example. Premise 1. Isaac Mizrahi says that given how constricted pants have become in recent fashion, many people will now want to bring back bell-bottom pants. Premise 2. Isaac Mizrahi is one of the trendsetters in the fashion industry. That's what I gather from Googling things on the internet, but maybe one of you knows better. Conclusion, it's true that many people will experience today's pants as constricting and come to see bell-bottom pants as trendy. Okay, now that's a supporter argument. It starts off by stating a premise about Isaac Mizrahi and the central place that he occupies in today's fashion industry. And it ends up with a conclusion to the effect that the reason Isaac Mizrahi gives for his conclusion that bell-bottom pants are soon coming back, the reason that he gives is a reason that's especially likely to be true. Why is it especially likely to be true that people are going to experience today's pants as constricting? Well, it's especially likely to be true because Isaac Mizrahi said it was true. And if Isaac Mizrahi says that people are going to experience pants as constricting, then that's going to make it more likely to be true because people who follow fashion feel about clothes roughly the way Isaac Mizrahi says they should feel about clothes. And so if Isaac Mizrahi says that they're going to experience today's pants as constricting, then very likely they will experience today's pants as constricting. And so they will demand a return of bell-bottom pants. Okay, so there's another supporter argument. And once again, I think this supporter argument is a good argument. It's not a deductively sound argument, but it's a good argument. Okay, so there are some examples of good supporter arguments. It's a lot easier to find examples of bad supporter arguments, of supporter fallacies. We can see some of those right now. In the last couple of lectures, we've talked about a couple different kinds of appeals to authority argument, amplifiers and supporters. Today we're going to wrap up our discussion of appeals to authority by talking about the third kind of appeal to authority argument, affirmers. So what's an affirmer? Once again, let me give a definition, give some examples of affirmers that are, at least arguably, good arguments, and finally we'll look at some examples of affirmers that are not good arguments, that are fallacies. Okay, so first, what's an affirmer? An affirmer is an argument that begins with a premise about a particular person who's making a point, says something about that person, and the argument ends with a conclusion that affirms that person's point, that endorses the conclusion that the person is drawing. So an affirmer doesn't say anything about the person's entitlement or authority on the issue. The affirmer doesn't say anything about the strength or quality of the person's reasons in support of their point. The affirmer just says, well, they said it, roughly, so whatever conclusion they drew is true. That's the basic form of an affirmer. Okay, let's start with a couple of examples of affirmers that are, as I said, at least arguably, good arguments. Okay, the first example is very similar to an example that we saw last time with supporters. There is a difference, though. So here's an affirmer version of the argument about Warren Buffett that we considered in the last class. Premise 1, Warren Buffett has argued that confidence in the dollar will rise and that therefore the price of gold will soon fall. Premise 2, when Warren Buffett speaks, investors listen and believe. Okay, now those two premises are the same as the two premises of the supporter argument about Warren Buffett that we considered last time. But here the conclusion is different. Here the conclusion is, therefore the price of gold will soon fall. So here the conclusion is not that Warren Buffett's reasons for his claim are good. It's not that, in fact, confidence in the dollar will rise, or that the rise in the confidence of the dollar is supportive of a drop in the price of gold. The conclusion is simply that Warren Buffett's conclusion that the price of gold will soon fall, that conclusion is true. Okay, so the difference between this affirmer argument and that supporter argument might not seem very significant. This is an example of an argument that could be spun both as an affirmer and as a supporter, but sometimes the difference between an affirmer and a supporter does matter, as in this next example. Suppose you argue as follows. The Pope argues that masturbation is carnal misuse of one's body, and that therefore it's a sin. Conclusion, therefore masturbation is a sin. Now, there's some people, I think over 1 billion of them, who believe in the infallibility of the Pope. And if you're one of those people, then you will think that this is a good argument. I am not taking a view on whether or not it's a good argument, at least not for the purposes of this class, but my point is that if you accept papal infallibility, then you're going to think that this is a good argument. But notice, you're going to think that this is a good argument even if you have no understanding whatsoever of what the Pope means when he speaks of carnal misuse of one's body, even if that phrase is completely opaque to you. So you have no understanding at all of the Pope's reasons in support of his conclusion that masturbation is a sin. Still, you recognize the Pope has given some argument. To you, the argument sounds like this. Blah, 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 blah. Masturbation is a sin. That's what the argument sounds like to you. But since you believe in the infallibility of the Pope, you think that whatever there is to say about the reasons that the Pope gave, the conclusion must be true. It must be true that masturbation is a sin, since after all the Pope said it and he argued for it. This is an example of an affirmer argument that is quite different from an analogous supporter argument where you conclude from the fact that the Pope gave a certain argument that the reasons that he gave in the course of that argument must be good. Right here, you're not drawing any conclusion about the Pope's reasons because you don't even understand the Pope's reasons. You don't know what carnal misuse of one's body is. Right? The only conclusion you're drawing is that the Pope's conclusion is true. And again, for those of you who believe in papal infallibility, this will look like a good argument, right? If the Pope is infallible and he argues that masturbation is a sin, then it must be a sin. Okay, so these are examples of affirmer arguments that are, at least arguably, good arguments. Now we can look at some examples of affirmer arguments that are not so good. Over the last few lectures, we've been talking about fallacies of relevance, including ad hominem arguments and appeals to authority. Today, I want to talk about a kind of argument that's similar to an appeal to authority, but not exactly the same. It's an appeal to popular opinion. Okay, so what's an appeal to popular opinion? Here, let me give a definition and then some examples. An appeal to popular opinion is an argument that begins with premises about the popularity of a particular claim and ends with a conclusion endorsing that claim. Roughly, an appeal to popular opinion is an argument of the form, well, everyone believes it, so it must be true. Now, some arguments of that form are actually good arguments. Let me give you some examples. So here's an argument, premise. Many people think, at least in my experience as a teacher, I found many people think that the verb to emulate is a synonym of the verb to imitate. Therefore, conclusion, at least one of the meanings of the verb to emulate is the same as the meaning of the verb to imitate. Now that's an appeal to popular opinion. It starts out saying what it is that a lot of people think, and then it draws a conclusion that what a lot of people think is true. But here, I think this is actually a pretty good argument. And the reason it's a good argument is because what the verb to emulate means depends, at least in part, on what the users of that verb take it to mean, what they use it to mean. And if people are using the verb to emulate to mean imitate, then at least one of the meanings of the verb to emulate becomes imitate. So popular opinion, in this example, popular opinion makes it true that the verb to emulate has at least one of the meanings that it has. Okay, here's another example in a different domain, but a similar sort of phenomenon where you have a good argument that's an appeal to popular opinion. So, premise, more and more merchants regard the local currency as losing value. Therefore, conclusion, the local currency is losing value. Once again, this is a pretty good argument, and it's a good argument because if more and more merchants regard the local currency as losing value, then they're not going to be as willing to trade their goods and services for the local currency. They will demand more of the local currency in exchange for their goods and services, or maybe they simply won't be willing to accept the local currency at all in exchange for their goods and services. And if that's true, then the local currency will lose value because each unit of the local currency will have less purchasing power. And so the local currency will lose value. Once again, here's a case where popular opinion makes true what it is that the people believe. Right? So this is a good argument. That's an example of an appeal to popular opinion. Not all appeals to popular opinion, though, are good arguments. Some of them are bad arguments. Some of them are fallacies. And let's take a look at some of those right now. We've devoted this week so far to talking about fallacies of relevance, but today we're going to talk about fallacies of vacuity. Let me begin by defining what a fallacy of vacuity is. A fallacy of vacuity is a fallacy that results when, roughly speaking, an argument starts by assuming what it's supposed to establish. You could think of it this way. A fallacy of vacuity is an argument that doesn't go anywhere. Its starting points presuppose what it is that the argument is supposed to prove. Okay, so there are different kinds of fallacies of vacuity. And in this lecture and the next, we're going to be talking about three different kinds of fallacies of vacuity. The first is something called circularity. A circular argument, a fallacy of circularity, occurs when an argument's conclusion is contained among its premises. You write out the premises of the argument, and one of the premises just is the conclusion. That's a circular argument, and that fallacy is called circularity. Another broader kind of fallacy of vacuity, when I say broader kind of fallacy of vacuity, I mean this kind of fallacy of vacuity includes circularity as a subspecies, is what's called begging the question. Begging the question is when an argument has the following feature. In order to be reasonable in believing the premises of that argument, you already have to have a good reason for believing the conclusion. So, unless you already have a good reason for believing the conclusion, independently of the premises, the argument can't go anywhere because you won't have a good reason for believing the premises. And so, if you don't have a good reason for believing the premises, then the argument can't give you a good reason for believing the conclusion. So roughly, an argument begs the question when you need to have a good reason for believing the conclusion already in order for you to have any reason to believe the premises of the argument. That's begging the question. Right? That includes circularity, because notice, in a circular argument, you have to have a good reason for believing the conclusion in order to have a good reason for believing the premises, because the conclusion is one of the premises. But begging the question can happen even without circularity, and we'll talk about examples of that next time. The last kind of fallacy of vacuity that I want to describe is something called self-sealing. Now, a self-sealer can be either a proposition or an argument, but roughly, a self-sealer is when a proposition or an argument is irrefutable by any possible consideration, no matter what. And so it doesn't rule out anything. So if I make some claim to the effect that at a certain point in time, you will then be doing exactly what you will be doing, you might think, well, yeah, so what does that tell me? What possible situations are ruled out by that statement? The answer is none. And so that statement is empty. It's vacuous. It's a self-sealer in the sense that there's no possible situation that it rules out, and so there's no possible consideration or evidence that could be brought forth against it. A self-sealing argument is one that commits a fallacy of vacuity because it does assume what it's intended to establish. Unfortunately, in a self-sealing argument, what it's intended to establish is nothing of any significance. It's nothing that rules out any possibility. And so it does tend to assume what it's supposed to establish. So, those are three kinds of vacuity that I want to distinguish. In the next lecture, we'll talk a bit more about circularity and begging the question, and in the lecture after that, we'll talk a bit more about self-sealing. See you next time. Now that we've introduced the topic of fallacies of vacuity, today we're going to talk about circularity and begging the question. So, what are these things? What is circularity and what is begging the question? Circularity is a fallacy that results when an argument's premises contain its conclusion, when the conclusion is right there among the premises. Now, this is a really egregious fallacy, not one that people are likely to make very often because it's so easy to notice. But let me give you an example, just so you can see what I'm talking about. So consider this simple example of circularity. Premise 1. This very argument, has a premise. Premise 2, this very argument has a conclusion. Therefore, conclusion, this argument has a conclusion. Now notice, the conclusion of that argument is the same proposition as premise 2 of that argument. In other words, the conclusion is right in the premises. That's a circular argument. That's an example of a fallacy of circularity. That's pretty hard to miss, and that's not the kind of fallacy that most people often make. But circularity is one very egregious example of a more general kind of fallacy that lots of people make, and that's called begging the question. So what's begging the question? Well, begging the question is a kind of fallacy that results when you can't have any reason for accepting the premises of the argument unless you already have some independent reason for believing the conclusion. Right? So in a certain sense, the argument assumes what it sets out to prove, because unless you already have a good reason for believing the conclusion to be true, you can't have a good reason for believing the premises to be true. And without having a good reason for believing the premises to be true, the argument can't give you any insight. It can't teach you anything. Right? No argument can teach you something unless you have a good reason for believing the premises of that argument to be true. So, that's the fallacy of begging the question. Now, what's an example of that? Well, these examples can be a little more subtle, right? Because not all forms of begging the question are circularity. Let me give an example of begging the question that doesn't involve circularity. So consider this argument. Again, it's a simple argument. The Pope says that he is infallible. Premise 2, whatever the Pope says is always right. Therefore, conclusion, the Pope is infallible. Now notice that argument is obviously valid. Right? If the Pope says that he's infallible and whatever he says is right, then he must be right to say that he's infallible. In fact, that's how the doctrine of papal infallibility was first established, was by papal decree. I'll let you look that up. Anyhow, if the premises of the argument are true, the conclusion has to be true. So the argument is valid. But even though the argument is valid, in fact, even if the argument is sound, the argument is still a fallacy. And the reason it's a fallacy is that we can't have any good reason for believing premise 2 of the argument unless we already have some reason, independently of the argument, for believing the conclusion. Right? Unless we already know that the Pope is infallible, why should we believe that whatever the Pope says is always right? Well, maybe there is some other reason, but unless that additional reason is supplied in the argument, this argument begs the question. It begs the question because it relies on premises that we have no reason to believe unless we already have a good reason to believe the conclusion independently of the argument itself. So this argument is an example of begging the question. But notice it's not an example of circularity. The conclusion of the argument that the Pope is infallible, that conclusion is not in the premises. It's not one of the premises. Right? There are two premises in the argument, and neither of those premises says precisely that the Pope is infallible. So this argument is an example of begging the question, but it's an example of begging the question that doesn't involve circularity. And that sort of fallacy is much harder to notice, much easier to make, and much more common in everyday life. You can see some examples right now. Today we're going to conclude our discussion of fallacies of vacuity by talking about self-sealers. So what's a self-sealer? Let me start by giving a definition and then giving some examples. So first, a self-sealer is a proposition or an argument that's irrefutable. It can't be refuted because it doesn't claim anything. It doesn't rule out any conceivable situation. So in that sense, it doesn't place any constraint on how the world has to be. Any possible way that the world is would conform to the proposition. So, what are some examples of that? Well, suppose someone says, and you might have heard philosophers who say this, suppose someone says, all human action is selfish. Now, at first, this seems like a bold conjecture, a very substantial thesis that could be right or it could be wrong. Now, there's an obvious objection to this thesis. You say, well, Look, what about self-sacrificing heroism? Occasionally, people will lay down their lives in the service of a cause that's larger than they are. Suppose you present this counterexample to the proponent of this generalization, and they say, well, look, even self-sacrificing heroism is itself motivated by the desire to be a hero. So the person who's performing the self-sacrificing heroism is still really acting selfishly because they're just trying to satisfy their own personal desire to be a hero. Some people want chocolate, and so they go out to get chocolate. Some people want to be a hero, so they go out looking to be a hero. Okay, well, suppose we decide to investigate this further. We find people who are who tend to engage in self-sacrificing heroic behavior, maybe people who are lucky enough to have engaged in such behavior in the past and they're still alive. And so we find such people and we test them in various ways. We do brain scans of them, we give them various surveys, we do behavioral tests on them, trying to test whether or not they have the desire to be a hero. And all our tests come up empty-handed. We just don't find any evidence. No matter how many tests we perform, we don't find any evidence that this person or these people really do have the desire to be a hero. They just aren't thinking about being a hero. They just want to save the world or save their fellow people or save the environment or whatever, right? So it's because of the larger cause that they're thinking about that they engage in self-sacrificing heroic behavior, and we have no evidence that they want to be a hero. Now suppose we present all of this evidence to the proponent of the generalization in question. We say, look, we've tested these people, we've given them brain scans, we've done surveys with them, we've done all sorts of behavioral tests with them, and we can't find any evidence that they have some desire to be a hero, a desire that motivates their self-sacrificing heroic behavior. And suppose when we put this to the proponent of the generalization, they reply by saying, well, look, even if their desire to be a hero isn't rendered apparent by the tests that you've performed, it must still be there. After all, how else could we explain their self-sacrificing heroic behavior? Okay, but now it's clear that the person is offering us a self-sealer. It's a position which they can defend no matter what evidence they're presented with. Right? So no matter what evidence comes up, no matter what considerations come up, they can stick to their guns. They can continue to propound their view that all human action is selfish. But now it's pretty clear that the view that they're propounding, the proposition that they're putting forth, doesn't claim anything. It doesn't rule out any possible way that the world could be, because as we come upon various ways that the world is that seem to tell against their generalization, what they do is they make their generalization less and less specific so that even if the selfishness of which they speak isn't made manifest in any way at all, it's going to be made manifest in the human action itself. Right? So as long as there's human action, there's got to be selfishness, they say, because what other way could you explain the human action? Okay, that's a self-sealer. It's a self-sealer because they're simply insisting on the position in the face of any evidence that comes up. All right. Now, that's a self-sealing proposition. What's a self-sealing argument? Well, typically self-sealing arguments are arguments that contain, among their premises, self-sealing propositions. They're arguments that depend on self-sealing propositions. But there might be an example of a self-sealing argument that isn't like that. I say might. I don't say there is an example. I say there might be an example. Let me offer it to you now and see what you all think. Here's the example. Premise 1. Not every argument has a conclusion. See? Now, I know what you're thinking. You're thinking, wait a second, didn't we define argument way back in one of those early weeks with a different teacher? Didn't we define argument as something that had one or more premises and a conclusion? Wasn't that just built into the very definition of argument? Well, look, sometimes things can be built into the very definition of something, But still, you can come upon considerations or evidence that lead you to revise that definition. Right? There are all sorts of institutions in human life that are defined in various ways, and then as the world changes, we decide we want to revise that definition. And there could be good reasons for doing so. So, originally we defined an argument as some premises and a conclusion, but maybe we should revise that definition. Why does an argument need to have a conclusion? Couldn't an argument just have a premise and that's it? Well, I'll let you debate that in the forums. But I just wanted to point out that if this really is an argument, if this premise really does constitute an argument, then the premise is true that not every argument has a conclusion. But unless you can think of some way of refuting the proposition that not every argument has a conclusion, then this particular argument, consisting of the premise that not every argument has a conclusion, this particular argument is a self-sealer, because there's no evidence that you could present to show that the argument itself is unsound or unsuccessful. So, that's an example of an argument that's a self-sealer, which, if it is an argument that's a self-sealer, is not the same as any particular proposition that's a self-sealer. Because the premise, not every argument has a conclusion, that premise is a proposition, and that proposition is not a self-sealer. But if that premise is an argument, the argument may be a self-sealer. Okay? All right. So that concludes our week on fallacies of relevance and vacuity. I'll see you next week when we'll talk about refutation. See you then. Over the last couple of weeks, we've been talking about fallacies in order to help you all figure out ways in which you can criticize an argument. Right? Sometimes an argument might seem valid or strong, but if you recognize that it's actually a fallacy, that'll help you to see what's wrong with the argument and not to be moved by it. But there are other ways of criticizing arguments besides recognizing them as fallacies, or in any case, recognizing them as one of the kinds of fallacies that we've been discussing so far over the past couple of weeks. And this week, we're going to broaden our scope a little bit and talk about other ways of criticizing arguments. This week, we're going to talk about refutation, its varieties and pitfalls. So, what's refutation? What are the varieties of refutation? And what are the pitfalls of refutation? Let's address those questions in order. So first, what is refutation? Refutation, or to refute an argument, is to show that the argument is unsuccessful in some way or other. That's what you're doing when you refute an argument. You're showing that the argument is unsuccessful in some way or other. Now, an argument might be unsuccessful because we're not entitled to accept its premises. Right? Maybe its premises are false, or maybe whether they're true or false, we just have no reason to accept them. Or an argument may be unsuccessful because whether or not its premises are true or known by us to be true, the premises don't support the conclusion of the argument. Right? So the conclusion isn't adequately supported by the premises. It doesn't follow from the premises. It's not something that the premises give us very powerful reason to believe. So we can refute an argument by showing that it's unsuccessful in any of those ways. Okay, so because refuting an argument is just to show that it's unsuccessful in any of those ways, there are going to be different ways to refute an argument corresponding to the different ways in which arguments can be unsuccessful. So for instance, if we're going to show that the premises of an argument don't support its conclusion, then we can do that by means of something that we'll call refutation by parallel reasoning. Right. One way of doing that, of course, is to point out that the argument is a fallacy. Right. It might appear valid or strong, but in fact it's not. But another way of doing that, independently of pointing out that it's a fallacy, is to refute the argument by parallel reasoning. And in the next lecture, we'll talk about what refutation by parallel reasoning is. Another way that we might refute an argument is by showing that its premises are false, or in any case, whether they're false or not, we're not entitled to accept them. And we can do that, we can show that we're not entitled to accept the premises by using things that we'll call counterexamples, or a method that we'll call reductio ad absurdum. Okay? So those are the varieties of refutation. We can refute an argument by means of parallel reasoning, we can refute an argument by means of counterexamples, or we can refute an argument by reductio ad absurdum. And we'll talk about those different varieties of refutation this week. Now, often refutations are successful and help us to see why an argument that someone else is giving, or maybe an argument that we ourselves gave, is unsuccessful. But sometimes refutations don't work. In particular, there are a couple of different kinds of error to which refutations are especially liable. One of those kinds of error is what's called attacking a straw man, or refuting a straw man. Sometimes when you try to refute a particular argument, you end up attacking something that isn't quite the same as that argument. Something that might seem very similar to that argument, you might mistake it for being the same as that argument, but it's not quite the same, and the difference is significant. That's called attacking a straw man. Your refutation of an argument also might be unsuccessful because it depends upon a false dichotomy. You assume that a particular dichotomy is true. Either things have to be one way or they have to be another way. And you make that assumption in attempting to refute an argument, but your refutation is unsuccessful because the assumption that you've made, the assumption that things have to be either one way or another way, is a false assumption. That's called a false dichotomy. Okay, so those are some dangers to which refutation is subject, and we'll also be talking about those this week. All right. So now that we've said what refutation is, what its varieties are, and what its dangers are, let's start talking about particular kinds of refutation. Next time, we're going to talk about refutation by parallel reasoning. See you next time. Today we're going to talk about refutation by parallel reasoning. Okay, so what's refutation by parallel reasoning? Let me start by giving a definition, and then I'll give some examples. So first, to refute an argument by parallel reasoning is to show that the argument's form is not valid or strong. The form of the argument is bad. Now, one way to show that, a way that we've described over the past couple of weeks, is to show that the argument commits one of the fallacies that we've described. For instance, that it commits some kind of a slippery slope fallacy, or it's a fallacious dismisser, or fallacious amplifier, or commits a fallacy of equivocation. That's one way to show that an argument is a fallacy, that its form is not valid or strong, that its premises, whether true or not, don't support its conclusion. But sometimes an argument is a fallacy even though it doesn't fit into any of the categories of fallacy that we've described up until now. But you can still show it's a fallacy, and the way you show it's a fallacy then is to refute it by parallel reasoning. And the way you do that is by finding another argument that has exactly the same form as the first argument. Exactly the same form, but the other argument is clearly a fallacy. So if the second argument is clearly a fallacy, and it has the same form as the first argument, then the first argument must also be clearly a fallacy. Since whether an argument is a fallacy or not doesn't depend on the truth of its premises or the truth of its conclusion, whether an argument is a fallacy or not just depends on its form, on the relationship between the premises and the conclusion. So if you can find an argument with exactly the same form that's clearly a fallacy, that shows that the first argument is a fallacy. That's refutation by parallel reasoning. Now let me give you some examples. So consider this argument. Premise: if I had a higher salary, I could buy a bigger house. Conclusion: therefore, if everyone had a higher salary, everyone could buy a bigger house. Okay, now, I've heard reasoning that resembles this kind of reasoning in the past. People think, well, if we can raise one person's wages and make them materially better off, then if we could raise everyone's wages, we could make everyone materially better off. Okay, but tempting as this kind of reasoning may be, it's fallacious. And in order to show that it's fallacious, let me refute it by parallel reasoning. Let me find another argument that has exactly the same form, but that's obviously a fallacy. So consider this example. This is a parallel argument. If one person stands up at a ball game, then she'll get a better view. Right? Imagine that she's sitting in an audience of people, all of whom are seated. Right? So there are all these people seated and watching the ball game, and maybe the people sitting in front of her are blocking her view of the events in the stadium. So she decides to stand up so she can see over the heads of the people seated in front of her. So if she stands up, she'll get a better view. Conclusion: if everyone stands up at a ball game, then everyone will get a better view. Okay, well, that conclusion is not just obviously false, but it's clearly not supported by the true premise. In fact, this argument is a very clear example of an invalid argument because the premise is very plausibly true. In just about any ball game, when you have one person sitting down, if they stand up, they individually are going to get a better view. But the conclusion is certainly false. If everyone stands up, then that does not mean that everyone will get a better view. In fact, if everyone stands up, then there are going to be some people who end up getting a worse view. So, this is clearly an invalid argument. But if this argument is invalid, then this argument must also be invalid because they have the same form. And that shows that this first argument about salaries has got to be invalid. It's got to be invalid because it has exactly the same form as the second argument about standing up at a ball game. It has exactly the same form, and the second argument is obviously a fallacy because in most scenarios the premise would be true and the conclusion would be false. So if the second argument is invalid, the first argument must be as well. Okay, that's an example of refutation by parallel reasoning. Now let's consider another example so you get the idea. So consider this argument. Premise 1. Most people who start their own businesses, ignore statistics of failure. Right? Because the statistics of failure for startup businesses are pretty bleak. Vast majority of startup businesses fail. They lose money, they go out of business. They go into bankruptcy. So most people who start businesses have to ignore all that, have to believe somehow, despite all the statistics of failure, that they are going to succeed. Premise 2, most people who ignore statistics of failure are stupid. Conclusion, therefore, most people who start businesses are stupid. Okay. Now, let me say immediately that I think this argument is a fallacy, and furthermore, that its conclusion is false. But how can we see that this argument is a fallacy? For most people who start businesses ignore statistics of failure, and most people who ignore statistics of failure are stupid, how can we see that it's fallacious to infer most people who start businesses are stupid? Well, to see how this argument is a fallacy, compare it to this other argument that has exactly the same form of reasoning. Okay, so here's a parallel argument. Most of my friends are organisms. Right? I mean, it's possible that a few of my friends are robots, but I think that's unlikely. I think at the very least, most of my friends are organisms. If one or two of them are automata who are cleverly disguised to look and act like human beings, so be it. Still, most of my friends, I'm confident, are organisms. Now, most organisms are microscopic. Of course, we don't always keep that in mind because most of the organisms that we interact with on a day-to-day basis are not microscopic. Human beings, dogs, cats, trees, right? These organisms are not microscopic. But in fact, most of the organisms that exist are microscopic. So, someone might infer, well, if most of my friends are organisms and most organisms are microscopic, then doesn't it follow that most of my friends are microscopic? Well, no, obviously not. In fact, none of my friends are microscopic. All of my friends are creatures that I can see without the use of a microscope. So this argument right here is obviously a fallacy. I mean, both of the premises are true, and the conclusion is certainly false. So this argument is obviously a fallacy. It's an invalid argument. But since this argument is invalid, and it has exactly the same form as this earlier argument about ignoring statistics of failure, it follows that this earlier argument must be invalid. Right? This earlier argument from the premises, most people who start businesses ignore statistics of failure, and most people who ignore statistics of failure are stupid, it does not follow that most people who start businesses are stupid. That doesn't follow at all. This is a fallacy. It's an invalid argument. Just showed that by means of parallel reasoning, by finding a parallel argument that has exactly the same form, but it's clearly a fallacy. So since this parallel argument is clearly a fallacy, this earlier argument about ignoring statistics of failure must also be a fallacy. Okay. Now, refutation by parallel reasoning doesn't always work. Sometimes we get results that are unclear or don't show what we were trying to show. For instance, let me give you an example of that. So consider the following argument. If guns are outlawed, only outlaws will have guns. That's premise one. Premise two, it would be bad if only outlaws had guns. Conclusion, therefore guns should not be outlawed. Okay, so that's an argument. It'll be familiar to some Americans. That's an argument. Is it a fallacy or not? Well, suppose we try to refute it by parallel reasoning as follows. If gum is outlawed, only outlaws will have gum. It would be bad if only outlaws had gum. Therefore, gum should not be outlawed. Now notice, this parallel argument has exactly the same form as this earlier argument about guns. The two arguments have the same form. So if one of them is a fallacy, then the other one is a fallacy. But is this argument a fallacy? That's not clear. It's not at all clear that it's a fallacy. So this attempt to refute our earlier argument by parallel reasoning doesn't succeed. It doesn't succeed because the parallel argument is not clearly a fallacy. So we can't tell by looking at the parallel argument whether the earlier argument about guns was a fallacy. So this is a case of refutation by parallel reasoning that doesn't succeed. So what's crucial in refutation by parallel reasoning is this. First of all, you have to make sure that the parallel argument that you're using to refute the original argument, that the parallel argument has exactly the same form as the original argument. And in all three of our examples that we've looked at, that is true. The parallel argument does have the same form as the original argument. But the second thing you need to make sure of is that the parallel argument is clearly a fallacy. Right? If you're trying to show that the original argument is a fallacy, and you're trying to show it by means of parallel reasoning, then the parallel argument that you pick has to clearly be a fallacy. Because otherwise, you haven't shown that the original argument is a fallacy. Okay? And this third example doesn't meet that second criterion. The parallel argument is not clearly a fallacy. Okay. So, that's refutation by parallel reasoning. Next time, we'll consider another way of refuting an argument. See you next time. Today we're going to talk about how to refute an argument by using counterexamples. So what's a counterexample, and how does it help to refute an argument? A counterexample is an example that runs counter to some generalization, and thereby shows that the generalization is false. Now, counterexamples can be used to refute an argument that contains a generalization either as one of its premises or as its conclusion. So if the argument contains a generalization as its conclusion, and the counterexample shows that the generalization is false, then in effect what the counterexample does is show that the argument reaches a false conclusion. If the argument contains a generalization as one of its premises, then the counterexample shows that that premise of the argument is false. But either way, the counterexample shows that the argument is unsuccessful, either because the argument has a false premise or because its conclusion is false. Okay, so what are some examples of counterexamples? Well, let's start by considering this argument. Premise 1. You should always treat others the same way that you would like to be treated yourself. Premise 2. I would not like anyone to change my diapers. So, conclusion, I should not change the baby's diapers. Now, this argument appears to be valid. Furthermore, I can assure you, premise 2 is true. So, if premise 1 is also true, then it looks like I have a good argument for why I shouldn't change the baby's diapers. I should get someone else to do it. But is premise 1 true? Well, premise 1 sounds familiar enough. You should always treat others the same way that you would like to be treated yourself. That's something we frequently hear people say. But that can't be precisely true. After all, I would like to be treated as an adult. But that doesn't mean that I should treat my children as adults, right? So if the generalization is that you should always treat others the same way that you would like to be treated yourself, that generalization is false. It's false because even though I would like to be treated as an adult, it doesn't mean that I should treat my children as adults. I shouldn't treat my children as adults because they're not adults. But I am. Now, that doesn't mean that I should baby my children, but I shouldn't treat them the same way that I would like to be treated myself. I shouldn't treat them as if they're adults. Okay, so that's a counterexample to premise 1. And that counterexample shows that premise 1, stated in the way that it's stated here, you should always treat others the same way that you would like to be treated yourself. Premise 1 stated in that way is false, and so this argument does not work. This argument does not succeed in showing that I should not change the baby's diapers. The reason it doesn't succeed is because one of its premises is false. Now, premise 1 might seem to be true, but if it seems to be true, that's only because something very similar to premise 1 is true. What's similar to premise 1 that is true is the claim that you should usually, typically, often treat others the same way that you would like to be treated yourself. Now, those claims are true. You should usually treat others the same way that you'd like to be treated yourself. But that doesn't mean you should always treat others the way that you'd like to be treated yourself. That general claim about how you should always behave, that claim is false, and our counterexample shows it. So there's an example of the use of counterexample to refute an argument. Let's consider another example. So consider this argument. Premise 1. If it's wrong for all of us to perform a particular action, then it's wrong for any of us to perform that action. Premise 2, it's wrong for all of us to try to take the last piece of bread on the table. So, conclusion, it's wrong for any of us to try to take the last piece of bread on the table. You could imagine this situation. Let's say a bunch of us are sitting around the dinner table eating dinner, and there's a basket of bread in the middle of the table, and we've been, bit by bit, reaching in to take out pieces of bread and eat them. And now there's only one piece of bread left in the basket, and there are a bunch of us sitting around the table. Well, it would be wrong for all of us to jump up and grab that piece of bread and start fighting over it. That would be wrong. That would be completely unacceptable. But just because that would be unacceptable, does that mean that none of us is allowed to go and eat that last piece of bread? Well, no, that seems like a preposterous conclusion. I mean, if all of us have to sit there just staring at that last piece of bread and none of us is allowed to eat it, well, then that's wasting food. That's not an acceptable conclusion. So it's got to be okay for one of us to take that last piece of bread, even though it's not okay for all of us to try to take that last piece of bread. So here's an example where it's okay for one person to do something, even though it's not okay for everyone simultaneously to do that thing. Right? It's okay for one, it's not okay for everyone. So that's a counterexample to the generalization that occurs in premise 1 of our argument. So this argument is not a successful argument. This argument does not prove that it's wrong for any of us to try to take the last piece of bread on the table. And the reason it doesn't prove that is not because the argument is a fallacy. The reason it doesn't prove that is because premise 1 of the argument is false. Premise 1 of the argument states a general claim, and that general claim that it states is not true. While it might be true that it's usually wrong for anyone to perform an action that it's wrong for everyone to perform, it's not true that it's always wrong for anyone to perform an action that it's wrong for everyone to perform. And in fact, I just gave a counterexample to that generalization. It's not wrong for one person to take a piece of bread, the last piece of bread on the table, even though it would be wrong for everyone to try to take that piece of bread simultaneously. Okay, so there's another example of an argument that we can refute by means of counterexample. We can use a counterexample to show that premise 1 of that argument is false, and so the argument is unsuccessful. Finally, let's consider this third case. Premise 1, breaking the law is almost always wrong. Premise 2, double parking is breaking the law. So conclusion, double parking is almost always wrong. Now, can we refute this argument by means of counterexample? Well, there's no counterexample to premise 2. Premise 2 is simply true. Double parking is breaking the law. That's part of what's involved in double parking. When you double park, you are breaking the law. But what about premise 1? Breaking the law is almost always wrong. Is there a counterexample to that? No, there's no counterexample to premise 1 as stated. If premise 1 were to say breaking the law is always wrong, then we could produce a counterexample to premise 1. Sometimes it's an emergency, you have no choice but to double park, you have to do something very quickly. It's not wrong to double park in that situation, especially not if you're doing it for just a few seconds. It's not wrong to double park, and yet you're breaking the law because there's a law against double parking. So if premise 1 were to say breaking the law is always wrong, then there would be a counterexample to premise 1. But premise 1 doesn't say that. Premise 1 says breaking the law is almost always wrong. Now, how do you produce a counterexample to a claim of the form almost always? Well, the answer is you don't. Because even if you produce an example of a case where breaking the law is not wrong, that still doesn't show that it's false, that breaking the law is almost always wrong. Maybe breaking the law is almost always wrong, but just not in the case that you produced. So you can't produce a counterexample to a generalization of the form breaking the law is almost always wrong. That generalization might be false, but you can't show that it's false by using a counterexample. Okay, so we cannot refute this argument by means of counterexample. That's not to say that this is a good argument. In fact, this third argument is not a good argument, but we can't show that it's not a good argument by using a counterexample. So sometimes counterexample can succeed in refuting an argument, and sometimes it can't. It depends on whether the argument contains a generalization to the effect that something always happens, or something is true in all cases. If the argument contains a generalization like that, an unexceptional generalization, a generalization without any room for exceptions, then a counterexample can be used to refute that generalization. But if a generalization is phrased in such a way that it admits of exceptions, like if a generalization talks about what almost always happens, or about what usually happens, about what typically happens, then we can't refute that generalization by means of counterexamples. Okay, so we can look at examples of counterexamples in the exercises that follow. See you next time. Today we're going to talk about a kind of refutation that we call a reductio ad absurdum. Now, what's a reductio ad absurdum, and why does it have such a mysterious name? Let's begin with the definition. So, reductio ad absurdum is a Latin phrase that means reduce to absurdity. And that's what a reductio ad absurdum is. It's a refutation of an argument that focuses on a particular claim in that argument, either one of the premises or the conclusion. And it shows that that claim, that proposition, implies some absurdity. And since it implies some absurdity, the claim itself has to be false, because nothing that's true can imply something that's obviously false. Only something that's false can imply something that's obviously false. And so, if you do a reductio ad absurdum on a proposition, you show that the proposition is false, and if that proposition is one of the premises or the conclusion of an argument, then you've refuted that argument. You've shown that that argument is unsuccessful. Okay, so that's a reductio ad absurdum. Let's look at some examples. So consider this argument. Premise 1, the best way to fight theft is to eliminate the conditions that make it possible. Premise 2, the use of a tangible medium of exchange, like cash, let's say, or gold, is a condition that makes theft possible, right? Without a tangible medium of exchange, there can't be any theft. Conclusion, therefore, the best way to fight theft is to eliminate tangible media of exchange. Now, I've actually heard this argument before. The argument is that if all exchanges, all transactions take place electronically, let's say in a way that's traceable by your fingerprint or by your retinal scan or something like that, if there's no cash, if there's no tangible medium of exchange, then we eliminate the black market and all kinds of goods and services, and we also eliminate the violent crime that's associated with stealing cash. Okay, so the conclusion of this argument might be true. In any case, it might be true for all I'm going to say here. But what I want to point out right now is that we can use reductio ad absurdum to show that premise 1 of this argument is false. So whatever else is true about the conclusion of the argument, premise 1 of the argument is false. And so the argument itself does not succeed in proving its conclusion. So why do I say premise 1 of the argument is false, that the best way to fight theft is to eliminate the conditions that make it possible? Well, if that were true, then think about the various conditions that make theft possible. One of the conditions that makes theft possible is oxygen, or water, or any of the conditions that make human life on the earth possible. Right? Without those conditions, of course, theft wouldn't be possible. So that would imply, premise 1 would imply, that the best way to fight theft is to eliminate the conditions like oxygen, like water, that make theft possible. But that's clearly not the best way to fight theft. It would, of course, be a way to fight theft, but it's not the best way. So premise 1 implies something that's obviously false, namely that the best way to fight theft would be to eliminate oxygen and to eliminate water. That's obviously false. And so premise 1 itself must be false, because nothing that's true could imply something that's obviously false. Okay, so that's an example of how we can refute this argument using reductio ad absurdum to show that premise 1 of the argument is false. Here's another example. So consider this argument. Premise: if you count long enough, you will eventually run out of numbers to count. Conclusion: therefore, counting is an activity that cannot go on forever. Now, this argument is valid, but the premise of the argument isn't true, and so the argument isn't sound. Why is the premise of the argument not true? Why is it not true that if you count long enough, you'll eventually run out of numbers to count? Well, here's a way to see that it's not true. Suppose for a moment that it were true, that if you count long enough, you'll eventually run out of numbers to count. Suppose that were true. Well, then there would be some last number, some greatest number. Now, whatever that number is, call it n. But now, whatever that number is, we can just add 1 to it. Right? Addition is going to be defined over that number n, whatever n is, and 1. So we can add 1 to n, and now we come up with a greater number. So if this premise were true, then it would imply something that's inconsistent with the premise, namely that there's a larger number than n. So the premise can't be true, because it implies something that's inconsistent with the premise itself. So the premise is false, and that shows that the argument is unsuccessful. So we just did a reductio ad absurdum of the premise of our argument. Now, I just gave a couple of examples of reductio ad absurdums that work. But not every attempt at a reductio ad absurdum works. Consider this one. Premise. Some things exist even though no one is thinking of them. Conclusion. Therefore, reality exceeds the reach of the mind. There's more to reality than there is in the mind. Now, suppose someone challenges the premise of this argument as follows. They say, look, you're saying that some things exist even though no one is thinking of them. But as you're saying that, presumably you're not just mouthing the words, you're really thinking it. You're thinking that some things exist even though no one is thinking of them. But if you're thinking that proposition, then you are thinking of those things. So whatever those things are that allegedly exist, even when no one is thinking of them, well, you're thinking of them right now. And so the proposition that you're thinking, namely that some things exist even though no one is thinking of them, that proposition is not true because you're thinking of those very things right now. Those very things that exist even though allegedly no one is thinking of them. Okay, now I leave it as an exercise for you to work out and for you all to discuss with each other in the forums. What's wrong with this attempt at a reductio ad absurdum of the premise of this argument? I'll let you think about that. See you next time. In week 9 of the course, you'll recall, we studied the linguistic phenomenon of vagueness and the different sorts of fallacies to which vagueness gives rise. These are different kinds of slippery slope fallacies, like causal slippery slope fallacy or conceptual slippery slope fallacy. Well, in the discussion forums, Carol Spencer pointed out that there's a passage in Robert Redford's opinion piece, the opinion piece that we analyzed back in Unit 1 of the course with Walter. There's a passage in Robert Redford's opinion piece that seems to commit a fairness slippery slope fallacy. Let's look at that passage from Redford's opinion piece and then look at Carol's argument to the effect that that passage commits a slippery slope fallacy. Okay, so first of all, the quote from Redford goes like this. He wrote, "What's more, in deciding to issue a permit to drill now, the Bureau of Land Management, the BLM, did not conduct a full analysis of the environmental impacts of drilling in these incomparable lands." He's talking about the Grand Staircase Escalante National Monument. "But instead determined there would be no significant environmental harm on the basis of an abbreviated review that didn't even look at drilling on the other federal leases." Okay. So why does Carol think that Redford is committing a slippery slope fallacy in that passage? Well, here's what she says on the discussion thread. She says, and this is a quote, "This reasoning seems based on contrasting full analysis and abbreviated review. Is Redford introducing a fairness slippery slope argument? It isn't fair that the Bureau of Land Management drew a line where it did when it decided that only some specific review steps, but not others, had to be taken before a permit was issued." Okay, So Carroll doesn't spell out in standard form exactly what the fairness slippery slope argument is supposed to be, but let me see if I can do that. Here's the fairness slippery slope argument that she's reading in Redford put into standard form. Premise 1. The BLM, the Bureau of Land Management, would never permit ConocoPhillips to drill, let's say, on Mount Rushmore or the Statue of Liberty or the middle of the Grand Canyon without a full review. Right? These are some of the most historically or ecologically or culturally important landmarks in the United States, and the BLM wouldn't permit drilling on these landmarks without, at the very least, a full review. Premise 2, a sufficiently small difference of ecological, historical, or cultural importance is not a significant difference, right? If it's a very small difference, then it's not significant. But from those two premises, someone might conclude, well, so the Bureau of Land Management can't permit ConocoPhillips to drill in Grand Staircase Escalante National Monument without a full review. You see, because even if Grand Staircase Escalante National Monument is many notches below Mount Rushmore or the Grand Canyon or the Statue of Liberty in its importance, even if it's many notches below those monuments in its importance, still those notches are each of them not a significant difference. And since each of those differences is insignificant, those differences can't make a difference to whether or not the BLM ought to permit Conoco to drill on those monuments without a full review. Right? In other words, if Conoco doesn't permit drilling on Mount Rushmore without a full review, then it shouldn't permit drilling on a monument ever so slightly less important than Mount Rushmore without a full review. And since that would only be marginally more important than another national monument that's not significantly different from it, then it shouldn't permit drilling on that other national monument without a full review, and so on, all the way down to Grand Staircase Escalante National Monument. So I think that's the fairness slippery slope argument that Carroll is attributing to Robert Redford in the opinion piece. Although, Carroll, I hope you'll correct me if I've misunderstood your attribution. Now, if Carroll is right that Redford is making that argument, well, that argument is a fallacy. Because remember, just because a small difference is not a significant difference, it doesn't follow that a big difference made up of a series of small differences is not a significant difference. Each small difference might be insignificant, but the big difference, comprising all of them, could still be significant, even if each individual small difference is not significant. And because fairness requires more than attending to significant differences, because it also requires things like predictability or drawing a line that can be applied consistently, sometimes fairness requires us to distinguish cases that are not significantly different, because we have to draw a line somewhere, and so we draw it in a certain place where it's easy for people to stay on one side or the other of that line. And so sometimes fairness doesn't require us to treat cases differently when they're not significantly different. We can treat cases similarly even when they're not significantly different. Okay, so there's an example of a fairness slippery slope argument that Carroll might very well have accurately interpreted in Robert Redford's opinion piece. And that's an explanation of why the slippery slope argument in this case is a fallacy. It's a fallacy because a series of insignificant differences can lead to a significant difference. Okay, see you next time. After discussing vagueness in week 9 of the course, we turn to the linguistic phenomenon of ambiguity and the fallacies to which ambiguity can give rise. I think a nice example of a fallacy to which ambiguity can give rise is presented in the discussion forums in Yao Yao's fascinating argument entitled, "The Practice to Visit Parents Frequently Shouldn't Be Legalized." Okay, so let's look at Yao's original argument. It goes like this. To visit aged parents, if we don't live together, is a basic moral demand. To legalize a moral demand and make it a law will demean our moral standard. He continues, once some moral demands are legalized, people will more and more refer only to law as their behavior guidance. What's required in law, they obey it. What not, they ignore it. They completely abandon what is required morally. Say someone falling onto the street and there's no law to require people to help those falling on the street so that no one comes forth and they just leave the poor guy lying there. Imagine how that world would be like. I assume when Yao uses the term legalized, what's meant there is not legally permitted, but legally required. So the question really is whether people should or should not be legally required to visit their parents frequently. Okay, now, in this rendering, it's not entirely clear what the premises of this argument are, so I've taken the liberty to put it in standard form, and I hope I've interpreted it correctly. Yao, please do correct me if I haven't done the argument justice. And here's how I understand it. Premise 1, it is a moral duty to visit aged parents. Premise 2, creating legal obligations to fulfill moral duties reduces the imperative to fulfill those duties. Now notice, I've introduced the phrase, reduces the imperative. I've introduced that phrase to try to find a way to express what it is that Yao has in mind in this argument. And I'll talk about that phrase, reduces the imperative. I'll talk about that phrase in just a moment. Premise 3, things would be terrible if the imperatives to fulfill moral duties were reduced. So, from 3, what follows is 4, we should not reduce the imperative to fulfill moral duties. And from 2 and 4, what follows is 5, we should not create legal obligations to fulfill moral duties. And from 1 and 5, what follows is 6, we should not create legal obligations to visit one's aged parents. Okay, so that's a deductive argument. It has some nice structure to it. But I'd like to ask, is this a valid argument? I think the answer is no. And the answer is no for 2 reasons. The first reason is relatively simple and obvious, which is that I think step 4 doesn't follow from premise 3. Premise 3 says things would be terrible if the imperatives to fulfill moral duties were reduced, and step 4 concludes, so we should not reduce the imperative to fulfill moral duties. But I don't see that follows. Let's say it's true that things would be terrible if the imperative to fulfill moral duties were reduced. How does it follow from that we should not reduce the imperative to fulfill moral duties? I mean, you might think the way it follows is that we shouldn't do something that would have a terrible result. But that's not necessarily true. Suppose that things would be terrible whether or not the imperative to fulfill moral duties were reduced. In that case, what difference does it make to whether or not we should reduce the imperative to fulfill moral duties? Either way, things are going to be terrible. So, just because things are going to be terrible if the imperatives are reduced doesn't mean we shouldn't reduce the imperatives, because things are going to be terrible if the imperatives are not reduced too. Maybe I can make this point clearer by making the following analogy. I remember once hearing someone say in an ad campaign on TV decades ago, if you take drugs, you will die. And I thought, well, that's right. If you take drugs, you will die. Does that mean you shouldn't take drugs? No, it doesn't mean you shouldn't take drugs, because even if you don't take drugs, you will die. So, just because if you take drugs, you will die, doesn't follow that you shouldn't take drugs. Similarly, here, where premise 3 says things would be terrible if the imperatives to fulfill moral duties were reduced, well, you don't want things to be terrible, but on the other hand, things might be terrible even if the imperative to fulfill moral duties were not reduced. In fact, things might be even worse if the imperatives to fulfill moral duties were not reduced. So, whether or not we should accept step 4 of the argument doesn't just depend on our accepting step 3. Step 4 doesn't follow from premise 3. We'd need more information in order to reasonably accept step 4 of this argument. So I said that's one problem with the argument. That's the obvious and straightforward problem with this argument. But I think there's another problem that's a bit more subtle. And that second problem has to do with ambiguity, specifically an ambiguity in the phrase that I introduced into Yao's argument, the phrase, reduce the imperative to fulfill moral duties. That phrase was intended to capture what Yao had in mind when Yao said people will more and more refer only to law as their behavior guidance. What is required in law, they obey it. What not, they ignore it. They completely abandon what is required morally. I was trying to come up with a clearer way of expressing what Yao meant when saying they completely abandon what is required morally. Of course, if what's required morally is also required legally, then they don't completely abandon what's required morally, because as long as they're following the law, they're complying with what's required morally. They're doing what's required morally as long as they're doing what's required legally, because what's required legally is required morally. It's not that they're not doing what's required morally. When Yao says they abandon what's required morally, I think Yao means something different than just they're not doing what's required morally. So what does Yao mean? Well, that's why I came up with the phrase, reduce the imperative to fulfill a moral duty, right? To try to get at what Yao had in mind. But notice that phrase, reduce the imperative to fulfill moral duty, can be understood in two different ways. It can be understood to mean that something reduces a person's motivation to figure out what it is that's morally required and do that thing because it's morally required. Or reduce the imperative to fulfill moral duty could just mean reduce the motivation to do whatever it is that happens to be morally required. Now, if we interpret the phrase reduce the imperative to fulfill moral duty in the first way, in other words, if we understand Yao, when Yao says they abandon what's required morally, if what Yao means is that they don't try to figure out what's required morally and do it just because it's required morally, if that's what Yao means, then I think premise 2 of Yao's argument is true, creating legal obligations to fulfill moral duties. Creating legal obligations to fulfill moral duties does reduce the imperative to fulfill those duties because it means that we no longer have as much motivation to figure out what it is that's required morally and to do it because it's required morally. Now, we just follow the law. We don't need to use our own judgment anymore. We just follow the law. So I think on the first interpretation of the phrase, reduce the imperative to fulfill moral duties. On this interpretation, I think premise 2 of Yao's argument is correct. Unfortunately, I think premise 3 of Yao's argument is not correct. Things would be terrible if the imperatives to fulfill moral duties were reduced. Well, why? I mean, suppose that the law required people to do all and only what's morally required of them. Now, I don't know that that's possible, but suppose it were true. Suppose that the law required all and only actions that were morally required. There was a perfect coincidence between moral requirements and legal requirements. Well, why would things be so terrible? As long as people actually followed the law, they'd be doing whatever it was that was morally required. They just wouldn't necessarily think of it as morally required. They wouldn't do it because it was morally required. They were doing it just because they were following the law. Is that such a bad thing? Would that lead to such a bad state of affairs? I don't see that. And maybe it would, but I don't see any justification for that claim. So, without further argument, I'd have to say that if Yao understands the claim that people will abandon morality, the idea that legally codifying moral requirements will reduce the imperative to fulfill moral duty, if he understands that to mean that it'll reduce people's motivation to figure out what it is that's morally required and to do it because it's morally required, well then I think premise 2 of Yao's argument is true, but premise 3 is false. But notice there's another interpretation of what Yao has in mind in speaking of abandoning morality, or as I put it, reducing the imperative to fulfill moral duty. The second interpretation, what Yao has in mind, is that something reduces the motivation to do whatever it happens to be that's morally required. Not because it's morally required, just for whatever reason. And on that interpretation, I think premise 3 is true. Things would be terrible if people didn't care to do whatever it is that happens to be morally required. If people didn't care to act in conformity with the requirements of morality, not necessarily because they're requirements of morality, just if people didn't care about doing what happens to be right, then I think that would be terrible. Right? People would be killing each other, stealing from each other, lying to each other. The world would be a mess. But while premise 3 is true on that interpretation, I don't see that premise 2 is true. Why is it that creating legal obligations to fulfill moral duties reduces the imperative to fulfill those duties in that sense of the term? Why does it reduce our motivation to do whatever it is that happens to be morally required? Look, it's morally required of me that I pay my taxes, but it's also legally required of me that I pay my taxes. And I'm pretty confident that I'm more motivated to pay my taxes because it's legally required of me than I would be if it weren't legally required of me. If it weren't legally required of me to pay my taxes, I might have some motivation to pay my taxes, but my motivation wouldn't be very strong. But now that it's not just morally but also legally required of me to pay my taxes, I have a very strong motivation to pay my taxes. And so I always do pay my taxes. So there's an example where introducing a legal obligation to do something that happens to be morally required can actually increase the motivation to do whatever it is that happens to be morally required, not decrease it. And I'm not sure why why visiting aged parents wouldn't be just another case of the same. So, in short, there are two possible interpretations of what Yao has in mind in speaking of abandoning morality, or as I put it, of reducing the imperative to fulfill moral duties. Two interpretations of what Yao has in mind. On one interpretation, premise 2 is true and premise 3 is false. On the other interpretation, premise 3 is true and premise 2 is false. But on neither interpretation is Yao's argument sound, because on neither interpretation are all the premises true. So even apart from the question of whether this argument is valid or not, the argument can't possibly be sound, because there's no interpretation of the crucial phrase on which all of the premises are true. Okay, and that's what makes this a fallacy of ambiguity. Okay, see you next time. In week 10 of our course, we studied fallacies of vacuity, including circular reasoning. Well, it was nice to see that one of the very interesting and also impassioned arguments delivered on the discussion forums was by Kim Johnson, an argument against capital punishment. And I think it'll be useful to discuss this argument in light of what we learned about circular reasoning. So, let's look at Kim's argument about capital punishment. Here's how the argument goes. These are her words, as quoted from the discussion forum. She writes, "When someone is proven guilty of murder with intent to kill, their crime is punishable by law. This crime is punishable because killing is not only illegal, but immoral and wrong. However, in various countries, capital punishment is still legal." I should mention that the United States is one of those countries. "Since taking another human being's life is wrong, it can't suddenly become acceptable because society decides a person deserves it. Regardless of that person's actions, however horrendous they may be, taking another person's life is never right. As humans, it is not our right to decide the value of a life and when it will end. Therefore, capital punishment is wrong and should be illegal in all countries. Okay, now let's try to set out this argument in standard form. It's a little tricky, but recall, when we're trying to set out the argument in standard form, the first thing we want to do is go through the different sentences and look for which sentences are actually supporting the conclusion, which are doing the work to support the conclusion, which sentences aren't supporting the conclusion, and then which sentences simply express the conclusion. Well, the conclusion is pretty clearly expressed in this last sentence. Capital punishment is wrong and should be illegal in all countries. I'll just abbreviate that. I'll say capital punishment is wrong. So that's the conclusion. Now, which statements in this text support that conclusion, work to offer that conclusion support? When someone is proven guilty of murder with intent to kill, their crime is punishable by law. That's a statement of fact. Does that support the conclusion that capital punishment is wrong? No, it doesn't. It just tells us, as a matter of fact, what crimes are punishable by law. It doesn't tell us anything about what's wrong. So we can delete that, because that doesn't do any work to support the conclusion. Okay? So that's not going to, that sentence, even though it's true, is not going to make it into the standard formulation of the argument. When we put the argument into standard form, that sentence isn't going to be there. Okay, then Kim continues, this crime, murder with intent to kill, is punishable because killing is not only illegal, but immoral and wrong. Okay, so she says, killing is not only illegal, right, but the fact that it's illegal, we've just said, is not relevant to supporting the conclusion, but immoral and wrong. So killing is immoral and wrong. Okay. However, in various countries, capital punishment is still legal. Okay, does that last sentence do any work in supporting the conclusion that capital punishment is wrong? No. Again, that's just a statement of fact. It doesn't do any work to support the conclusion that capital punishment is wrong, so we can delete that because that's not going to make it into the standard formulation of the argument. All right. Since taking another human being's life is wrong, it can't suddenly become acceptable because society decides a person deserves it. Regardless of that person's actions, however heinous, however horrendous they may be, taking another person's life is never right. Okay, so what's the point of these two sentences? The point seems to be simply that taking another person's life is never right. Is never right. Okay. As humans, it is not our right to decide the value of a life and when it will end. Therefore, capital punishment is wrong. Okay, so what are the points that support the conclusion that capital punishment is wrong? Well, they seem to be these. Killing is immoral and wrong. Taking another person's life is never right. And it is not our right to decide the value of a life and when it will end. Well, that we don't have the right to decide the value of a life isn't really relevant to supporting the conclusion. So what's relevant is that we don't have the right to decide when a life will end. But these statements all seem to be different ways of saying the same thing, which is that no human has the right to decide when a life will end. Right? The four sentences that we just isolated in Kim's prose all seem to be different ways of stating that same point, the point that no human has the right to decide when a life will end. And so when we put her argument into standard form, it looks to me like the argument just has one premise, stated in different ways, and a conclusion. Therefore, capital punishment is wrong. Now, this argument, let me just say, this argument may very well be sound. That's to say, the argument may very well be valid and its premise may be true. But if you don't already have a good reason to believe the conclusion, then why should you believe the premise? The premise says that no human has the right to decide when a life will end. Right? Not the executioner, not the judge, not the jury, not any representative of the legal system, not any authorized human, under any circumstances, has the right to decide when a life will end. Now again, maybe that statement is true, but can you be justified in believing that statement without already being justified in believing that capital punishment is wrong? Well, maybe you can, but that's hard for me to see. I would think that in order to be justified in believing that no human has the right to decide when a life will end, you'd already have to be justified in believing that capital punishment is wrong, which it may very well be. Capital punishment may very well be wrong, but I don't see that this argument shows that it is, even if this argument is sound. So how could a sound argument fail to show that its conclusion is true? Well, it could fail to show that its conclusion is true because even if the argument is sound, we might not have any reason to believe that it's sound. In particular, we might not have any reason to believe that the premises are true unless we already had a reason to believe the conclusion. So if we don't already have a reason to believe the conclusion, then even if the argument is sound, we might not have a reason to believe the premises. And so the argument can't give us a reason to believe the conclusion. Right? Arguments give us reasons to believe their conclusions only insofar as we already have reasons to believe their premises. But if having reason for believing this premise requires us to already have a reason for believing the conclusion, then this argument can't give us a reason for believing its conclusion. So this argument, I say, is an example of circular reasoning, which is a form of the fallacy of vacuity. But thanks very much for the fascinating example, Kim, and for bringing up an extremely important issue about which I think much more needs to be said. Okay, see you next time. In week 11 of the course, we talked about refutation, and in particular, we talked about refutation by parallel reasoning. Well, it was nice to see that one of you on the discussion forums submitted an example of refutation by parallel reasoning. And so today I'd like to talk about that particular example, and I'd like to assess whether or not the refutation is successful, whether or not the reasoning that it uses really is parallel. Okay, the example is one submitted by Maximiliano Marzetti, and Maximiliano, please forgive me if I've mispronounced your name. The example is called, "If God does not exist, neither do barbers." Here's how it goes. So, Maximiliano argues, premise 1, there's suffering in the world. Premise 2, if a God existed, he would not tolerate suffering in the world. Therefore, conclusion, God does not exist. Now, that's a familiar argument. Many of us have heard it before. Many of us have thought about it before. But Maximiliano intends to refute that argument by parallel reasoning. So here's his parallel reasoning. Here's how it goes. There are people with long hair in the world. This text is directly copied and pasted out of Maximiliano's contribution to the discussion forums. There are people with long hair in the world. Premise 2, if barbers existed, there would be no people with long hair in the world. So, conclusion, barbers do not exist. Okay. Here are two arguments, and superficially, they might seem to be parallel. Clearly, the second argument is just terrible, right? Because there are people with long hair in the world, so premise 1 is true. And the conclusion that barbers do not exist is clearly false, but so too is the second premise. If barbers did exist, there would be no people with long hair in the world. Since the second argument is clearly terrible, Maximiliano's suggestion seems to be that the first argument must also be terrible, since it seems to share a form with the second argument. If the second argument is a failure, then the first argument must also be a failure. But is this right? Well, I think there's a problem with the analogy that Maximiliano tries to draw between the two arguments. The problem is this. The first argument has a second premise that says if a God existed, he would not tolerate suffering in the world. Okay, and why should we accept that second premise? Well, because God, at least as understood by many people, is a being who is omniscient, omnipotent, and omnibenevolent. That's to say, God is a being that knows everything, can do anything, and wants only good things. Right? So, since God wants only good things, God doesn't want for there to be suffering. Since God can do anything, God could eliminate suffering. And since God knows everything, God knows when suffering would take place without intervention, and so God knows to intervene so as to eliminate suffering. So it seems as if a God, understood as a being that was omnipotent, omniscient, and omnibenevolent, if a God existed, he would not tolerate suffering in the world. That seems like a somewhat plausible premise. But now notice the second argument, the argument that Maximiliano wants to suggest is parallel to that first argument. The second argument relies on a second premise that says if barbers existed, there would be no people with long hair in the world. Well, now, why should we believe that? And in fact, barbers do exist, and there are people with long hair in the world. Why should we think that barbers would make it so that there were no people with long hair in the world? Is it just because barbers are meant to cut hair? Well, sure, barbers are meant to cut hair, but just because they're meant to cut hair doesn't mean that they make everyone's hair short, first of all. Right? Barbers don't make everyone's hair short. A barber can cut your hair but still let you have long hair. And anyway, barbers are not omniscient, omnipotent, and omnibenevolent by anyone's lights. That's to say, just because barbers are supposed to cut your hair doesn't mean that they want to cut everybody's hair. It doesn't mean that they have the power to cut everybody's hair, that they have the ability to cut everybody's hair. And it doesn't mean that they know how to cut everybody's hair. There are probably a lot of people in the world that barbers don't know anything about and wouldn't know how to get to. Right? So there are obstacles to barbers cutting everyone's hair short that there aren't to God's making sure that no one suffers. Right? God doesn't have any obstacles in the way of making sure that no one suffers, but barbers have lots of obstacles in the way of making sure that they cut everyone's hair short. So just because God could eliminate suffering if God wanted to, it doesn't mean barbers could eliminate long hair if they wanted to. So there is a problem with the analogy that Maximiliano wants to draw between the first argument and the second argument. And it's because of that that I believe this is not a successful refutation by parallel reasoning. That's to say, the first argument, the argument that God does not exist, is not refuted by Maximiliano's parallel. It might be refuted by other considerations, but it's not refuted by this. But thank you, Maximiliano, for the interesting example of a refutation by parallel reasoning.
Okay. Finally, as the last argument in this course, is the one that bothers me most. And it comes from Lauren Brush. I think it must have bothered her too, because it's not clear that she was ever happy with the formulation and kept changing it. But I'm going to give a very simplified version of it and see if we can reconstruct it and determine whether it's really sound. This is what Lauren said. In my words, not hers, exactly. Walter wants to up the number of students who get the most out of this class. Now that's true. I want to increase the number of students who get the most out of this class. That's the point of teaching. Therefore, Walter should shave his hair on camera and make the video open to all students. No, my beautiful locks, no. That is what's upsetting. But luckily, this argument's not valid. No way. It's possible for the premises to be true and the conclusion false. So, sorry, Lauren, I'm not convinced. Uh-oh. She can add another premise. She's probably assuming this. More students will get the most out of this class if Walter shaves his hair on camera and makes the video open to all students. Okay, I guess I got to admit that too. I think people will get more out of the class if they see that, because part of what you get out of this class is you have some fun. At least I hope you've had fun. I have. Okay, Lauren, but still, it's not valid. It's not valid, and so I'm not going to shave my head yet. No way. Uh-oh. The main reason it wasn't valid was that the premises were about what I want, and the conclusion is about what I should do. But wait, now maybe it is valid. Sure looks valid if we add one more suppressed premise. Walter should do what will accomplish what he wants to do. Oh my gosh. But if what I want to accomplish is to get more students get the most out of the class, and if I should do what I want to do, then I should do what's going to make the most students get the most out of the class. And if shaving my head is doing that, then it sure looks like I should shave my head on camera and make it open to all the students. I feel like I'm in trouble now. What's going to happen? Oh, wait, I've got it. Even though it's valid, premise 3 is not true. That I should do what's going to accomplish what I want? What if I want something like, I want to smoke? Well, maybe I shouldn't go to the store and get a pack of cigarettes, because even though I want to smoke, I still shouldn't, because it's bad for me, because it's going to hurt me. So, it looks like you have to qualify that premise by saying that I should do what will accomplish what I want to do, unless doing it has worse effects, like in smoking, when it might give me cancer and hurt me. So, now I'm safe. Now I don't have to shave my head. That makes me feel better. Because you can't get the conclusion that I should do it from those 3 premises, right? It's not valid anymore. Oh, he needs another premise. Walter shaving his head on camera and making the video open to all students will not have worse effects. Because shaving my head is not going to give me cancer like smoking. Matter of fact, hair will grow back. It might be embarrassing for a few days, but only a few days. That's not that bad compared to all those students out there in Coursera land. And so I guess I have to admit that premise 4 is true. But wait a minute. If the argument is valid, and premise 4 is true, and premise 3 is true, and premise 2 is true, premise 1 is true, now it's looking good. And we can even break it up to make it easier to understand. I want the number of students to increase that get the most out of the course. More will get most out of the course if I shave my head on camera and make that video available. So shaving my hair on camera, making the video available will give me what I want, and I ought to do what I want if it doesn't cause worse harm. This is not going to cause worse harm, so I ought to do it. Oh my gosh, now I'm worried, because that means that the conclusion's true. If the argument's sound, it's valid, and the premises are true, then the conclusion's sound. Or at least if I accept the premises and the conclusion follows validly, then I'm committed to that conclusion. I'm committed to the fact that I should shave my hair on camera and distribute the video to all students so you can all watch it. Lauren has convinced me of that. But notice, this argument applies to me, it also applies to Rom. So if I've got to shave my head, Rom's got to shave his beard. So, although I have to shave my head, at least I'm not alone. Guess we gotta both go do it. I'm committed to the fact that I should shave my hair on camera and distribute the video to all students so you can all watch it. Lauren has convinced me of that. But notice, this argument applies to me, it also applies to Rom. So if I've got to shave my head, Rom's got to shave his beard. So, although I have to shave my head, at least I'm not alone. Guess we gotta both go do it.
Okay, so I'm convinced that I should shave my head, but I'm just not gonna do it. I don't know if I could live without my beautiful locks.
Yeah, I know exactly what you're talking about. I mean, I'm equally convinced that I should shave my beard, but it just doesn't feel right somehow.
I know. There's no way they're gonna force us.
I don't think it's gonna happen.
No.
It's just not gonna happen.
Yo, I'm gonna make you do it. Dude, you need to recognize the power of reasoning and argument.
Oh no, he got me.
Thanks to all of our students. We hope you learned a lot and had a lot of fun. We sure learned a lot from you. I remember learning about goats from a goat farmer in Afghanistan, and AIDS from an AIDS activist in Africa, and traffic flow from an Australian engineer, and wild dogs from a student from Eastern Europe. We've also been inspired by a lot of students. One student had her house destroyed by a cyclone and apologized for missing a deadline. An Iranian group of linguistics students met together every week, and so did a group in a cafe in San Francisco. We had visually challenged students from Eastern Europe, and one student with a chronic disease that had never been able to take a college course before. So now, sadly, we have to say goodbye, but we hope that the lessons will stay with you. Our goal has been to teach you to, first of all, ask whether you have good enough reasons for the positions that you hold, and then to enable you to formulate those reasons better when you do have good reasons for your own beliefs, but also to pay attention to other people and appreciate and be fair to opponents who hold different positions. So please use these skills throughout the rest of your life. They will help you cooperate with other people and succeed in your own goals, whatever you want to accomplish.
So now there are only two things left to do. One, we'll send all that here to Locks of Love. And two, now that it's all gone, you might as well paint my entire head Duke blue. I don't know, I got my doubts now, but it did seem like a good idea at the time. Luckily, I'm not going to be alone. Rom, your turn.
So listen, you gotta make sure nobody knows about this, okay? I do not want to be associated with that big Duke Blue clown, okay? So nobody can know about this, all right? You don't tell anybody? All right. Good man. Okay. We are so grateful to all of you for taking the time out of your busy lives to take our course and help us make it even better for future generations of students. Thank you to the graphic designer from Mexico who secretly wants to go study philosophy. Thank you to the retired social worker from Darwin, Australia, who is studying to become a workplace meditation consultant. Thank you to the recent college graduate from the Philippines who stuck with our course even when the massive typhoon tragically devastated her country. Thank you to the polite gentleman from Huntsville, Alabama, who had to stand up to the criticism of his peers in order to take our course. Thank you to the young man from Rio de Janeiro who did the problem sets in the middle of Carnival. Thank you to the barber from Cairo who would complete the quizzes whenever he had a break between clients. Thank you to the taxi driver from Bangalore who would contribute to the discussion forums using voice recognition software while driving. Thank you to the hypnotist who found time to complete our course while also getting all of his clients to do so as well. And thank you to the anesthesiologist who would read our lecture transcripts out loud while at work. It is because of all of you that our work was worthwhile.
Bye, guys. Thanks for doing such a great job. Bye.